Yad, siéntate. Good morning, everyone. Carlos, siéntate. Good morning, everybody. Welcome to the 9th edition of the Photonic Integration Week. It's always a pleasure, and we've been thinking a lot about this event lately. So we started in 2017, and we've done it every single year, except one because of the COVID-19. And we're really happy to see that this is growing, that it is of your interest, and that you find it useful. Mostly companies find it very useful to come and gather together for this 1 day and a half, but we also attract as well part of the academy, young students that want to see the ecosystem directly, and I think that this is a very nice mix. So you are the stars of this. I won't take long. We have 1 day and a half, as I said, 5 sessions, 3 sessions today, 2 sessions tomorrow morning. First session is devoted to clusters working around photonics, and we want to know the vision with respect to everything that is happening in semiconductors at large, but as well what it takes to photonic integration. So I won't say anything else. I will welcome Sekfo to a stage for the first presentation.
Okay. Thank you to the University Polytechnic of Valencia for organizing every year this event. I'm Elizabeth, and I would like to talk to you today about how building competitive advantage in integrated photonics. Let's start with the market reality. The global integrated photonic markets is expected to grow from $13.6 billion in 2025 to more than $25 billion by 2030. This means an annual growth than more than 30%. It's a lot. This is not an incremental growth. It's a structural acceleration, I think. Thank you. What we are witnessing now is a transition from experimental photonics to industrialized photonic systems production. And one of the main drivers of this great growth is because the artificial intelligence is one of the main drivers. Artificial intelligence is creating an unprecedented demand for optical transceivers. As computing power scales, electrical interconnects become inefficient, and then optical interconnects are no longer optional. They are becoming essential. So integrated photonics is therefore moving from a specialized technology domain into a critical infrastructure for digital transformation. Then we observe that beyond market growth, we also have to consider the strategic investment landscape. As we can see, at European level, CHIPS Act provides the strategic framework, and then initiatives as PICS Europe, coordinated by ICFO with more than 400 million investments, and at national level, Spain participates with PICS Spain, coordinated by the University Polytechnic of Valencia, that is connecting Spanish capabilities to European pilot lines. And then we have also Micro Nano Spain, that brings together the country micro and nano electronic infrastructures, strengthening access to fabrication and prototyping capabilities. Together, all these initiatives show us a great strategic momentum. They build capacity, they build infrastructures. So let's talk about the market. This market growth and this investment in infrastructures alone does not guarantee a competitive positioning. We must capture industrial value, and this requires more than technology. First, I think we have to work in the ability to industrialize, to move from the lab to a scalable production. Second, we need an activation of the demand. Strong local industries willing to adopt and integrate these technologies. And third, the most important is coordination, alignment between science, talent, capital, and industry. Because without coordination, even a strong technological ecosystems like a Spanish ecosystem struggles to scale. Okay, so what we think at SECFO, that is at the starting point in Spain. If we look at the Spain position in integrated photonics, for one side, we have strong capabilities. Spain has a solid base in photonics and related deep tech technologies. We have internationally recognized research centers, universities, and highly specialized companies. Over the last decade, photonics has increasingly converged with semiconductors, artificial intelligence, advanced materials, and sensing. But at the same time, we face structural challenges. Our ecosystem, I think, is still fragmented. Industrial scale in certain segments remained limited, and the transition from research and development excellence to large-scale implementation is not always as fluent as it could be. I think the challenge is not talent. We also have the investment. The challenge is coordination to scale. Except for during these years, we have been in more than 15 years in photonics and now in deep tech. We have observed that there is an innovation gap, that it's not only one innovation gap. There are like three critical, I think it's, well, this slide is not working very well, but well, there are three gaps between the proof of, and the most critical ones are from the proof of concept to pilot, and then to scaling the product to the industrial and to the market. Okay, and then we have to work in these three gaps. We know that in Europe, and Spain included, we perform very well in early and mid-stage. That means TRL 1 and 7, but fails in the transition to TRL 8 and 9. We are strong in research, we are strong in validation, and also pilot lines are helping to demonstrate feasibility. They reduce a lot the technical risk, they validate processes, but I think pilot lines alone are not business models. So the real difficulty begins when we move from pilot success to industrial scale. TRL and 9 requires something different: volume manufacturing, integration into real industrial systems, and sustained market demand. I think without a clear path to manufacturing at a scale and adoption in real markets, even the most advanced pilot facilities risk becoming cutting-edge infrastructure, but with not a lot of long-term customers. So what can we do to work on that and to bridge that gap? I think it requires coordination. Ecosystems like SECFO, ISME, these events that we are organizing to bring together our knowledge are very important because we have to operate as a united ecosystem infrastructure, not just a network. And during this year at SECFO, we have been building like a methodology to connect this collective intelligence, the market, the science, and then I think that we have speak a lot of strategy and positioning, and what I want to do now is go deeper in what we do at SECFO and how we think we can help. So for that, I will call my colleague Sandra, and she will explain how we work here in SECFO.
Thank you, Eli. Sorry, I have a little bit cold. Okay, there was the animation. Okay. Okay, so let me tell you a little bit about our history and how we became what we are today. We started as a Photonics cluster 2009, and the purpose was to unite every actor on Photonics ecosystem in Spain, because there was no Photonics cluster in Spain at that time. So we got on that ride and we started building a community. That was our goal back then. And then we started growing, we started reaching every actor that was doing something, was doing innovation in photonics and had strong capabilities in photonics. And as we grew, as we were uniting all these companies and different entities, we thought to ourselves, okay, the applications of photonics, it's so broad. If we don't stop here and we get to create an ecosystem that it's connecting not only photonics, but all of the other deep techs that are connected to photonics, and photonics have like strong synergies with, and if we combine them together, they can do a deeper level of technological innovation. We dreamt about this, about building a different ecosystem and inviting other actors and other technologies into our ecosystem. So this was in 2018. We did that jump and we opened our cluster to from a photonics cluster to a deep tech ecosystem, and we invited all of the other deep tech technologies into SECFO just to strengthen this collaboration and just to create a really strong like network. I think that's really an important word for us, to create a strong network and to promote collaboration. Okay, so that's where we are now. As you see, the growth's been really nice. And this is what we are today. All of these logos are the companies that belong to SECFO right now. There are a lot of different entities. We have end users, we have research centers, we have universities, we have research groups of universities, we have startups, we have SMEs, all of these different kind of entities, and all of them together, our goal is to connect them to promote their collaboration and just for them to share their capabilities with each other and see how they can keep collaborating together. So that's our role, and that's how our ecosystem looks right now. These are some stats. As you can see right now, together, combining all of these companies that you saw earlier, we have like a network of 1,200 experts in deep tech and all of these different disciplines. 165 patents published per year, because we are really strong on research and we are advocates of this. This is really important for us. Also, scientific publications, millions of euros in annual revenue. This is all collective stats, okay? But we are really proud of these numbers because this is our ecosystem. Okay, so when we did that jump, when we went from photonics to deep tech, this is all of the deep tech technologies that were introduced into SECFO's ecosystem. So, as you can see, microelectronics and semiconductors, AI and data, quantum technologies, advanced materials. I don't need to read all of them, but you can see. And our goal, of course, was how to connect photonics with all of these other technologies and how the photonic technologies can apply and collaborate with all of these other technologies. But we are focusing on photonics today because we are in the few. This is Photonics in our ecosystem. This is all of the actors that are focused in photonics in our ecosystem. As you can see, a lot of them are here today. Maybe some of them will come tomorrow. But yes, this is really strong and different ecosystem, and we have from startups and spin-offs, from research centers, from universities and everything. So this is how it looks right now in SECFO when it comes to photonics, and we're really proud because there's more. We have right now like up to 170 companies, and more than 60 of them are photonics. So we still have a really strong core in photonics. And how do we connect this ecosystem? What do we do to connect it? We really take pride in our events. We organize a lot of them, a lot of them online in online format for them to be comfortable, and everyone gets to come and gets to promote their capabilities and their ideas and their innovations. So it's really great. And also we also do. Events in person, those are really great too, for them to just connect in person and keep out that barrier of online meetings. And yes, this is a great chance to promote networking and to dynamize it in a way that they are having a great time, but also focusing on building projects together and how they can share the capabilities with each other and maybe foresee future collaborations also. This is some pictures. As you can see, we have really great times when we gather together. Okay, all the ways that we promote the collaboration in our ecosystem and how do we do it? We are really close to end users. Some of them are a part of the SECFO's ecosystem. Some of them are really close friends. They're not in a cluster, but we really have open lines of communication with them, and we have our own methodology. We scout all of these technological challenges. We get close to them. We try to understand what's their challenge and what do they need. We manage these challenges mostly in sectors, and because a lot of technologies maybe can be used combined to solve one technological challenge. So we categorize them by sector, and yes, we do this challenge approach and with the end user. Also, we do the tech scouting. We send this technological challenge to our ecosystem. Everyone that gets to identifies that they have potential capabilities or capacities to solve this challenge, they apply, and we send all of these companies to the end user. And sometimes when there's a lot of actors that can solve this technological challenge, we do innovation workshops where we gather all of these companies with the end user, and they get to do maybe a short presentation where they show their technology or several projects that they have worked in that maybe can apply to the technology that they need. And these are really, really good sessions that work very well. And after that, we do working groups. But this is one of the ways that we are trying to break that barrier between the industry, the end users that need this technology, and all of the companies that are part of SECFO, just to promote their technology and to show their capacities, and maybe for them to collaborate together even, because maybe someone is doing photonic an imaging sensor that can be combined with AI and data, and we gather all these actors so just for them to collaborate, and that is our main goal, the collaboration. These are some of the projects that have come out of these technological challenges where they collaborate together. Some of them are also from public subventions calls where we applied as an ecosystem, and these are really great projects for us. I'm not going to read every one of them, but all of the ones that I'm showing here, they use photonics and sensors or lasers. This one was really great. Also, this one was a laser vision system for a surgical robot with all of these. You can see the logos of the companies that were involved in this project. And these have been really great because it's going from an idea to actually a prototype and a pilot. And that's been really great for us, like seeing technology come to life. And yes, this was just some examples for you to see, but if you're interested in knowing more about them, you can reach me or my colleague later and we can see them. But this is all of these are focused in photonics or laser or photonics technologies or quantum. And yes, a lot of other action that we are actually doing right now. We are building a SECFO catalog. This is to display all of the capabilities of the SECFO ecosystem. We are preparing this as we talk, final touches. And we are really proud to say that CEDETI is sponsoring this catalog. And this is really great for us. This is a great achievement for us that a public entity as CEDETI is recognizing SECFO's ecosystem, and they believe that we are strong in deep tech and in photonics, and they believe what we're doing is good and it makes sense for them also. This is just an example of how does it look. It's really visual. We didn't want to be a lot of letters and everything. We really wanted to show product and just to be really visual and show the capabilities of the ecosystem. And yes, we will do a presentation event of this SECFO's catalog at CEDETI, actually, in March. And this is really great for us. This is the first edition that we are preparing. And it's exciting because the aim is to become a reference guide for the deep tech ecosystem, and anyone that looks at this catalog can really see the capabilities of the deep tech ecosystem in Spain at a glance, like something really quick and easy to consult. And if any of you is here in March and want to come to this event, you can go to SECFO's schedule and just subscribe there to register to attend if you want to. And yes, thank you everyone for your attention. And me and Ellie, we have a booth. If you want to reach any of us, you are welcome to come later. Thank you.
Hola, sí, now, sí, thank you, gracias. Thank you, no, don't go away. Ellie escaped, but you have to stay. Now Ellie can come to stage. So, well, thank you for the nice presentation, Ellie, Sandra. Is there any question from you to SECFO? Guillermo.
Thank you very much for the presentation. That was really interesting. And actually, I wanted to ask you, when you've shown this innovation gap, when you mentioned that we fail at the end in the industrialization, is this in the photonic sector? Is it at the level of the country? What is the statistics that you have collected there? Is our sector, or is in the whole industry, or even at European level?
We analyze it in Spanish level, and not only photonics, I think in general innovation in disruptive technologies. We talking with our members, with the industry, we see that there are these three critical gaps that mean to focus and maybe assessment to go to the next step. But I don't know at European level is what we know during this year in our ecosystem.
Thank you. Any more questions? I have maybe a question, Sandra. You mentioned that yes, you organize gathering together, so workshops, events, but can you describe a little bit like which type, how many people, if they are more or more focused?
Yes. Actually, Ellie is in charge of doing all of our event agenda, so I'm going to...
Okay, that's fine.
Yes. We have designed some like 6 type or 7 type events from, for example, we have tech meetings that are little events with maybe 20, 25 members focus on one technology. For example, the last one was imagine and artificial intelligence applied to the, cancer diagnosis. These are very focused in a technology applied. Sometimes we invite industry, in this case we invite hospitals to know about this technology, and we debate about the potential, how we can collaborate, and knowing the state of art of this technology. Then we have market focus that are more are online also, and more huge events like 80, 100 people connected online. It is more presentations, very short presentation to at a glance, and maybe in 1 hour, 1 hour and a half, know a lot of technology in one market. For example, in energy sector. Today we are having one in it's called Agriculture 5.0 that it's about advanced sensoring, artificial intelligence, applied to agriculture. So here we can invite industry to come, and they are open events. So we have the innovation workshops that Sandra explained that are more focused in a challenge. Then we have best practice that are more to help startups and spin-off in more practical issues, and maybe with how to find investment, how to speak with the investors, how we can, well, very, very practical ones, more financial ones maybe. And I think these are the most important. And then the presential events are, we try to be very creative and original and do more, a lot of dynamics to connect the maximum people to speak about it. So maybe very short meetings and or gaming dynamics, and we are very focused on try to do it funny, and I think that's most of them.
Okay, thank you. Is there any additional question? Yes, over there.
So from what I've seen, like some of these companies are also like competitors in between themselves in some product range or some sector. Like, how do you manage to keep away this competitiveness between them, or do they not show the full picture of their things? Or yeah, I think you understand.
Yes, that's been an issue in the past, but about some companies. But most of them are really open to collaborate between them. It's really funny because when you gather them together in a room, maybe some of them are focusing on the same technology, but they are not experts on the same discipline or super concrete device that they're applying this technology with, or maybe. And so we've seen that most of them are really open to talk between them, and even when we do when we send a technological challenge, all of them apply, and maybe we do these innovation workshops and they do their presentation about the technology, and they're super open to talk between them, and we think that's really great because innovation does not happen alone. We build it together, as we said, right? Because we need to work together, and it's better for two companies that are focusing on the same technology work on a project together than none of them working on a project together. So I think they understood, and I think it's great that we are like destroying those barriers, and they're speaking with each other, and I think we've built something nice. We didn't have much of a problems in these late years.
Thank you.
Okay, thank you. Let's thank Ellie and Sandra again. Thank you.
Thank you.
And now we welcome to stage Sergio Vicente from ISME. Welcome.
Maybe if I have this, there is no need for. Okay, so good morning, everyone. It's a pleasure to be here. First, I would like to say thank you to the organization for inviting us, ISME, to present our vision about the Spanish ecosystem, Spanish semiconductor ecosystem. As I said, well, I will start with some introduction. I'm Sergio. I recently joined ASMI like 3 months ago. So if possible, don't make me any difficult questions, please, or be merciful with me. I recently joined, and I came from a company you may know, is ASML. I studied, so more in a personal level, I studied here in the university. So for me, it's a really nice day to be here, coming back and seeing that in Spain we are doing something that is related to photonics and semiconductors, which is really a strong industry now. So then today I will walk you through the Spanish semiconductor ecosystem. As I said, this is not a static map of institution. I think SECFO really showed what is this about. So I will show you a dynamic and interconnected and rapidly evolving system. So then let's get started. First, what is ASMI? Is the Spanish Semiconductor Industry Association with a clear mission, simple but strategic, which is give visibility, coordination, and representation to all actors in the semiconductor value chain in Spain. As you see here, we have members from startups to universities, so startups pushing disruptive architectures. We also have members, SME members with mature technologies. We have not so much large international firms, but we also have some. And we have RTOs, or research and development centers, and universities also part of the ecosystems. So I wanted to mention here that this is what implies an ecosystem. Here is interdependence, talent flow, and shared infrastructure, and also you need to align in some policies. So then this is not a picture of just fragmented institutions. We are trying to gather all of them together so we can act as a fully ecosystem. Next, I want to show some numbers about the semiconductor overview. We have 160 companies, 50 universities, or plus 50 and plus 160, and plus 30 RTOs, which they represent activities from design, manufacturing, packaging, photonics, that should resonate here, quantum and advanced materials, for example. So then I think Spain has one of the most diverse semiconductor ecosystem, because in some countries in Europe they have this technology but they don't have the other. But in Spain I think we have a good mix of everything. So then that is always good. We have also 3 important factors in our opinion, which is the academic density and the public R&D capability. We will discuss later about the funding and everything. And we have an emerging entrepreneurial moment because of the public fundings that are going on, and that Europe finally took seriously the semiconductor ecosystem. I wanted to show you just briefly as well this map, because I think it shows that we have several hubs, let's say, with some concentrations of companies and RTOs and so on. You can see that we have Madrid, Barcelona, and Valencia, and Basque Country as well as the hubs that I was mentioning mainly. And then, for instance, Valencia is internationally recognized here for silicon photonics. This this ecosystem or this map shows that cross-regional collaboration is key to strengthen the ecosystem, because usually those hubs, they tend to be specialized in something. So cross collaboration between region, I think, is key. Another semiconductor overview slide about what is the composition of the ecosystem is, you need to think that roughly 1/3 of the semiconductor companies are startups. So when we say startups, we mean 4 years or less of activity. And then nearly 30 international companies have established operations in Spain. And this dual dynamic matters, in our opinion, because startups generate innovation, and international players may bring a scale to the ecosystem. So let's go to the next one, which shows a bit more detailed the value chain distribution by services in this case. So then you see that we have a strong focus on fabless and backend and EMS, which the front end is not so strong. What they do, no, in those services, what the companies do for which technologies they use is basically, the first one is photonics and optoelectronics. We are also leaders in RISC-V to really or driving Europe's efforts to develop architecture for microelectronics. We also have quantum computing to highlight because it's globally competitive. And I wanted to mention as well manufacturing, even though we are limited in volume in Spain, but we have a high specialization potential in here. I think Spain's comparative advantage lies in advanced and knowledge-intensive segments rather than high volume, because what I said, in limited manufacturing capabilities. Another slide showing how we distribute by value chain position. You see we have design and IP and testing and assembly and equipment materials. We have strong positions. As I said before, manufacturing is not so strong in Spain, or at least it's not, its volume is not high enough, let's say. What does it tell us? Spain is strategically targeted towards advanced technologies like, for example, power electronics or specialized processes and advanced packaging, for example. So then I would say semiconductor industry is, the identity is design driven with growing back-end and strategic manufacturing ambitions. Let's see if we can scale up with the manufacturing part. Now I'm going to show you some numbers or metrics about the industry, the semiconductor industry. We as ISME, we were born in 2021, so we are not so old, let's say, as SECFO. So we have different associates, different numbers. We have this 1 billion annual revenue, and this, as I said, this is calculated or estimated with figures, internal figures with ISME data, because it's not so easy in Spain to collect semiconductor industry figures, because we don't have the identification code, especially for semiconductors. So the companies, they usually register with the final end use of the product that they are selling, or with the providers, or with the customers. So yeah, in that sense, it's difficult to collect numbers. We have 6,000 direct employment in the semiconductor ecosystem, and then we see, this is more generic, we see also huge R&D investment, and the active patents in total are increasing. So I think this suggests a maturation process, not a stagnation, so we need to seize the moment, because the momentum, I think, is now to really scale up, as I mentioned before as well. Now I want to show you a bit the key players in this ecosystem, or describe a bit what are the key players in the ecosystems, in this ecosystem. As I said at the beginning, Spain hosts internationally recognized RTOs with hundreds of researchers per organization, advanced nanofabrication facilities for integrated circuits, photovoltaics, power devices, quantum, you name it. I think, as I mentioned before, we have the most diverse, or one of the most diverse ecosystems in Europe, because we have mainly all the technologies. And then these RTOs are especially important because they act as technology incubators. No, they have, or they can provide some infrastructure. No, and they are talent multipliers because they are innovating hard. They are innovating a lot. I think that's what I wanted to say about the RTOs. Now we move to leading universities. We are in one of them, so you know that Spain's top technical universities provide talent to the ecosystem. And we have over 50 universities contributing nationwide. Some of them became national and international reference in their fields, so that is important when you have an ecosystem to have this backbone to really support the industry and the ecosystem itself. Because, as you know, without engineers there are no chips, and without researchers there are no innovation. So I think leading universities are really needed in this ecosystem. I forgot to mention that we also have strong collaborations with industry leaders and internationally, so that also helps us to connect through universities to the broader ecosystems in Europe especially. The next key player, I would say, is the enterprises. I think I've been mentioning this during the previous slides, but you see here this analysis a bit more visually. As I mentioned, we are lacking a bit the global corporations with established semiconductor operations or manufacturing in Spain. So then this is a vulnerability, sorry, but this is also an opportunity. We have also mid-size, strategic mid-size enterprises like Booktics or Das Photonics, which is close here, and Semi-Dynamics, that they are working in different fields, and then they are leaders of their own markets. And of course, we have startups that are working, for example, in RISC-V architectures, on AI accelerators, and quantum processors, for example. So in those two last parts of the ecosystems, I think, I think we are relatively strong. As I said, the only part that I think we are missing as an ecosystem is to attract a large enterprise or enterprises, so then we can scale up the ecosystem. This can show as well that this is a structure that could be an early stage ecosystem, and it's about to scale up. But as I mentioned, we need to seize this moment and the funds that are coming from the public sector. I want to discuss a bit about the technology, or the core technology specialization that we have mainly in the ecosystem. I didn't put here all the technologies, but I wanted to at least highlight the power electronics part that we are quite strong in Spain with gallium nitride applications, for example, in automotive and renewable energy applications. We have radio frequency and microwave for communications. And last but not least, we also have photonics and sensors that it's a really key specialization in the Spanish ecosystem, in our opinion. These are exactly the enabling technologies, if you realize, about green transition, defense and space, communication, and autonomous mobility, which may be the drivers of the future growth. So then this is, we can see this as the Spanish ecosystem is aligned with the future critical technologies that will drive the growth in Europe and probably in the rest of the world. I want to mention as well some success stories about the ecosystem. We have several here, but I won't mention all of them, but I want to mention the first commercial foundry for 3.5 semiconductors photonics, because that should resonate here as a success. We also have the first dedicated graphene state-of-the-art foundry. And then we also have the advanced packaging fab for automotive communication, which is a project that is going to be also quite huge. And we have something strategic here in this slide, right on the bottom right part, which is maybe you didn't know or you know already, but IMEC is going to open an R&D facility outside Belgium, and is going to be in Spain. So then that's a huge push, or a huge a step forward for the Spanish ecosystem, because this could bring a strength to the industry. I think these are not just incremental developments. As I tried to mention, I think they are structural positioning moves, like the IMEC, that could bring a really a good momentum to really scale up, as I was mentioning during my presentation. Now I want to mention a bit, or I want to connect with what has been doing with the European network, or what is going on internationally and especially in Europe. We have these European competence centers under the CHIPS Act. So the competence centers were launched on March last year, on March 2025. And the idea was to create an interconnected European network for semiconductors. As you see, we have all the member states. They have one competence center. In Spain, we are one of the countries. I think only Germany has two. We are one of the countries that we have two competence centers. One is Micro Nano Spain, which is being coordinated by ISME. And the other one is PIX Spain. So I think only Germany has two competence centers. That is something that we should highlight, or we should be proud of. As I mentioned, European integration amplifies national semiconductor ecosystems. So this is an opportunity to really connect and move forward to the next step. I want to explain a bit what is Micro Nano Spain, because it was also mentioned in the SECFO slides, and we are coordinating it. So I thought that this European network explanation deserved some space in the presentation of the ecosystem. So we have Micro Nano Spain, and what we want to do is divide our action in three pillars. The first pillar is the access to technology and to infrastructure. Basically is managing and unifying the way we access, or the way companies or research institutions or academic institutions, they can access the infrastructure already available in Spain. The second pillar is the workforce development, because, as I mentioned in one of the slides, without engineers or without a specialized workforce, the ecosystem will not develop. So then this second pillar is about gathering training programs from public, private institutions to provide anyone interested with those trainings or with really focused in semiconductors ecosystem or in semiconductors industry, that they can they can get trained in those fields. The third pillar, I think, is quite important, and sometimes when we do this kind of projects, we don't think about this, but is the ecosystem development, which is basically building or driving entrepreneurship and innovation through a venture builder. It would be some kind of an acceleration hub to guide companies from the startup phase to the scale-up. So then that venture builder will bring hopefully some companies to grow and really take the lead in the next wave. As I said, this integrated infrastructure integrates talent and capital and training and infrastructure. So I think we have a good initiative here with Micro Spain to really cover and to really cover and make a good use of the European funding that we are getting. So the next one is about the future opportunities and strategic priorities. I think you already seen in my slides those future opportunities and strategic priorities, but I want to gather all of them in one slide. We have to let me start with the growth drivers, and then we go to the priorities. The huge investment from the European Commission it was a driver until now, and then new CHIPS Act is coming, and then they are discussing the new possibilities. We have the green transitions, as I mentioned before, and defense and space. They can be really a good driver for growth. So then these semiconductors are no longer just industrial products or components. They are geopolitical instruments, as we are seeing lately. So then I think Spain has an opportunity to specialize where Europe needs a strength. And then, as I said, in the strategic priorities should be the European CHIPS Act alignment between countries and public institutions. We need to extend, as I mentioned, the fab capacity, because in Spain, as I mentioned, fabrication or manufacturing is not one of our strengths. We need to develop talent because this is growing rapidly, and if we don't have the right talent at the right moment, we might miss the opportunity. And of course, I think this is about Spain growing its own ecosystem, but this is something that we cannot do without international collaboration. We need to take advantage of some of the Europe strengths and then use them as something to build together instead of competing with each other. And last slide that I wanted to show you, let me conclude with one central message. I think I mentioned it several times, but Spain's semiconductor ecosystem is innovation dense or highly innovative. We have a lot of talent that we still need to develop as well. And I think, as I mentioned in the last slide, we are structurally aligned with the Europe possible growth drivers. And then we are in a scaling phase. So the opportunity is now, as I mentioned. And here at the Photonics Integration Week, we are looking at one of the Spain's clearest strategic assets. We have that strength that we need to take advantage of. And yeah, as I mentioned, Spain has decided to be part of this new wave in semiconductor industry. So I think we need to seize this moment and take advantage of it. Now, as I mentioned at the beginning, I will be happy to take your questions, but not difficult questions, please. I just joined.
Thank you, Sergio. So, any easy or difficult questions? Okay, Sergio. Then I have to make a question. There's no coffee. So, yes, Sergio, just wanted to know, how do you see, this is not easy question, I'm sorry. No, Sergio, but okay, later on I'll pay some beers. But how do you see the coexistence of there have been a lot of electronics company for a long time in Spain. And then there is lately in the last 10 years, 15 years, the emergence of the Photonics guys, right? Yes. And there's starting to be synergies. I see it in ASMI, in the optoelectronics working group. So how do you see that? Is that a promising or maybe it's like just a convenience? How do you see it?
I think it's an opportunity. I mean, as I mentioned in one of the slides or several of the slides, collaboration is key. If we think that we can build this only on our own by being in silos, no? Photonics is this silo and then microelectronics is this silo, we are really wrong. We are really wrong because we are seeing this with photonics integrations in some microelectronics, that it could bring a scale, it could bring benefits because when you start collaborating, everything comes together, everything starts to be easier in a way. And then I think we should see this as a collaboration opportunity and not as a competitive or a hassle. So I think it's an opportunity and I don't see any issue because there is enough market for all of us. So there is no need to really start competing with each other or not collaborating because of possible issues that you might find. In my opinion, collaboration is key in this sector, everywhere in the world as well. So.
Okay, thank you, Sergio. Okay, now you want coffee, right?
Thank you. Sergio, thank you very much for your presentation. Really, really good. Very brave, being 3 months into the job and presenting. I wanted to ask, so collaboration is great, and I think Eli and Sandra, they mentioned a similar situation, challenge of industrialization and scaling. And as good as collaboration is, the barriers to entry to really scale are huge because we are competing against companies, big people in Asia, Taiwan, China. How do you think that can be overcome? Because competition is huge, and also staying competitive because of the labor and the cost of scaling and industrializing. So how do you see that can be overcome, not only in Spain, but even in Europe?
Europe, yeah, I think. That's a good question. As I said, I didn't want difficult questions, and then I got 2 difficult questions, guys. Okay. I think collaboration is one of the keys to really strengthen that. But we in Europe, or in Spain, or in Europe in general, we are not really good at the phase of scaling up. And then why is that? In my opinion, is because we are not so good at attracting venture capital, for example. If you look at the US, for example, let's put that example, they are really good at selling the pitch, selling the idea, like innovating and creating like really momentum from like private capital. So then that's one of the key aspects that we should try to correct for ourselves, for Europe in general, because this is a Europe problem in fact, because Spain maybe is not the leader in semiconductor, but except maybe the Netherlands and some parts of Germany. In Europe we are not really strong, or France, some parts, but we are not really strong in semiconductors, or at least not to the level of Asia and US, right? So then that's the two things that I mentioned, collaboration and attract venture capital. And the third one, I think, is we need to really convince the public institutions that we need real investment and real commitment from them to really push this forward, because this is really a capital-intensive market. And then, yeah, to build a factory, you need billions. So we need a lot of money for scaling up, right?
Yeah, thank you, Sergio. There's one last question over there. I saw one hand. Okay, Javier, yes.
Sorry, I hope this will be a third hardball for you. You were talking about talent development, but you didn't mention Cátedra Sperte, which has been a huge effort from the Spanish government, the companies, and the universities. So is there any effort in using that momentum? And a separate question, just to develop the internal talent that is working in the companies, we just have to copy some of the things that are happening, for example, in Midas and Ireland. And I don't see actions. I mean, we talk a lot, but we don't act too much. Sorry for that.
No, I mean, I cannot do anything else than agree with you. Basically, for the first question, it was a matter of space and time, so we didn't include the Cátedra chip, but we also didn't include some other parts of what we are doing. So then, yes, that's important, and that's part of the talent development, of course. And for the other question, yes, we like to talk a lot and then do not so much, and then when you lose the momentum, then that is more difficult to get started again. What I can say about that is, like, we need to all be aware of this weakness. In Europe, I think now we are being more or less aware with all this collaboration between competence centers and this European Chips Act. We are gathering together every now and then with some regularity, and when we are trying to copy some of the things that work in Ireland, for example. But this is not easy because it's a cross collaboration between countries, different cultures, different interests. So it's not easy, but I know that that's one of our weaknesses. It's like we like to talk a lot, and then when it comes to the action, Asian people, for example, is better than us when it comes to action.
Okay, thank you, Sergio. I think that it was a very nice presentation, nice discussion, hard questions. Thank you very much. Let's thank Sergio again. We welcome then Santiago Royo from Photonica 21. Come on.
Okay, good morning, everyone. First of all, thank you very much, Pascual, for the invitation. It's really a pleasure to come here and see the ecosystem grow. And I would say also that one of the pleasures of becoming, let's say, a senior researcher is the fact of seeing both old people, since a long time, but also students which have been around and which now are becoming the experts in the field. So thank you very much for the invitation. It's really a pleasure to come here. Pascual asked me to speak about trends in the European Union research agenda perspective for photonic integrated circuits. I mean, I did my best. I will try to do it as interesting as possible. I will first speak a little bit on my book, which is Photonica 21, Photonica 21. Especially related to the activities we have related to the PIC community now. Then I would like to make a short introduction on where's the status as far as it is known publicly in photonics in Framework Program 10, so after Europe 2028. It's coming, 2028 is in 2 years. And then finally, I would like to introduce or to present the call that's opening in June July relating to reinforcing Europe's strength in photonics, which is a very relevant call for this ecosystem, I would say. I think this was more or less what was expected. Photonic 21. Photonic 21 is the Spanish photonics technology platform. We are like a kind of community which we have a lot of members because essentially we are free. So essentially you want to join and you can join, you request to join, and then we group the people in their partners, and then we end up having a very large community which is now 300 people. So we have most of the stakeholders in the community. And we also have the capability to interact directly with the European technology platform with Photonics 21, because we are kind of the mirror, the replication here, and then that gives us the connection to the rest of European ecosystems across all Europe. It's open, and the goal is to push forward the photonic sector. We got all types. We got startups, SMEs, large companies, and since 2021 we are in Polytechnic, in Technical University of Catalonia, Universitat Politècnica de Catalunya. We are in the center, in C6, we are having the secretariat. This is the ecosystem. This is part of the ecosystem. I don't have the 300 logos, but I would like to stress that we have almost, oops, this is working as a laser? No. Can I point? No. Yeah, it should. Okay, no power, not enough power. The idea is that we have small companies, we got large companies. We organize some events, not at the scale that SECFO can organize or they can organize, but we organize periodic events which we invite you to come. We normally try to organize them in critical trade fairs, in Fruit Attraction, we did it in FeinDev, and we are going to continue doing this kind of events at a rate of 1-2 per year, both addressing the photonics community, but also both addressing the photonic integrated community, but also addressing the full photonic community, because we are more not only covering in these companies, we are covering the photonic integrated community, but also the one that is not, the systems and integration and the component units which are not related to integrated photonics. So that's great. We have universities, technology centers, whatever you can see. I mean, we got everything. We organize that way. We are organizing 8 different working groups, a central one which we call Plataformas Fotónicas, which is the equivalent of the core photonics that they have in Photonics 21, and then out of these core photonics, which in our case is number 7 and was called photonic platforms, we are having like different applications which are trying to export these core photonic applications into the different application sectors, and we got one expert, or some of the experts are here around today, that are leading each of the working groups and which are trying to push forward, activities and partnerships inside of that, on that working groups. Now, currently, we are in the process of structuring what we call the research agenda. We do periodically review the research agenda that we elaborate every 2-3 years, because it's kind of a map of what's being done in Spain currently. And in 2022, which was the last item, we got over 120 national experts participating in the elaboration of the agenda. And I would like to take advantage of the opportunity of coming to this forum to invite you to participate in the strategic research agenda that we are now working on. Because one of the things that has more strongly changed from 2022 to 2026 is for sure the photonic integrated circuit community, which has grown strongly. So adding up whatever needs to be added up in the photonics part of the photonic integrated circuit community is something that would be very valuable. We've started with the workshops. We did now the first online workshop to present each of the working groups and to start the activity in each of the working groups, presenting all the different research lines and updating the activities that we currently have. And in particular, we are having one directly related to photonic platforms, which is the one which is more related to integrated photonics in this moment. Maybe we should change the name. That's something we are considering, which is led by Javier Gamo from the Fábrica Nacional de Moneda y Timbre. and which did already the first workshop. It's not a problem. It's saved. We got it recorded. So we can, if anybody's interested, to join and add to the research agenda, which is finally something that we deliver in the ministry, please send us an email. We can send you the materials, and then you can contribute. I mean, this time we are already 100 people contributing in the different working groups, and I would encourage you to participate also in all the working groups that you may be interested in, okay? So that's the first part, okay? If you want to contribute, send us an email to that email, please. Okay, Framework Program 10 and Photonics. Well, there's going to be changes, as you possibly know. What best can be said right now is that we are following the process to Framework Program 10. Framework Program 10 is the short name because it's called the Multi-Annual Financial Framework for 2028-2034. So it's going to be a long in time, a long point time, but it's starting in 2 years. The forecasted process was this one that you are seeing here. So we mostly could say that we are or we should be around here. So we're in the middle of the process. So currently the member states should be having a kind of general agreement on what's going to happen with the framework program regarding the amount of money, regarding the distribution and the priorities. We are getting some information on that, but it's not something that is very openly transparent, but this is a critical year because by the end of the year, hopefully, it should be an agreement between the countries in order to establish which are the limits of Framework Program 10. Then will come the details. Then, as you possibly know, the deadlines get compressed at the end, so maybe it's not the end of 2026, but hopefully, for the moment, I think they are being quite in that position. This is the current proposal from the Commission, which is being discussed by the countries. This is one of that slides on billions, where it's difficult to really cope with what's being stated. But it's clear that the 4 pillars are something that's going to stand there. It's not so different that's currently there. We got like excellent science, which could be kind of the European Research Council, as far as we know. We got competitiveness and society, which is the larger one. So a focus on impact is going to be there. We know it from several years ago. So the discussions on transferring the technologies, on bringing the pilot investments to the market as something which is going to be very relevant. And we are going to be here. We are, again, going to be in the digital part. We're going to be in the digital leadership part, which is a relevant, it's a very relevant part of the thing. We've got a societal part in the bottom. Then we got an innovation part, which is more linked to the European Innovation Council, plus some other actions. And then we got kind of the infrastructures, area policies, and the spreading excellence, this kind of thing, this kind of transversal activities that they place in the end in the European research. So it's a very big budget. It's billions in the American sense, of course. It's thousands of millions. But okay, that's what's going to be at stake, right? What's currently being clear is that photonics is going to fit now into the CHIPS Act or into the GU chip. That's something which is now, I would say totally, always things can happen, but normally it would be very surprising if it did not end up in the chip GU, which is a very good news for this community. However, as Photonic 21 or as Photonics 21, we also are considering how to interact with whatever it is that it's not photonics integrated circuits. We have to care all the photonics community, in our view. People is doing lobbying. There's another significant difference beyond that thing on the all people, not only photonics, all people working in photonics, is the fact that working in a JU is significantly different from working in the Unison framework, because we are going to need to manage complementary national funding, and that can have implications, right? We'll see later when we see the call, the details of what does it mean to work with national funding, because the structure in Spain is not as simple as it should be, and I think that with ISME we should work together in order to try to simplify the procedures, because that's something that doesn't make sense. You will see, when we explain it, you will see that, okay, it takes a time to understand, but it is. What has been doing, what is being done now by Photonics 21 and with the collaboration of Photonic 21, we are doing like sharing position papers and trying to position photonics inside of the in front of the politician to have more impact. And that means that we have like a, here it looks like it appears, yes. This one, which is the most relevant, is 30 pages and it contains the most novelties. If you have to read one, unless you are in AI or in some particular type, this is analysis of the grant system in the US. This is a position paper where we are trying to position or request a lot of money for photonics and try to press the politicians. This is a recopilation of high-end user industries trying to push forward a strong framework program trained for photonics with the signatures of the people, and this is a document especially linked to AI, linked to photonics, which is a very critical thing for this sector. The main novelty that has appeared along this year in the position paper is the fact that beyond the, on request of the Commission, what was called was to speak about grand challenges. So we were asked to provide relevant grand challenges which were solved by photonics to the community, and these grand challenges should accomplish these kind of ideas, should be critical for Europe, should impact Europe, should have impact on the full innovation pipeline, and should define and deliver market-ready products by the end of the framework program 10, right? And well, there was a debate, and finally it was approved that we had like 8 grand challenges. The detail of these grand challenges, there are 3 pages for each. At the end of the document I mentioned before, the position paper, it's available in the downloads of Photonics 21 section. And you got these like 8 different grand challenges which involve AI, which involve circularity, clean food and environment, clean orbit, Europe's defense, of course, directed photonic energy. Directed photonic energy is going to be something which is going to become critical because it appears twice, because directed energy effectors and peaks for defense are another critical line. In health, what has been proposed is the personalized optical digital twin, so doing the monitoring by creating a twin of the persons. And then, well, we got scaling photonics, something focused on scaling innovation, microfactories for space and defense, and new horizons through secondary sources. I insist that the development of each of these, the detail of these lines is something which is included in the position paper I just mentioned before, right? So, this is different. Instead of working by working groups, we have been asked to work by grand challenges, and that's something which makes more interesting because of the novelty, what's going to be the annual meeting. Next June, we are going to gather together in Brussels for the partnership annual meeting on 9 to 10 June 2026. And essentially, we will have different types of events, presentations related to photonics, gathering the community together, and discussing and proposing and growing or detailing a little bit the grand challenges. So it would be a pleasure to meet most of you or several of you in Brussels. And that's the part I can tell, that's what I can tell on the Framework Program 10. And then, we move over, and then we move on to the call of this year. It's not formally published. It's something that could still have some modifications related to when they go to the member state and they do a kind of cycle. And however, this is the technical idea of the call. The idea is that, of course, it's within the CHIPS Act, and it's an innovation action. So it's not highly funded. It's not the best funding, but it's very good funding. It's an innovation action. It's 20 million for 2 projects. That's the concept that we should be keeping in mind. It's going to be launched in July, and it's going to be closed in September. So if you want to go there and you want to play this game, it's good to start working right now, because the time between July and September, of course, is going to be extremely short. There are some brokerage events already running on. The idea is, once again, to support industrial scale-up of photonic technologies and to bring that further and to bring that into products, which fits very well with all the competence centers and all the different instruments that you can find here. And the concepts are very linked to that. So you have to manage to show that you are going to be at TLL 7.8 when you finish the devices that you are going to deliver, right? So several of the following elements should be included: pre-production capabilities, design for manufacturing, supply chain reinforcement, technology roadmaps for industrial development, and contribution to EU strategic priorities, right? So essentially, I would say that the two first ones are very, very critical. The second ones are good, all are good, but I mean, the real convincing thing should be your pre-production capabilities and the design for manufacturing that you can deliver. And then what's expected, what's the scope, what should be in? Well, they are expected to address the following elements: scaling of wafer-level photonic processes, packaging and testing, heterogeneous materials and components, and design process co-optimization, plus demonstration of system-level functionality. The call is explicitly not platform-based. So it can be gallium arsenide, it can be indium phosphide, it can be lithium niobate. I don't care. They don't care. I mean, especially I don't. But I mean, the idea is to have this level of integration here. It's not a simple call from the point of view that I think that the Commission is getting wrong with ChatGPT, and they are starting to say that, okay, you have to write more pages, because the request is that the limit of the document is 200 pages. So it's a bit, I don't know. I mean, from time to time they want to get it smaller, from time to time to get it bigger, but the proposal this size is going to be huge. So you have to start working now if you want to work with that. You can have more pages, but maybe they are not evaluated. So, I mean, in 200 pages, I guess people should have enough to explain whatever they want to explain. Then, what else? Funding, of course. Eligibility, nobody has to have more than 30% of the budget, right? Scores focused on impact, with a minimum of 3. It's kind of the regular thing, but with a focus on impact and a less focus in implementation, right? And in fact, everybody should be participating in these levels, no more than 30%. Oh, what the funding rates? Well, the funding rates, these are the EU funding rates. And we got the national funding rates, which are different. The EU funding rates are going to be these levels: 35% for universities, not-for-profits, and SMEs, and 25% for profit organizations, not an SME, right? Okay. What about national funding? What about Spain? Well, Spain, in this sense, is a bit complex, because depending on the type of partner, you have to go to a different window. If you are a company or you are a private agent, and you should check what type of private agent they are referring to there, you should go to the Ministry for Digital Transformation, Transformación Digital. While if you go to the agency, if you are a university, a research entity, a non-profit, research, this type of the entities of public research, go to the Agencia Estatal de Innovación, right? Yesterday, we were finally confirmed that the call is going to be the PCI, which are Programas de Cooperación Internacional, right? So it's confirmed that this call is going to go through the Agencia Estatal de Innovación, through the way of the PCIs, right? The Programas de Cooperación Internacional. The national funding is not granted. The national funding is something you should check that you are going to be there. They have to be aware that you are applying and that you are going to have the money. There are projects from the CHIPS EU which have been evaluated positively in Europe, but then, I mean, there has been such an expansion of the Photonics integrated circuit community that you may get out and you find there, and well, there was not enough money for the lower priority despite they are approved. So it's good that you have some interaction with the ministry via ourselves, via our SEMI, via whoever, just to be aware that this could happen, right? So please inform your national contact person. It's defined in the call, and you can do it. Then, companies. Companies can manage to get up to 60% maximum minus the joint undertaking. So if there was a 35%, the maximum they can get is 60, right? So it's not easy to understand how it's written, but people can get up to these situations, right? And the Ministerio never will provide more funding than the CHIPS EU. So if the EU provides 35, it can be up to 60, so they will provide less, right? So never will be more money from the Ministerio than from the chip GPU. If you are a university or research center, it's even more complicated because you have to go through a PCI, Proyectos de Colaboración Internacional, which is a call that opens, which is competitive, but it's, I mean, you will get the project if you are in the list, right, to say it that way. But then you have a limit, and you have to take into account when you do the budgets that you have a limit on 350 maximum. That's what you request. You may not get all, right? So be aware of that. Unless you are a coordinator. If you are the project coordinator, then you can get up to 500,000, right? Up to 500,000. Remember, all the time they are speaking of up to, right? So it's not the easiest framework. I think we should try to work together in order to improve this kind of chaos that you have to apply for two projects, but the two projects are equivalent. You have to, I mean, especially for companies, it's relatively manageable. It's kind of a project with the money coming from two sides, and it works quite well. You have to do an investment. You have to do a prerequisite of, you have to, no me acuerdo, I don't know, that kind of money that you have to place in the bank, a warranty. You have to a warranty if you are a company, but that's it. And not last but not least, you have to recall that, I mean, there's not now a minimum budget, but in the past it was. So these projects should be relevant to the Spanish community. And this is something you should understand in the most broad sense, right? That is how it's written. So that's why you should contact. I mean, is this relevant if we are not? In the past, this was thought to be a 4 million budget from Spain, right? Now there's not a mandatory budget, but contact your partners, your agent, your contacts in order to evaluate if that's relevant or your project has chances to be funded or not, because otherwise you will find yourself with a 35% from the JU, and then working in a project 35% is not something which is nice and which normally you don't like. And I think that's it. I'll be happy to take any questions. Thank you very much for the time.
Thank you, Santiago, for the presentation. Questions?
Yeah, so my question is, so I think for a long time Photonics has been like a very strategic, let's say, sector for the European Union in terms of budgeting and stuff. How is Photonics going to be, like, could you dive a bit more in why Photonics will still be a very important sector in this new reality that is going to increase a lot in military budgets and in finished weapons?
I mean, the definition of photonics as a K-enabling technology, I don't think it's something which is in discussion. Possibly it will be defined already as that. What possibly will not be there anymore is a closed budget for photonics as it was in the past. So the idea is that, I mean, already in FP9, the Commission wanted photonics to be integrated into the chip GPU, and in the end, it has been something very similar because the pilot line came from the chip GPU, and now this call that is getting out is also coming from the chip GPU. So in the end, we ended up like this. So in the fact that, I mean, we resisted sometime in FP9, but FP10, it's going to be impossible to resist to the fact of the integration in the new framework, which is entering into this level, into this new chip GPU. The good point is that what's expected to happen is that Photonics 21 will be one of the key associations that will be inside of the chip GPU. The chip GPU is currently constituted by 3 associations, which are basically microelectronic semiconductors, EPOS, AENEAS, and a third one, which I don't recall now, an insight. And then we will have a 4th one, which will be Photonics 21. So Photonics 21 will have the chance to influence the research agenda, will have the chance to intervene into the calls. I mean, we will have to defend that from inside of the chip GPU against the 3 other associations, which will not be easy because they are big associations with a lot of power and a lot of, I mean, we are getting in there as the newcomers. So we will have to fight there. That's why it's relevant to have a Photonics 21 strong secretariat.
Thank you. Yeah, last question maybe.
Hi, hello, thank you very much. My question is because this morning we have seen that we see a huge growth in the semiconductor and photonics environments, and more focused in Spain, but at the same time there is a lack of big companies. So my question is how much this growth is driven by the market, in the sense that there are clients but we don't fulfill the needs, or we don't have capability, or there is not capability enough, or the idea is to create the needs of the future pure in public money?
Wow. That's a very good question. The first thing I would say is that I would not agree that we don't have large companies in photonics. Because we got Telefonica, we got Navantia, we got Indra. I mean, we got a very big defense industry, which is a very good news. We got Photonics working in this. We had a number of companies working there. Photonics is not big, not as big as Indra, of course, but we got a number of them who have this chance to be big enough to be competitive. We got Sener. So we got large companies. We do not have large semiconductor companies, but rather we have large application companies, right? I would say that's the main difference. The question that you're doing is really the critical part. I mean, the point is that these things are not something, my view, my personal view, and I'm not Photonic 19 or Photonics 21, my personal view now. My personal view is that, okay, we have a huge opportunity, which has been the recovery funds, which has been the investment that has been coming, which is the pilot line, which is Spark. There are a number of things which have been together. For some reason, we have managed to have it here. How we will translate that to the market is the critical point that we are not really knowing how to do, and that's very relevant. We expect to create the need, but that's not the best. So my view is that I would keep as much as possible international with a very, very broad view, European, because the money has come from Europe, but I would keep a very, very much European-wide view in order to make that kind of transfer. But I strongly agree, I see Carlos, no, I strongly agree that the strong point that we have missing, and that's a critical point, and we should care more, is about having this kind of bridge. I mean, we have to define how we move from a pilot line to an industrial pilot line, and that's not well defined enough, and that's a problem we have to handle. So that's the situation, in my view.
Okay, thank you, Santiago. Let's thanks Santiago again. And then last speaker, ¿prefieres este? Sí. Last speaker for the session is Carlos Lee from EPIC.
Please smile, or if you're media shy, go like this. This is for social media. There you go. That task is done.
Aquí tienes, luego me lo devuelves.
Thank you very much. So my name is Carlos Lee, which is always very strange, but con los españoles I write Dear Carlos, and then I finish Carlos, so it's always a bit awkward for me. So, the slides. So I prepared some slides, and to show that I did some work, and then the remote didn't work, and then I came back to the computer. Here we go. And then I put a map of all the fabs and the foundries, and I put with Europe, and then I put, this was actually the work where I kind of think, you know, what is it that I want to share today and get questions and get your input, and then I put this into ChatGPT, and then ChatGPT made super nice slides, are very interesting. He even makes recommendations, puts the height to emphasize, I was very, very impressed. I just did that so I want you to see that I'm not lazy. I could have a nice presentations, but in the end, I still want to go back to my 10 bullet points on a white slide. But you cannot criticize me for being lazy. You can say I have bad taste, but not lazy, okay? So I just have that one single slide. And I welcome questions and challenges and say, oh, constructive feedback. You can just shoot at me. It's very fine. I welcome any question. If I have not thought of that question, I sincerely welcome the question. If I have some thoughts on that question, I'm happy to share any ideas that I have. These are not answers, you know, it's just ideas. I've been working for 14 years at EPIC. EPIC is the Photonics industry. It's EPIC, European Photonics Industry Association. Okay? Every word matters here. It's European, and it's for the photonics industry, all photonics, and it's industrial oriented. Okay? That's 14 years, and before that I worked 16 years at SEMI, the Semiconductor Association, the Global Semiconductor Association, of which the last 6 years was on lobbying and advocating for key enabling technologies and what then became known as the IPCI, important projects of common European interest. So for 20 years, day and night, I've only been thinking about European competitiveness. Okay, how do you make an industry competitive? So please ask any questions related to that. I would be very, very happy to get your thoughts. So that's about me. I'm neutral. I'm neutral in the sense that I don't invest into companies. I'm not on a board of companies. I don't even understand photonics. I have a business degree. A bit embarrassing in front of you, but I have a business degree. So really, whether you say indium phosphide, silicon photonics, hybrid integration, same to me. So I'm neutral in technology-wise and also country-wise. I happen to live in Belgium, and I even say I don't even live in Belgium. I have a house in Belgium, so when I don't travel, I'm just in my house. It could be anywhere. So I don't have any nationalistic feelings. Although you may see my father is originally from, he's from Singapore, then too rich, too young, never had to work, Australia, UK, and como todos los ingleses que no tienen que trabajar, Costa del Sol. So I'm born in Malaga, in Playa Marta de Molinos, that's where I'm born, because my mother and the whole thing. Anyway, I'm born in Spain, father from Singapore, but I don't have nationalistic feelings. So whether it's in Spain, in the UK, in Switzerland, same to me. So in that sense, I consider myself neutral. And I would say that I'm an observer in the sense that I'm not in the companies, but I meet companies, I talk to companies, and that kind of generates an idea and a vision of what I would have. And I'm strongly committed to Europe. Everything that EPIC does, everything, even if sometimes it could be a little bit confusing, but you do this and you talk to this guy and you have been there, 100% it's always for European competitiveness. It's our slogan, we pitch it, and that's it, okay? So if you have any questions or challenges, you can go, but that's about myself. What Europe has and what we don't have. So I think we have all of this strong research infrastructure, okay? When I go to India and I say, listen, unless your government puts into research manufacturing with these machines that cost 2, 5, 10 million, unless India goes to that, you're just gonna be doing software on computers. But we have, in all of these European countries, from the CSE, MVTTs, and over here, and the DICFO, we have an incredible amount of manufacturing equipment, which not every country has. Again, India doesn't have that, to my knowledge. Well, they have a little bit, but not as much as we have. That I think we have. We also have a lot of nice talent. People that comes from these universities and from these research organizations, this we have. We have the startups, we have the ideas and all of that. What I think that we don't have is the markets. We don't have, some markets we have, some we don't have, so let's correct that. I think we have nothing, and please challenge me, I'm provocative, but that's just so that you can provoke me back afterwards. But I think we have nothing in telecom and datacom. And even if we say that we have some companies like, let's say, British Telecom or something like that, you know, like, or European companies, I don't want to go back to what you said about the Telefonica, but even if you take a company like that, ask yourselves, okay, let's take Telefonica, I'll just pick on you. But Telefonica, yes, Spanish, fantastico and everything. What do they manufacture? What do they buy? Where do they buy it from? And I will give you a concrete example of Sonia Eriksson, which is under a bullet over here about Americanization. Ask Sonia and Eriksson, they sell racks with all of these nice boxes and cables, and ask them, where is this coming from? This cable come, and in this box, in this rack, you have a chip, you have a transceiver. Where is this coming from? Where is it manufactured? Because if in the end, yes, it sounds like it's European, but if there is nothing made in Europe, then in the end, well, what do you care? And would you rather have an American company, like a Tesla that manufactures everything in Europe, or would you have a European company like a SEAT that buys everything from outside? So we have to be honest with ourselves. Okay, I think that's a very important one. We have to be sober. I mean, you can, to the politicians and to the investors and to these funding things, of course, we're great and fantastic and you have the markets, but towards ourselves, I think we owe ourselves to be honest. And so when you say some companies, what part of that is in Europe. But we do have, I think that Europe has, of course, defense is a lot. We have the Airbus for the space. We have medical. We have that. We have a lot of industrial, or what is vision machines, industrial manufacturing. We have of that. Telecom, datacom, I think we don't have. Automotive, let's see how that goes in the future, because that is affecting a lot of our industries. So I think to have an honest vision about the industries. But we do have some industries. Some countries, they don't have. I have to be careful, because I noticed yesterday this is recorded. This is the end of my career. This presentation is recorded, and this is going to appear on YouTube. Somebody like, look when he says, Vietnam has nothing, and Malaysia has, no, well, Malaysia they do have, but Vietnam, Indonesia, there isn't. There is no industry over there. Yes, they have factories and they manufacture and they do. It's just contract manufacturing, you know. It's the Americans, they put the fab over there and they just do the screw stuff. So they don't have this industry, but we do have some markets. Actually, one of the reasons that I now like more Taiwan than Singapore, I love Singapore, gateway to Asia. I can use Google, I can pay, they speak English. But you know what they don't have that Taiwan has? They don't have companies. Taiwan, Acer computers, Asus computers, Foxconn for the assembly, TSMC for the manufacturing. They've got companies. Singapore, as much as I love it, they don't have companies. Okay, but we have some companies. So we have the R&D, we have the technology, we have some markets. Okay, so we have all ingredients to have. It's like cooking. We have enough ingredients to make a really nice recipe. Now the question is, what recipe are we going to cook? So the case for industrial manufacturing, I believe in manufacturing, because that when I started, the whole lobbying at SEMI 20 years ago started because AMD, so AMD, the chip maker, was attracted to Dresden, Eastern Germany. They attract to companies and say, oh, if you come over here, we'll give you money. Oh, fantastic. AMD, the chip maker, comes to Dresden, and then AMD is doing very well. Oh, that's great. Then they want to scale up, and they say, well, you know, we need more support. And then Europe says, oh, sorry, we cannot give you more money because that's unfair towards the French and towards the English. So the French and English have nothing to do with this. I mean, they don't even do the same stuff. Yeah, but European law. And that's how we focused on creating this important project of common European interest. It has nothing to do with the Germans and the UK. This is a European level. We need a company like AMD. Of course, the lobbying takes 10 years. It took 10 years between we pitched to them, you have to help companies like AMD that you attracted over here until you have this IPCI. It takes 10 years. In the meantime, we lost it. They went to Albany, New York, where they had, I think, like $200 or $400 million, the double that we could afford. Okay, but that was the trigger point of saying we have to help companies independent of these European countries. So, yes, my experience with AMD, when you've got a factory that is going to attract machines, you need building, you need the chemicals, you need the gases, you need the wafers, people have to come and service the machines, you have to go over there, you have a whole ecosystem that creates, you need people, so the universities, they have to train the students over there, and so a factory, for me, drives a whole ecosystem, including research and academia. Okay, that is my personal belief, which for me is not necessarily on the other side. You can have a lot of universities and a lot of research that does not necessarily translate into a company, into growing a company and creating that. So I do believe that a company which is making a product which is profitable, which reinvest, is going to drive an ecosystem, but not necessarily the other side. So this is why I focus on the industrial side, because I think of it as a driver. That's the case for manufacturing. Then acquisitions. You have to go all the way till the end of the story. The reason we work at EPIC and to have a strong photonics ecosystem is not to have startups which are funded from your PhD is financed, and then your research is financed, and then you make a startup company which is also financed by the region, and then you test your product on a pilot manufacturing line which is also financed by the EU, and then you're successful, you have a product, and then comes an American and he says, you know what, I love what you do, I'll give you $50 million. And the guys go like, yes, we got it. Investor is happy, the 4 guys are happy, and it's seen as a success story. And I do not see that as a success story. So for instance, Xscale from Aachen, they were bought by Astera Labs. Should we be happy for that? If you have a large company of maybe 100, 200 employees, maybe they will stay in Europe. VLC Photonics is a nice example. I really liked the company, have a decent size, you were acquired by the Japanese, and they gave you more resources to go forward and to do more in Europe, because you had a certain size, and because the company that acquired you was very good. So I was very excited to visit VLC Photonics, a spin-off from over here. But a company that has 10 employees, that's been there for 2 years, I challenge how much of that is still left in 5 or 10 years when they are bought by a non-European entity. So it's important, in my view, to look at the acquisition side. Who is buying who? Because in the end, if we're just making pretty babies for them to pick the prettiest ones, that's not what I'm working for. The Americanization of companies. In our membership, Ericsson, Nokia, yes, European companies. My contact points all in the US. The membership bill paid by the US. I went to Helsinki and I said, hey, can I meet somebody while I'm there? I like to visit companies. No, sorry, there is nobody in Helsinki for Nokia for you to visit. No, they couldn't. I asked 5 different people. So I asked the guys from Nokia from Milan. I had also some contacts in Sweden and in the US. And I said, who can I visit in Finland? There is not. It's not there. So again, let's be honest, where's the competence center? Because in the end, I don't care necessarily so much where goes the money. You know, you have to have one nationality. You have to have one owner. And maybe the money goes over there. What I care is where's the competence? Where's the manufacturing? Where's the research? Where is all of that happening? The reason I care about the ownership is because when shit happens and the companies have to cut costs, very often, you know, their home countries where they will cut last. So that's the reason why I would care. Otherwise, in terms of ownership, I'm not too much caring. But let's be honest also on this Americanization. The public funding. So the public funding, and this is, I think, the core of my point over here. So we're seeing all of this EU Chips Act, and that's giving money, and I see a lot of people being super excited of that money coming in there and jumping on that wagon and all of that. But can we backtrack to where this whole, and let's focus on this specific on this Chips Act. Where is this coming from? This is from when the Commission said we need to have a Chips Act, which, by the way, was 2 years later after the US said it. So it's just following. So for me, just following, nobody in the whole world cares that Europe can also make chips. Seriously, nobody cares. I mean, that's not giving you, at a world level, any competitive advantages. And then you can bullshit yourself, is not a credit, can we record it? You may lie to yourself, you may, you know, yourself that, oh yes, we are independent, we can also make chips. Listen, either you're 100% independent or you're not independent. 99.99% is not being independent. If one person holds 0.1% of a material, of a chip, of the software or something, you're not independent. So that whole independency, I kind of challenge it a little bit, but just following the others, I don't see how that is, how anybody cares. So I'm concerned that it is politicians who are deciding things, you know, and that then we jump on that bandwagon. That is my very big concern. Was this CHIPS Act driven by industry? Was that driven by, at that time, ST, Infineon, NXP? Was that driven by them or not? And if I recall well at that time, they were not backing that up. You know, what they wanted to do was not what they said. Then the Commission said, they also being realistic. Oh, we're going to make 20% of the chips in the world. That is quadruple. And only one time, I'm not very diplomatically with these guys talking, but one time I asked, do you believe we're going to make this? You know, in your wildest dreams, do you think there's any chance we're going to make 4 times more chips? You know, because and the guys, but they had a good answer. They're good politicians. They said, yes, but we have to be optimistic, ambitious. We have to be ambitious. That was the way to say, like, no way, no, we're going to make it. We have to be ambitious. But it was driven by them. So that is, number one, who is driving the strategy for the industry? Is it politicians? And by the way, look at their CV. Okay, I'm going to say more. I have to stop. I said it's my last. Please thank me because it's my last. I'm fired after this video too. Or is it industry? Okay, that's point number one. That's a point I want to say. Then, how is all of these proposals coordinated? We're here in Spain, and again, and the only chance for Europe, for this industry or in the world, is to unite together, including the Swiss and including in the UK and all of that. In isolation, all of each country is too small. Their only chance, in my view, is all of Europe working together. So I'm really, really hoping that when I will not show the slide where you say, first foundry 3.5 Spain. I don't even know what that meant, but if I show that to Smart Photonics from the Netherlands, I wonder how they will react when they see that slide, which I will not do. But I really hope that all of the actors are talking together, that it is not a competition between the companies, between the countries, and that aspect goes into that collaboration part. Because in the end, my pitch is always this: we are competing, the two companies are competing, but you're not enemies. Okay, either Europe makes it together or we fail it together. Okay, but I really hope there is a good coordination, and I'm not sure that this coordination is truly happening. Maybe Inigo, who is one of the 8 people who signed this position paper for Photon Delta, maybe he will know to what extent all the key actors were involved. Because when I looked at the list of these 80 participants who were in that meeting, I didn't see ST, I believe, in that meeting. And I believe, I could be wrong, I'm not a statistics guy, but I think that ST isn't that, I think, please challenge me afterwards, I think it's the only one who's manufacturing high volume silicon photonics. With AWS, it was announced in February. So you need to have the key players involved. All the smaller players coming with ideas and stuff, listen, you need to have the key guys on board. So anyway, European coordination. Is public funding diverting from company strategy? As I said, you know, they come with some ideas. Oh, we have to do a CHIPS Act, let's give 40 billion. Oh, you get 10 billion. Oh, now we have to build a fab, let's do something. This is like the Chinese. I've got 3 Chinese companies that, oh, we went public, IPO, so they've got, Carlos, we have $100 million cash. We want to buy a European companies. Can you help us? Like, what is that for a strategy? I need to buy a company because I just got 100 million cash. But isn't that a little bit the same that is happening? Oh, we've got 10 billion. We have to do something with it. We need to have a fab. Really, is that the strategy part? You know, where I'm going always from the market strategy side. But you know what? If the governments or the investors, with all the respect, the camera, if they give money, you know, that should be fine, no? I mean, what's the problem? What is the problem of organizations taking the money and doing for something that is, even if it's not their money? And here is, I added one slide here on this opportunity cost. This I learned at school. Who does not know what is opportunity cost? Raise the hand. Ah, so you all know. Okay, 2 guys. Okay, well, I'm sorry for you too, because everybody else seems to know what is opportunity cost. But opportunity cost, and this is my concern with this public money, opportunity cost is what you are not doing because of that. So if a company or anybody here had an idea, oh, I would actually like to do this, we're good at that, and I think there is a chance for this, but then, oh, we can get money for doing this, so let's go and do that. Well, now you are not doing that. And so the opportunity cost is what you're not doing because of that. And my concern or question, or no, it's a concern, is that we are going in a direction which was driven by politics, which maybe is not the right place for Europe to be, is maybe not the place where I think Europe can be competitive. And that is my concern with public funding maybe distracting us. So voila, so I please ask questions, challenge, anything related to any of that. But I'm just concerned that the public funding driven by public authorities is distracting the industry for somewhere where really would have a really good chance for Europe. In a global landscape, in all of this integrated photonics, isn't there testing, packaging, service design? Isn't there something else which is better suited for Europe? Thank you for attention, and I welcome your questions and comments. Yes, so we have Inigo and here.
Thank you, Carlos. Great talk, great presentation.
Now it comes.
So, because of references, you mentioned this group of 8 CEOs pushing these guidelines for the European Commission on this. The reason for this, for everyone to know and understand this, is you mentioned that lobbying takes a lot of time, IPCI 10 years. So CHIPS Act, the original CHIPS Act, was driven initially by a very small and selected group of CEOs from the microelectronics industry towards the European Commission, who were actually trying to set up the guidelines, as you mentioned, right, market-driven, for the European Commission to try to allocate the funding where it was more needed. So following this principle, we try to do the same thing for photonics. We gather a set of CEOs from companies that we have been here for already 15, 20 years in photonic integration, and try to have these guidelines for the European Commission for them to try to set up this program towards the upcoming CHIPS Act 2.0. I strongly agree with you that ST should have been there. But that time, ST, well, the strategy of Silicon Photonics with ST was not very clear. They were not very much on board. Now this is changing. It still is extremely hard to get in touch with them. But I fully agree that if you don't have one of the major players, industrial players in Silicon Photonics as part of this ecosystem, it's going to be very hard to convince the European Commission on that. So what we are trying to do now is to get the backup and the feedback from all the other relevant players in Europe on this. But we have to understand also that, and this is my perspective, that European photonics industry is very much fragmented. We are all very small SMEs. And in many cases, we don't have a strong case to argue with the European Commission about what needs or doesn't need to be done, right? So that's one of the fragilities I see from our ecosystem, the size. So you in EPIC, you are more than 800 companies, right?
825 real companies who pay a real membership fee, yes.
So what's your feeling on that? I mean, how strong we are in terms of being able to lobby for the European Commission when we are such a small, diverse and a small group of companies?
So first of all, I congratulate Photon Delta for doing something, and I'm not criticizing because, it's the guy who criticized but he didn't do, so very congratulations to do that, also because they involve different countries and the whole value chain and all of that. I did, before they published that paper, I had, I think, 2 or 4 meetings where I had invited people, I don't know, maybe you were invited, I don't remember, but I had organized a few meetings where I had also Gabrielle Kreen, the lobbyists that we had done that, and it's really hard to get many people to agree to something very detailed. I will have a position paper for 500 CEOs to sign, but it's just 2 pages that say, oh, we're fantastic and we're beautiful, you have to help us. That's very easy to get a signature. But to get something very concrete like what Photon Delta did, you have to have a smaller group, and I support that. In terms of lobbying, you're absolutely correct. Even if you take ST, NXP, or Infineon, they do not have a lobbying office in Brussels. Not on them has a lobbyist person, and these are the largest semiconductor companies, so we're really out of there. Who has lobbying presence in Brussels is the Defense Association, the tobacco. Tobacco they have for cigars, for rolled tobaccos, for raw tobacco, and they have 3 or 4 associations for tobacco. The same for alcohol. They have all of that. So, but we're not there. Okay. So what can we do? I think we have to continue the lobbying with the resources. You have to take the patience and you have to play the game. And the playing in the game is you have to knock on the doors. You have to do the position. You have to go with some people and all of that. You have to try your best. It's the Parliament. It's the Council, and it's for me. It's always been. It's a sales process. Lobbying the European Commission is a sales process. You don't know who are the decision makers and who are the right guys. You knock on every single door. You go with the pitch. You align with Photonics 21, with EPIC at national level. You check Virkunen, she's from Finland. Okay, you try Photonics Finland. So you play that game of the lobbying with the position and with the arguments. What you should not do, and I don't think that we're doing that, is to contradict yourself. If Photonics 21 puts out a paper or Photon Delta puts out a paper, you should not contradict that. The worst thing that you can do is to come with another strategy, with another numbers. Okay, so sometimes EPIC backs off of doing anything, because the only thing we should do is to support that position. So independent of my opinion of that paper, we support that paper. And we support the position of Photonics 21, was to support each other. Then what you have to try is to rally the big guys, And the problem in our community, and that's absolutely the issue, if I ask all of you to write in a sheet of paper a name, who is Mr. Photonics, and not me, of course, who is Mr. Photonics in Europe? And you write the name, you will not have the same guy, and that is what is missing. In the US, it's Elon Musk and the Amazon guy and these guys. We do not have an ambassador. When it was in the semiconductor industry before, no, not the new guy, I'm going to get fired, but the old guy from ST, the small Italian guy, Pasquale Pistorio. Pasquale Pistorio, I think it's a Sicilian guy, small guy with the wool jacket and everything. He was an ambassador. He was the figurehead. Who is the figurehead for Photonics? I thought it was going to be Peter Leibinger, Trumpf, family-owned, multi-billion company, nice and flashy, but the CEO, president, well, he decided to go for the German industry. But we are lacking these key players. But we do have, you have Zeiss is a big company, ASML, they're semiconductor, they will not attach. But Zeiss, I visited it Friday, Zeiss, Jenoptik, so I think we have to rally the big players that we do have in Europe and to have a strong position with that. So I think, to answer your question, you have to play with the big guys, because in the end, these are the guys who are recognized, who make a difference. I do not put down the startups and the whole thing, but in the end, the one that have more weight and more influence, for me, are the big players. We had a question here. Oh, maybe the lady, I saw her raising the hand earlier.
Thank you, Carlos. Fantastic presentation. I just wanted to ask if you foresee like a possibility of the industry being strong enough to be the one, like powerful enough to be the one making the calls, and the government following the industry, and on the other way, like you said, because the common feeling when we talk with the companies and everything is that we do not get to compete with other parts that are stronger than us, because they have more investment in the public side. So do you see a foreseeable future where the industry is the one making the calls?
Yes, I think there is a spot for us. And if you would take like a big company, like in the sales project, you've got some big players who sell all of the machines, applied materials. It's always the big guys. You've got a smaller equipment manufacturer. But you know what? They always find a niche. There is always some spots available. But again, if you try to go into the same field as the big guys for the same amount of the whole thing, they will eat you alive. So one question which I did not ask to you was like, don't you think that the semiconductor is just going to eat us over, take us over? Because you can talk about collaboration, which is nice and fantastic. This is companies, it's shareholders, it's making money, it's competitive, okay? There is money, we want more money, and we want to have more of that. So that is, I think, is one reality while we are talking about the collaboration. So you guys, Photonics, you have some money, I want to grab that money for my company, and I'm making chips, and I will try to do that. So I'm a bit cautious on, yes, on the collaboration, but you've got the reality of the companies who say, you know what, I'm going to pay you 500,000 euros a year, and I'm going to make you VP of Innovation and Technology at one of these big companies, and your job is to lobby the commission. You've got 10 years, that will cost us 5 million, and I want you to bring back to my company 100 million. Well, that's a 20 times return. That's a good plan. Pascual, you go for that, okay? So that's how I think, that's how I would look at it if I was a big company. And Pascual, he's already going to the commission. So I think you have to find your niche, your area, but to try to compete with somebody else and try to take a piece of the cake of one of the big guys, I have doubts on that. So either you find, we work together with them, and just make it big, but let's say that we still play the role in there, or we find other angles on how to get money. But yes, 100%. There is always a way to find money at national, regional, or European level. I really believe that, yes. Got a question in the back? Oh, machine vendor. Is that because I said something about the machines?
No, so my question is quite general. But yeah, very, very nice presentation. I would say I fully agree with all you said. And my question would be like, so you made quite a good presentation of the European landscape. So it's mostly small, medium enterprises, some startups, but there are also some big players. I see that in events like that, but also like similar events that Epic does, like industrial events, the big players somehow are missing. Maybe only a few of them like passively attend and so on. And the messages like this, but are mostly addressed towards strategy, right? So you're talking, what should Europe do in a big picture in order to be competitive with US or China or whatever, right? Because these guys, they have the money, so at some point they come and they just buy us, yeah? They come with 50, 100 million euros. The company, which is founded by 4 people, they get 10 million euros each, so they are all happy, right? So my question to you is, what is the call for action for such small audiences? So here, most probably, the companies where we come from, like including VLC, for example, there are 4 co-founders, they got a few million euros, they are happy. So from a personal level, so we could see this from 2 points of view, right? From a personal level, why shouldn't the acquisition happen from the founders, right? They are happy to just make an exit and become millionaires. They solve their life forever, right? And maybe for a few generations. Maybe from the European point of view, this is not the nicest thing to do, but sacrificing this step could also mean death of such companies, right? So if you don't sell at the right moment, then most probably you're going to lose the race, right? So what's your call for action for this audience? Like, what should we do? Should we just, I mean, when I say we, it's not me, right? But
yeah, for the companies, for the startups as they grow, they are, okay, so first says the company Photonic that was sold to a Chinese investor. And don't take me wrong, I'm not an extremist political stuff. Sometimes being bought by an American or a Chinese is the best thing that could happen. I mean, listen, you're selling 80% of your machines to China. That's your biggest market. Maybe that's the biggest sense. Maybe you are in the AI field and being part of the US ecosystem is the best solution. So don't take me wrong, I'm not politically like this, so maybe it could be the best. But what I think is missing is that you have options in Europe to continue your growth. So what we're doing is on the mergers and acquisitions, I'm contacting any company in Photonics who has more than 100 employees to consider growing by acquisitions. That is in my highest priority, highest impact is that Europe needs to consolidate itself. So if any of you starts a company, first, in which field are you going to play? And realistically, what is going to be your exit scenario? Where is it going to be? Is that something where you can be competitive, or you're better to focus on something which is more European oriented? So if you go telecom, datacom, very likely it's going to be a US kind of related story. If you make big sensors for industrial applications, maybe you have a bigger market opportunity over here. You never do something for Europe. You know, you can tell this to your wife and to your kids and to your dog if you want, but business is business, okay? What is the business opportunity, the growth, and all of that? And if it happens to fit in Europe, that's good. But companies will always act on a business perspective. So where do you find that opportunity? And then based on that, where are these investors that maybe are less, not commercial oriented? A VC, I give my money to a VC so that he maximizes my return. That's what a VC does. He buys a company, he invests, and he sells it out to then maximize the return to his investors. But you have other kinds of investors as well. So my favorite investor now are companies like foundations. So foundations is what they call in the US. I finally found the word. It's called a trust. I think that the trust is how it's called in the US. But foundations you cannot buy. It's a non-for-profit. So Zeiss, Schott, Herhaus, Bosch, these are foundations. Nobody can buy those companies. You know, their purpose has others. You cannot buy that. That's my #1 favorite kind of acquirer. Then you've got the large families. Merck Electronics, Merck from Darmstadt, 3,000 employees, majority family owned. In France, HUF Group also they have. So you have these large family owned companies. Then you've got other companies that are looking into our sector. So MIBA is a Swiss company that nobody has heard of MIBA. Raise your hand if you have not heard of MIBA. So you can raise your hand. No, but you know what? They have $1 billion revenue. Mr. Mitter, I call him Mr. Miba, but it's called Mitterbauer. He created a company like 8 years ago, and it's $1 billion revenue. And the kids, they say, well, we have enough with that. They just want to reinvest into industry. Please invest into photonics. They've got 2 people from the M&A team from MIBA, which is, you know, in a high-tech kind of environment, invest into us. So from the EPIC side, what we're doing is to bring more investors from that field, not just the VCs, you know, they will find you, but from these families and private and evergreen funds. And on my recommendation to the companies here, I think you should not be concerned about a European aspect. I don't think that's going to fly neither with investors and doesn't fly in a company strategy. I think you should just focus on being successful on your technology, on your product, on your market. Just focus on your company. And the exit, listen, that's you should not care, I think, of the exit. Leave that to organizations, the commission, or whoever. We should make sure that you have the options for you to exit in Europe and to have a good success outcome in Europe. But that should not be, and then, yeah, maybe, you know, for 5 or 10%, you know, whether I make 20 million or 22, then I'll just go for a European because of the legacy. But I don't think that the company should be concerned with that. Leave that to others, like, yeah. Okay, thank you.
Thank you so much. Thank you all for attending. So now we're gonna go for a break and then we return 11:30 for next session. Thank you.
was more like a beauty queen from a movie scene. I said, oh mine, but what do you mean? I'm the one who would dance on the floor in a round. She said, I am the one who would dance on the floor in the round. She told me her name was Billie Jean as she crossed the scene. Then every hair turned red eyes, a dream of being the one who would dance on the floor in a round.
People always told me, be careful what you do. Don't go around breaking young girls' hearts. A mother always told me, be careful what you love. Be careful what you do, cause a lie becomes a truth. Billie Jean is not my love. She's just a girl who claims that I am the one. But the kid is not my son. She says I am the one. But the kid is not my son.
40 days and 40 nights, lost on her side. But who could stand when she's seen the man, her skins and plans? Cause we dance on the floor in a round. So take my strong advice. Just remember to always think twice. She told my baby we'd dance a treat, and she looked at me and showed a photo. My baby cried, his eyes were like mine. So we danced on the floor in a round.
People always told me, be careful what you do. Don't go around breaking young girls' hearts. She came and stood right by me, then the smell of sweet perfume. This happened much too soon. She called me to her room. Billie Jean is not my love. She's just a girl who claims that I am the one. But the kid is not my son. She says I am the one. But the kid is not my son.
In my eyes, in this pose, in disguises no one knows, hides the face, lies the snake. The sun in my disgrace, boiling heat, summer's tense. Neath the black, the sky looks there. Call my name through the cream, and I hear you scream again. Black hole sun, won't you come and wash away the rain? Black hole sun, won't you come? Won't you come? Stuttering, cold and dim, still the warm wind, tired friend. Times are gone for honest men, sometimes far too long for snakes. In my shoes, walking sleep,
tried to laugh about it, cover it all up with lies. I tried to laugh about it, hiding the tears in my eyes. 'Cause boys don't cry. Boys don't cry. I would tell you that I love you if I thought that you would stay. But I know that it's no use, that you've already gone away. Misjudged your limits, pushed you too far, took you for granted. I thought that you needed me more. I would do most anything to get you back by my side. But I just keep on laughing, hiding the tears in my eyes. 'Cause boys don't cry. Boys don't Take a look at my girlfriend. She's the only one I got. Not much of a girlfriend. Never seem to get a lot. Take a jumbo, cross the water, like to see America. See the girls in California, I'm hoping it's going to come true. There's not a lot I can do. Could we have keepers for breakfast? Mommy dear, they got to have them in Texas, 'cause everyone's a millionaire. I'm a winner, I'm a sinner, do you want my autograph? I'm a loser, I'm a joker, playing my jokes upon you. There's nothing better to do. Don't you look at my girlfriend, she's the only one I got. Not much of a girlfriend, never seem to get a lot. Take a jumbo, cross the water, like to see America. See the girls in California, I'm hoping it's going to come true. There's not a lot I can do. Just like an angel, your skin makes me cry. You float like a feather in a beautiful world. I wish I was special. You're so very special. But I'm a creep, and I'm a widow.
perfect body. I want a perfect soul. I want you to notice when I'm not around. You're so very special. I wish I was special, but I'm a creep. I'm a weirdo. What the hell am I doing here? I don't belong here. Whatever makes you happy, whatever you want. You're so very special. I wish I was special, but I'm a creep. I'm a weirdo. What the hell am I doing here? I don't belong here.
She sits alone, waiting for suggestions. He's so nervous, avoiding all her questions. His lips are dry, her heart is gently pounding. Don't you just know exactly what they're thinking? If you want my body and you think I'm sexy, come on, sugar, let me know. If you really need me, just reach out and touch me. Come on, honey, tell me so. Tell me so, baby. Now he's acting shy, looking for an answer. Come on, honey, let's spend the night together. Now, hold on a minute before we go much further. Give me a dime so I can phone my mother. They catch a cab to this high-rise apartment. At last he can tell her exactly what his heart meant. If you want my body and you think I'm sexy, come on, sugar, let me know. If you really need me, just reach out and touch me. Come on, honey, tell me so. Oh, no. His heart's beating like a drum, 'cause at last he's got his girl home. Come on, relax, baby, and now we are alone. Oh, they wake up down, 'cause all the birds are singing. Two total strangers, but that ain't what they're thinking. Outside it's cold, misty, and it's raining. They got each other, neither one's complaining. He says, I'm sorry, but amount of milk and coffee. Never mind, sugar, we can watch the early movie. If you want my body and you think I'm sexy, come on, sugar, let me know. If you really need me, just reach out and touch me. Come on, honey, tell me so.
Precious kisses worth and burn me. Lovers never ask you why. In my heart a fighter's burning. Choose my color, finest star. Precious people always tell me there's a step too far. Do you really want to hurt me? Do you really want to make me cry? Do you really want to hurt me? Do you really want to make me cry? Words I fear I haven't spoken, like a waste 1,000 years. Grabbing sorrow words that are token. Come inside and catch my tears. You ain't talking but believe me. If it's true, you did not know. This one loves without a reason. I'm prepared to let you go. If it's love you want from me, then take it away. Everything is not what you see. It's over again. Do you really want to hurt me? Do you really want to make me cry? Do you really want to hurt me? Do you really want to make me cry? You and me, we used to be together, every day together, always. I really feel I'm losing my best friend. I can't believe this could be the end. It looks as though you're letting go, and if it's real, well, I don't want to know. Don't speak, I know just what you're saying, so please stop explaining. Don't tell me 'cause it hurts. Don't speak, I know just what you're thinking, and I don't need your reasons. Don't tell me 'cause it hurts. Our memories, they can be inviting, but somewhere else hard to get mine, frightening, and as we die, both you and I, with my head in my hands and sit and cry. Don't speak, I know just what you're saying, so please stop explaining. Don't tell me 'cause it hurts. Don't speak, I know just what you're thinking, and I don't need your reasons. Don't tell me 'cause it hurts. It's all ending, I gotta stop pretending who we are, who we You and me, I can see you sighing. Are we? Don't speak, I know just what you're saying, so please stop explaining. Don't tell me 'cause it hurts. Don't speak, I know just what you're thinking, and I don't need your reasons. Don't tell me 'cause it hurts. Don't speak.
If you wake up and don't want to smile, if it takes just a little while, open your eyes and look at the day. You'll see things in a different way. Don't stop thinking about tomorrow. Don't stop, he'll soon be here. He'll be better than before. Yesterday's gone, yesterday's gone. Why not think about times to come? Not about the things that you've done. If life was bad to you, just think what tomorrow will do. Don't stop thinking about tomorrow. Don't stop, he'll soon be here. He'll be better than before. Yesterday's gone, yesterday's gone. All I want is to see you smile. If it takes just a little while. I know you don't believe that it's true. I've never meant any harm to you. Don't stop thinking about tomorrow. Don't stop, he'll soon be here. He'll be better than before. Yesterday's gone, yesterday's gone. don't you look back. Oh, yeah. Don't you look back. No. Don't you look. Won't you come see about me? I'll be alone dancing, you know it, baby. Tell me your troubles and doubts, giving me everything inside and out. And love's so strange, so real in the dark. Think of the tender things that we're walking on. Slow change may pull us apart. When the light gets into your heart, baby, don't you forget about me. Don't you forget about me. Will you stand above me? Look my way, never love me. Rain keeps falling down, down, down. Could you recognize me? Call my name, I will come by. Rain keeps falling down, 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 down. Hey, 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 hey. Ooh, don't you forget about me. Don't you forget about me. As you walk on by, would you call my name? As you walk on by, would you call my name? When you walk away, every move you make, every bound you break, every step you take, I'll be watching you. Every single day, every word you say, every game you play, every night you stay, I'll be watching you. Oh, can you see you belong to me? How my poor heart aches with every step you take, every move you make, every bow you break, every smile you fake, every claim you stake, I've been watching you. Since you've gone, I've been lost.
Hello everyone, welcome back. I hope you had enough coffee and sweets and your brain is again wake up and ready for the next session. And this session is called the Company Pills, where we give our exhibitors some space in order to show and to tell us what they do and what they can offer and service for us. And the first presentation comes from EMEA. It's partially shared between EMEA, APS Technologies, and Backward Automation. And since we are a little bit late on time, just please go on stage. Thank you very much.
So, hola, hi, I'm Rafa from ME Electro Solutions. So today we just give a brief overview about our company and the solutions we bring to Spain and Portugal. Later I will invite my colleague Walter Meiring from APNS to tell a little bit about APNS solutions for wet process equipments. And later Odin or Mohamed Bila will speak about Vanguard automation on the photonic wire bond and phase attached microlenses. So let me go up a bit. It's easier right here. So basically we work as a distributor for different equipments on the semiconductor, photonics, cleaning and surface treatment, ESD and clean room, electronics and battery solutions. Lately, let's say during the last 3 or 4 years, let's say our business is maybe 60 or 70% related to photonics and microelectronics. So after the wafer is made, we do all the related process. Okay, so from wafer we do dicing, grinding, polishing. Then we go for wafer level packaging or balling as well, redistribution layer, additive nanomanufacturing with holding, photonics, wire bond, active alignment, die attach with all the process related, CO2, snow cleaning. Then we go for plasma, different types of systems, wire bonding, wire and die testing, laser marking, the flashing, cropping. So all the processes that are related to the backend, we are covering. And what's interesting is that we are focused not only on manufacturing, but on R&D. So we work together with the customer, we understand their requirements, and basically we try to guide them or stay with them during the complete roadmap for manufacturing. Okay? I will not take much of time. I will let the guys speak about their technologies. So just a little bit about the brands we are working with. So most of them are very well known on the market. Recently we have integrated APNS and Onto Innovation on our portfolio that the guys, that Walter will speak a little bit about. Later on, a little bit about our references. I mean, here's just a couple of customers, but we work with almost all the universities we have in Spain and Portugal as well. That said, let's say one thing that's very important for us as well is the service and prototyping. So we collaborate with our different suppliers for prototyping. Let me just come back here. So normally all of our suppliers, they have their demo room with different tools. Let's say, for example, if I take one of the companies, they have 10 different machines. So we prefer that we take the product and go with our customers to our manufacturers and sit down together with them, develop the process together, and then deliver, let's say, the machine with the application ready. That's it. Something that we also work with, we have our technicians here in Spain and Portugal. So we do the installation, commissioning, calibration, whatever is needed for running your production or your R&D. Also, something that's important is we collaborate with Albion Group for clean room and also for the consumables directly for, well, clean room environment or ESD or electronics manufacturing. So now I ask Walter if you can come here to speak about APNS.
Thank you, Rafa. Thank you to organizers of Photonic Integration Week for this opportunity. I would like to represent APNS International. We are a family-run company in the second generation with over 20 years of experience and over 250 employees worldwide and with over 800 installed tools worldwide. Our most biggest benefits in comparison to other suppliers is that we have our own in-house electrical engineering, mechanical and chemical engineering. We have our own software company, our own process engineering, and our own automation. Of course, we have also noticed that the photonics will be a kind of a hype also worldwide. That's why in the last 2-3 years we are involved in several projects. Most of them are, of course, in Europe. And recently also in Spain. I am observing this market for the last 2 to 3 years, and it is exploding from my perspective. But we are also working with our companies, with our partners in Asia and in the US. What business units or what areas APNS covers? In the first row, we cover single wafer equipment for different processes like etching, cleaning, post-CMP, lift-off. We offer also equipment for the batch processes for different wafer sizes, for different wafer thicknesses, for different wafer numbers in the batch, and various grade of automation, so highly customized equipment. We also offer production support equipment for drying solutions, and also for the cleaning and drying of FOUPs, SMIFs, and different parts, and also tubes. And last but not least, our very strong after-sales unit supports you with the trainings. It supports with the spare parts, with maintenance, and by all issues regarding our equipment. What areas do we cover within a semiconductor industry? It is, of course, cleaning, etching, PR stripping, lift-off, and ELS plating. So in general, mainly the tasks are in front end of line, but also for the back end of line, we have different solutions. What are the major benefits by APNS? That first you have our demo lab. We have also process simulation tool. We offer parts cleaning. We also offer, in some cases, leasing options and pay-per-use. With our equipment, you can grow with your production. You can easily add or remove modules or process chambers to your equipment. We also can supply you by refurbishments, and we are ready to develop with you the next generation equipment. Thank you for your attention.
So thank you, Rafa, for the introduction. I will be quick. We are Finger Automation, and we are offering additional manufacturing through photonic wire bonds and facet-attached micro lenses. The pictures in the middle represent both structures, especially the blue colored ones. The long ones are photonic wire bonds, and the other one are actually facet-attached micro lenses, 3D printed with 2-photon polymerization, and we position them to be actually in between of these two existing technology. On the other side, we have active alignment. You may call it butt coupling, for example. Simplified setup, but large size due to the coupling element, for example. And then on the other side, we have heterogeneous integration with increased complexity. So how do we fabricate them? We use the first machine called Sonata 1000. That's actually your machine to print those structures. And then the Reprise 1000 actually helps to cleanse and also to encapsulate the photonic wire bonds. In the case of the lens, it's not necessary. And then we also have incorporated our software inside the machines so that we are able to actually detect the waveguides in less than 100 nanometer accuracy. And then additionally, we also created or developed our own materials, namely the polymers. And then also we offer professional services. The key differentiator would be the following slide, where we actually tested our photonic wire bonds in different tests. The first one is actually damp heat, a very typical test in Telcordia setting, and then also temperature cycle from minus 40 degrees to 85 degrees Celsius, for example. A single data point in the first two groups are actually representing an average of 40 connections. On the other side, we also tested our lenses at high power output, up to 200 milliwatt and up to 75 degrees Celsius. And as you can see in the pictures at the bottom, they do not change the coupling loss after 5,000 hours. Further tests are made by our end users. As you can see, we listed them on the left bottom side. We would be happy to receive questions in our booth. Thank you.
Thank you very much, Mea, who shared the time for the presentation. The answers, as they mentioned, we can go to visit the booth to make the questions, the corresponding questions you might have. And the following presentation comes from Microworld.
Hello everyone. I'm glad to have the chance to present myself in front of you today. I will briefly present Microworld. My name is Igor. I'm a technical sales engineer specialized in microelectronic, and I'm working at Microworld, a company based in France, in Grenoble, based now as the Semiconductor Valley of France. I will briefly present you how Microworld is supporting the client from the device testing to material characterization and back-end processing. So who are we? Microworld, we are not only sales equipment suppliers, we position ourselves as real technical partners since we are supporting, we have been supporting our client from the research, university, and industrial fab. For more than 30 years today, we have been supporting by providing innovating solution with tailor solution, high expertise, and a strong responsiveness. Our DNA is based on 7 major pillars with technicality, reactivity, trust, quality, loyalty, and ethics. Our big vision is simple: it's societal and environmental well-being through technology, and to serve that, our mission is to provide for each step of semiconductor industry a specific solution. So where are we? As I said earlier, we are based in France, more specifically in Grenoble, and it's a city known for the semiconductor, and the city metropole won lately the prize of the first innovative capital in Europe. So we are actually where the things are happening, and it helped us to stay closely connected to all the high-tech research centers, the industrial fab, and the innovative startups. We have a lot of clients all over France, like ST Microelectronic, Airbus, and Thales. And worldwide, in Spain, we work a lot with the university, with La Politécnica de Madrid, and other big companies and labs. So, to have a more in-depth view on what we actually do in Microworld, I will present it to them now. One of our biggest strengths is our ability to cover the full process of semiconductor process from the front end to the back end. From the front end, we are more specialized in electrical measurement, probing, and mechanical analysis. And at the back end, we are doing all about dicing, bonding, and we are also doing all the accessories for each steps. So if we talk about the electrical measurement and probing, for several years, Microworld has specialized in probe testing and electrical layer characterization with flagship products such as probe station setups and 4-probe measurement system. So we are a niche player in a niche market inside the niche industry. We are also providing in-house software that help the client to perform remote control of the system, to do mapping of the sample, and a lot of different useful tools. Historically, Microworld began with dicing products, particularly cutting blades, and today we are still in the game, and we are providing various machines for the back-end processing, like tape mounter, tape expander, UV carrying system, die and wire bonders, and pick-and-place machine. So now let's have a look on a very interesting system. It's our compact probe testing system. That is actually our most customizable solution. Basically, it's ideal for die-level electrical validation before packaging. We can perform electrical tests on die, to perform current and voltage measurement, failure analysis, and you can basically do anything you want with the system. For example, if you want to install more controllers, we can do it. If you want to add piezoelectric microprocessor, it's also possible. We can also install fiber optic on the system. The strength of this system is to be able to work under a specific environment, such as we have variable temperature. It can go down to 77 Kelvin to 1,500 degrees Celsius. We can also work in vacuum and insert the gas that you want. It can be liquid nitrogen or argon. Another system is our electro-optical Hall characterization platform that enable the users to correlate some parameters like mobility, the conductivity, resistivity with physics features like temperature again, with a variable magnet and variable magnet field from 0.5 Tesla to 1 Tesla. You can also have a variable illumination that helps you measure the same parameters under a specific illumination with different wavelengths. This is particularly powerful for photonic and optoelectronic materials, where electrical behavior depends on light excitation. With this system, we don't just measure materials, we help understand how they behave under real operating conditions. So I have these two equipment on my booth, so if you have questions, I can directly answer and present them to you on my booth. To complete the electrical characterization, we also provide mechanical analysis with equipment such as tribonometer, ellipsometer, and profilometer. They can be either optic or manual. They help to measure the thickness on the sample, and they give you information of physics parameters of the sample. We also provide equipment to do the burning tests and the thermal testing with the test socket and our thermal tester. So to finish the presentation, we also provide consumables and accessories for each step of the process and for each machine, like the tape, the positioners, the tips, the anti-vibration table, and also the microscopes. So what's MicroWorld in brief? It's a technical solution for each step of semiconductor component. It's the technical expertise who accompany you from the quotation to after sale. We also perform the installation ourselves, and we have our own machine in our labs in Grenoble that help us to do the measurement and test before to send the material to the customer. And we have today 35 years old to be accurate, and we have more than 1,000 customers in the world, the entire world. So thank you. If you want to connect with me, you can scan my QR code if you want. Muchas gracias.
Thank you very much, Aiko. Okay, we will continue. Are there in the audience any one of you who work with metrology or in the lab? I see a lot of students, so I can imagine that many of you use this kind of equipment. So you can visit Igor in his booth and check how can you make easier your measurements. Next presentation comes from Expo and Fibercom.
Okay, thank you to the organization committee, and yes, thank you for hosting us here in sunny Valencia. So my name is Hugo. I'm here with Jorge Lopez and from Fabercom. Fabercom is our partner in Spain, proudly born in Zaragoza 35 years ago. Group Fabercom has also within the group Aragon Photonics, might be familiar to you, the name. And as Expo, myself, I've been about 20 years at Expo, and And Expo, I can say briefly, is a Canadian company. We were born 40 years ago in Quebec City. And as many of those companies and many of companies here in Spain, I was born from the University of Laval, a spin-off in Quebec. And here we go. So most of you might know already Expo through some of the handhelds and testing instruments, most of them for the field, the very beginning, and that's how Expo was born. And producing some power meters, light sources, and attenuators. And then Expo started to get traction in the industry and have an amazing growth through the years. And later on, we went into the lab market, the R&D market. And this is some of our devices. These are bench tops. Some of those are battery powered, like the LTK one. That one is quite flexible because you can have different configurations. From photodetectors, you can have also lasers, DFBs, and broadband light sources and tunable light sources. We can have variable attenuators in that form factor. OSAs, OTDRs, but we also have tunable filters, excuse me, manual and automatic tunable filters. Those two that you see in the bottom, I'm going to talk about that in a minute. But to complement the bench tops, we also have rack mount solutions, quite flexible, because you can have optical devices, the ones that I mentioned, from photodetectors, light sources, attenuators. You can also have even OTDRs, and it's quite flexible because there you can have traffic generators up to 800 gig, bird testers, and that's the LTV8 platform on top, the one that you see. And that one is about 3U. We have another one that is 4U that can have up to 12 slots. We do switches up to 192 by 192 as well. And then this is, I think, for the photonics industry, and this is something that Expo is extremely passionate because our DNA is about innovation. It's about bringing solutions. And Expo, one of the growth strategies was acquiring a company 7-8 years ago in France. This comes from our Genista acquisition, where we have tunable lasers that cover from the O band all the way to the U band, those models on top. And those can be combined with our CTP10, which allows characterization of passive components, and is unparalleled resolution, and 20 femtometers. You can do the sweep, fast sweep up to 200 nanometers per second. Thank you, sorry. And then with the CTP10, we do insertion loss, return loss. Alternatively, you can do insertion loss PDL, and then that one you can have up to be fair, I cannot remember even if it's hundreds of detectors, because you can daisy chain, so you can have that CTP10 and daisy chain to others. So this is one of the solutions that today the photonics industry worldwide is adopting to characterize, for example, from PIC, and then the tunable lasers, not the tunable lasers, the tunable filters that I mentioned earlier, the manual and the automatic. Those come also from that acquisition. We have BERT analyzers, electrical BERT analyzers, BA 1600. That one was launched last year. And we invite you all to come to OFC, because we are going to launch something interesting there as well. and but we do from 1 gig all the way to 800 gig on that form factor on the LTB, both the electrical bit error rate and with FEC analysis on the BA 1600. And last but not least, and I find this quite relevant for today, along with all the instruments that we have in our portfolio. And 3-4 years ago, Expo acquired another company, at this time in Quebec City, and this company is called EVA. So we went into a market where, yes, there are some incumbents there that can be quite strong. But our scientists in this company, EVA, they designed and manufacture these probe stations. We have from single die probe station, multi-die, and the wafer for 300 millimeters wafer characterization. And one of the value add of these solutions that we have for peak characterization is that is extremely flexible and is modular, so you can add and grow it as you need. You can have, for example, 2 optical heads. You can have 2 electrical heads, and then the other thing that is extremely unique is the pilot software that helps from taking the GDS and from the die or the wafer, and then be able to do full automation of the testing. So, and we can obviously we have an open system, and where you can add Python scripts, but we have our own by default spiral and other scripts to be able to do the optimization of the characterization of peak. And that one is going to be showcased also at OFC and in LA. And as a whole, yes, we are extremely proud for the solutions that we have. Again, we were born there in Quebec. We have R&D in Quebec, Montreal, here in Finland for home security, and then in France, in Lannion, for the tunable lasers and the CTP10. So yes, if you need any instrument, and we strongly encourage you to consider talking to us, Buy Canadian, and yes. So if you have any questions, I'm here with Jorge, and we can discuss downstairs. Okay. So thank you very much. Gracias. Thank you, Gloria. Gracias.
Okay, next presentation comes from Thomas from Mycos, Iberia. Thank you very much, Thomas.
Thank you very much, Gloria, for this introduction, and thank you very much to all the organization to organize this interesting conference. I was already in the first edition, and now it's the 9th, and much more people are present. But I think the spirit is the same as in the beginning, to go forward with this photonic. I'm Thomas Etzkon from Mycos Iberia. Mycos Iberia forms part of the PI group, Physikinstrumente, and I will present today one new product from us. It is a fiber alignment system based on piezo's, and it is a 6-axis positioning cube. And it closes the gap in our product portfolio for application which require only a reduced travel range in the alignment. But first of all, I will I have one slide about PI Group. PI produces high precision positioning systems and units. It was founded in 1970, and today we have about 1,700 employees all over the world. We have 9 production sites all over the world. The headquarters is in Karlsruhe in Germany, but we are working globally. Here we see the main competence fields of PI. We have the performance automation. In this field, we offer linear stages, rotational stages, hexapod, all with electromotors. We are talking here about resolutions of 100 nanometers and repeatabilities in the micrometer range, and travel ranges up to 1 meter approximately. Then we have the nano positioning unit. Here we offer positioning units based on piezoelectric actuators and the flexure design. We have stages, we have tip-tilt mirror. This is, in the last time, very important for free optical communication. And we have objective scanner. And finally, we have the piezo technology. There it started with the production of actuators, which we use for this part, but today there are a lot of applications beside this positioning application for these components. Already 10 years ago, approximately, PI introduced this fiber alignment positioning systems. So it's not a complete system, it's not an probe state, so it's just the alignment task for testing or packaging. And it's a very useful system, as it has 6 degrees of freedom and a very high resolution. It is based on the combination of an hexapod and a nano positioner. These are pretty well, they're working very good. I think it's the quickest system in the market. But when you don't need these big travel ranges of the hexapod, it's oversized for some application, and this is the reason why PI developed this new nanogroup, which has now 6 degrees of freedom, so 3 linear and rotational. It is based on parallel kinematic design, so all the actuators are actuating against the same platform. This means that you have the same dynamic in all the axes. This is important for a quick alignment. Another important point is that you, as it is the case in all parallel kinematic setups as the hexapod, that you can define the pivot point, the point through which you make the alignment tasks. When we look at the specifications, we have a travel range, a maximum travel range in the linear axis of 0.5 millimeter, which is a lot for a piezoelectric device, and for the rotational axis, plus minus 26 milliradians, which corresponds to 3 degrees total. The minimum step size is about 50 nanometers and 5 microradians. With this first fiber alignment system PI offered, we had alignment routines which are very important, and also for this system we can offer this so-called fast multi-channel alignment routines. We have routines for first light, search, as we see here. It is an area scan. But when you have found the first light, then we have also the gradient scans for optimization of the coupling. And very important, you can do this optimization in several axes in parallel. There's one point we must have into account, and this is that the travel ranges in a parallel kinematic setup depends on the position of the other axis. So one axis has only the maximum travel range when all the other axes are at 0. PI offers a simulator which can be downloaded from the web page, where you can simulate the possible positions of this nanocube. I have made here, so here I have changed the set nearly to the maximum value, and here we see what means this for the rotational axis. Two rotational axes are not affected, but the travel range of one rotational axis is reduced. This for all parallel kinematic setups has to be so you have to have in account. And yeah, the best is to make a simulation. I have the simulator here. If someone is interested, I can show it, or I can also answer any question you might have. Thank you very much for your attention.
Thank you, Thomas. Any questions for Thomas? There are a couple of minutes. Not? Okay. Then they can visit in your booth, and now we can follow on with the following presentation, with the following speaker, who is from Nanoscribe. Okay.
Oh,
Thank you very much.
Yes, oh, wonderful. And it's over there. Oh, good. Okay, yeah. Thank you for giving the introduction. And my name is Alexander Legand from the company Nanoscribe, and we do a lot of different things. And here it's about, I would like to highlight what we are doing then in terms of printing interconnections, or doing optical interconnections then for photonic integrated circuits. And this direction or that direction? Yeah, this direction. And so a few words to the company. So company Nanoscribe, we are now quite since a few years then in the market. We are a German spin-off from the Karlsruhe Institute of Technology, still located there. A few thousand users in the meantime over the years with a lot of different publications. Main market is academia. Still, we grew quite a lot over the year, and we are just perhaps even the only profitable company based on two-photon polarization systems. We have done more than 400 systems sold in the meanwhile worldwide. So, for example, 9 of them for Spain. Last year was again a very successful year then with around nearly 25 million revenue, and around 20%, 25% of it then coming from industry. And oh yeah, sorry, I just forgot to mention that. And so, for example, and also since more than a year, we are part of the Lab 14 group. So, for example, one of our sister companies, Heidelberg Instruments, will also give a presentation then a few minutes later. So you see here just an overview of different applications what our customers are doing. So you see here some are printing in life sciences then, that you print for example, then fine details into microfluidic channels. Or what you also can do is then you see over here, so you can print models then here for vascular systems. Some go more for medical engineering, so you can print microneedle arrays either directly or as a master for replication. People are interested in MEMS, movable objects, for example. We came from the area here, photonics, micro-optics, and of course here it's about then this area here then, just photonic integration then, photonic packaging. So just to show a few things, then, for example, we have had a project done here, the OCT project, then that we were included or part of this type of this project in here, that we got this type of prototype. And if you just look a bit closer into it, then it was more around than this area, or to look even more closer than this part, and you see then that you have some waveguides, and now the ideas then, or the questions then, how to communicate from one part to the other. And then what you saw over here is then that we do edge coupling, that we print here these elements at the end of these waveguides then to guide just the signal to another place where it should go to. And all this, of course, of a lot of different materials, silicon nitride, silicon oxide, silicon, and so on and so on. And for any component you can think of. And of course, so before I showed we have a lot of different applications, but for this application we dedicate in one single system the quantum X-Align. And so we support that by different patent portfolio, but also we provide then the whole just environment, the whole process, the whole workflow. So typically for photonic integration, it's about then that you have different optical elements and with different mode field, so with different mode field diameters and different mode field shapes. And what you want to do is then that you want to overlap, communicate between the different types of elements, like put optical elements, lenses on top of optical fibers, do edge coupling, print something on a chip surface, what you see over here. And so if you just look on the different mode field diameters, you see then here typical sizes in the micron, sub-micron range, different shapes between these different elements. And now it's about how do you print something to couple from one area then to the other area to another element. And so this is the solution here, as you see. So I said before, quantum X-Align is the hardware, the instrument, and this is the software. So it's an easy-to-use software, what you see over here, which defines in what you want to print. In this case, so these lenses here were printed on top of the optical fiber, automatically aligned it, and tilt measurement done from the surface, and automated the SDL mesh of each single fiber was then corrected to get a parallel output then at the end of each fiber. And also we made some testing, so for example, like some thermal shock testing, and compare then, so then what was the loss before. You see then losses were achieved then between, so around, in this case, around 0.5 dB. And so this is how it typically looks like. So you, for example, for testing, that you just couple in, couple out, measure what is the signal, and also then let's run some circles, overheating, temperature shocks, and you see that at the end you still get the same signal, the same low loss as compared to before. And you have a lot of design freedom, easy to use equipment. So for example, if you are interested in something like this, what I say is then you always should do some testing, also just put your hands yourself onto the system just to see what you will get then at the end. And so we have full operator freedom then on the designs, on the software. And so we also support that with different materials. So we have then the material then with the highest effective index for any two-photon polarization material on site, or we have also then on the market, or we also have then so the easiest to use lower fluorescence material than the IPX clear then, so on the market for two-photon polarization. Another example is then that you can do edge coupling, that you have here, for example, then a waveguide. And at the end of the waveguide, you print here, aligned then just optical edge couplers. We are the only one compensated here, for example, the shadow effect, that if you focus from the top of the laser, of course, you will lose some signal then here at the edge, and we compensate it by directly measuring it from a confocal module inside this step, and automatically then adapt the laser power to get always sufficient then polymerization, no matter where you are exposing here. Again, so you see here typical numbers then in the minutes range then of print speed, and again some testing then that the output became slow, was stable before heating and after heating, that you get the same low losses. And again, you see here some examples then in the dB and below 1 dB range. Another example, so here work from again then with so here Pixel Photonics spin-off from University of Münster group, that you just here have internal reflection then to guide here the signal out, to do optical coupling then out of the plane. And so all this is provided in here why all this environment here from the company described that we provide from us then the final solution, not only in equipment, that you can change, if you like, then here software designs at the beginning look automated for some types of markers. And we also do then, of course, provide the hardware, also the training on the job that as soon as possible then that you get to the market and you get your results. And all this then, of course, with also then the supported different materials. More examples then just to wrap up more or less. You see then here printed lens and optical fibers. You see here how you can just prepare them such a print shop with up to around then 4 fiber arrays with each 8 fibers inside that you can also here print, for example, and prepare a print shop with different chips then on these type of elements then for these edge coupling or for the optical coupling. And here you see another example then it was printed. And so on one side, just to so of course then, so one address, one market that you want to address, one application is then rapid prototyping. So you can here print single elements, but you can also do just print a master, do replication via microinjection, for example, or NIL, non-imprint lithography. And also, what we also have then, just some of our customers also do direct printing, direct manufacturing then of a small series. And this brings me to the end, so to our motto, think big and print nano. And if you have questions, you are welcome then to visit our booth. Thank you very much.
Thank you very much, Alexander. Any questions for Alexander? About technology? Yes?
Well, I was going to ask, but I think I already see. Do you work with the industry to provide packaging solution as a commercial, up to the commercial level, but is Fix one of your partners?
Fix is one of our customers, so it was before a partner, then they bought an equipment. And if you would like to have printed lenses automated then on optical fibers, you can go to them. They have a job shop on their website and directly order there. Another question? Yeah.
Thanks a lot, great talk. The question is like, what is the maximum temperature of those microstructures they can handle, or if there is any, strategy to increase maximum temperature?
Of course, then, so this is a standard test. So that's the reason why we show these numbers with 85 degrees Celsius. So they are, of course, more than that. We also had some testing according to soldering. And what you also see is then that people very often use the polymer then as a template, then later on do, for example, coating. And then, or for example, also on our website, we also have provided and tests then for how to the material evaporate according to temperature. And then if you just look at you see then the loss of material according to the temperature, then you see that the turning point is typically for most materials around to 300 degrees Celsius. Okay. Thank you.
Thank you. Thank you very much. So we are now getting to the middle part of the session, and I would like to ask you 3 fast questions. So raise your hand if you have learned something new or something that you didn't know that existed. Okay, good. Raise your hand if you learned something that you knew the company, but you didn't know that the company had this kind of services or products. Good. And raise your hand if you would like to learn something else about their services or capabilities or so. Okay, I think this session is working. Good, it's good to know. Okay, next speaker is from Fintech, sorry. Sylvain?
Hello everyone. Thanks Gloria, Pascual for the organization, UPV for hosting 3 times for me in
in here in Valencia. Always a pleasure, and more people coming in. I am Sylvain Dulphy from Fintech. We are a pure player about flip chip bonding equipment. If I just make a short sentence to this morning session, thanks Carlos Lee to pointing out that we have some solution within Europe, some equipments, that we have our market. I should tell that it was a niche market for the photonics. It's now really booming, and we have a lot of equipment going everywhere. And yes, there's a risk for some of it going high volume, being taken by wafer fabs. Maybe it's not a risk, it's just for us to set where we can sell the machines. So for sure, I agree what was said to what was said this morning. So what we do is we help customers to do what they do best, which is a design product and supply product. We are true believers about hardware. So with our platforms, our die bonding platforms, we propose to do advanced bonding and some also classical bonding so that you can do some prototypes, some products, and of course some production. This is part of these things that you can do with our machine that we help you allow to do. So heterogeneous, yes, photonics. Any kind of interconnect, it should be also semiconductor, not only photonics. And some 3D to 1.5D system level assemblies. We are more and more focusing on transceivers that used to be system in package, and now they are all stuck together on top of each other. That's what you can do with our machine, and that's what we support for you to do. What we propose in the machine, accuracy. So you will see some of the machine afterwards. We go down to 0.2 micron placement accuracy. This is also very important. Going lower, yes, why not? What for? So this is also part of the ecosystem and where we have a win-win situation, which is what do you need? And we will develop the correct module. And we need to develop this all together. So you developing the new innovations and us developing the machine able to tackle those things. It's really not one after the other. We have to run together. Process control, it's more and more production. So production means that we are going out of the lab for most of the machine, even the tabletop machines. Going out of the lab means some measurement possibilities in the machine, some SPC calculation, some connections with your networks, so that all the data can be flowed in the quality system. Modularity, flexibility is what we are well known for. You buy a machine with some process modules, so heating modules, glue dispense modules, ultrasonic modules, laser assisted, you name it, usually we have it. I'm always being cautious because you have always a lot of imagination. The thing is that we developed the machine in order to be upgradable. So you need now a soldering for a laser diode. It is classical for us, okay? But tomorrow you may need a system in package or a transceiver with some glue and soldering. Well, you just buy the glue dispense module. It's half a day installation, half a day training, and then you run. Then you have it. This is what we propose, is to speed up, to help you speed up, thanks to the machine, the way you work and the way to develop product, test them. I would tell you that for HPC and AI and quantum, people are in a rush now, really in a rush. So when they decide to purchase a machine, it's already too late because the machine is between 3 months to 6 months delivery, and we are one of the best in this field because we have a standard platforms. When we deliver the machine, they are to the week to show a demonstrator with their financial people, with their key stakeholder, with their customers. It's really going fast. So more and more we are proposing some support, process development support. So we don't do the process, your process. We make it happen in the machine. So how to handle the chip, how to dispense the glue, how to do the force, the coplanarity, how to have the right tools. That's what we do. And we do that more and more in advance. As soon as we have the PO for the machine, we work on that. Sometimes even before. So, because yes, time is running. And when you look at AI, time to market is something. There's a lot of startups, there's a lot of research, not all of them will succeed. Scalability, that's where we are going now also. So I will show you the equipment. We have now new equipment going for more volumes, more standard production levels. Part of the equipment, well, we have a booth like everyone, so just come back down in the booth to discuss the details. Our traditional tabletop systems, automatic femto machines, and the new platform that we presented in Productronica last November. Tabletop system, you would be amazed what you can do with such a thing that you put on this table. You can do a placement of half a micron accuracy with this kind of machines. So for R&D up to a few thousand a year production, you can work with those machines. Even in Europe, even considering the human rate labor cost, you can do that. Some of our customers do production with tabletops, as long as it is a few thousand a year, not more. If you go to a few 100,000, then you go to the femto machines. The interest part is that we use the same software all along. So what you develop on the tabletop with university or with a partner, you can transfer to the automatic machine. Whether it is you buying it, whether it is you using some EMS partners. And there are a few in Europe that have our machines also. Not only in Europe, but also in Europe. And the new machine is more or less higher throughput, but also fully software compatible to production levels and also to any kind of inline machine. So robot feeding, any kind of elevator for wafers, compatible with also, of course, 12-inch wafers, but also some of the trays that could be 60 centimeters by 40 centimeters to do volume production. Just come to the booth, to the details. So what we illustrate is that from the feasibility, from the first idea of the device that you are designing up to the full production, we have different solutions, and you can use maybe the same machine, at least to start with. We have good success story in Spain, where some of the process of one of our customers in Tres Cantos did some development on one of our machines at a third-party partner. Then they bought our Femto2 machine for their pilot lines, and that's where we stand now with them. So it's really ongoing process, and yes, we have the knowledge of what is needed in a full production process, and this is different from a pure R&D things. Ideas of advanced process that we tackle. So indium bump interconnect for infrared, for quantum, indium quantum, always, as long as it is going in the cryostat. It's not always bumps, it's sometimes big pads. Indium has its own issues, let's say, for the processing. We tackle them no problem. Thermocompression bonding is one of them. Adhesive bonding is classical, never easy. No? It's never easy if you don't know it. It is a process development. Don't think that you can put a dot of glue, put something on it, and that it works. Coplanarity is always an issue. Bond line thickness is an issue. Glue retractation after curing might be also an issue depending on your design. So let's discuss about those things to make sure that the machine will cope with all those constraints and your specification. Ultrasonic bonding. This is something we have since years. Ultrasonic is not new in the area. All the wire bonding is ultrasonic bonding, but you can do that on chips also. Let's focus on the fact that Asia is doing a lot of ultrasonic. Why? It's fast. Of course, it's moving, so you cannot tackle lower than 3 micron accuracy placement, so there's some limits about design, but it is really fast and really efficient. So if you need some throughput, could be there. And laser-assisted bonding. We are speaking about 3.5 on whatever, whatever being silicon, sapphire, diamond maybe, any kind of ALN, ceramic, whatever. You can use laser-assisted soldering. It's also very fast, very efficient, and you don't have any thermomechanical effects on one materials being behaving differently in temperature than the other. So we have that on our machines. There was one name of a Netherlands company just slides before. They have the same machine also, and they have it. And now we've been selling 4 or 5 of them with different laser systems, different powers, different optics. Because yes, we think that this is maybe advanced, but for sure coming in the production and tackling the throughput. I was saying that we were purely European. Yes, we are 240. We are home-based in Berlin, Germany, and we sell everywhere, which means that some of our customers have production machines within Europe, but they also have production facilities in the US or around the US or also in Asia. So I have 2 or 3 customers where they have machines in Europe and they want to copy-paste the solution. Copy-paste the solution in Taiwan. I'm proud of that, thanks to the customer, because Taiwan has almost everything in machinery, but this part is so specific that they developed it in Europe with us. It's a co-development, and they will copy-paste the machine this year in Taiwan. Same thing in the US, and I have another one with tabletop production that has been copy-pasted in Japan and China. Some example of partners and customers. It's not limited. We cannot tell also for all of them, but let's say that we work with most of the whether institutes or industry. And I really, just to finish, I really trust that industry is something giving some structure, because pushing the people, getting the money where it is needed, and having all kind of jobs for us, job for our children's, economics, supply chain. It's all an ecosystem, so let's work as an ecosystem. Thank you.
Thank you very much, Sylvain. If you have any comments or questions, you can visit the booth. Now we are going to move to SMA, and they share their time with Seth. Okay?
Yes. Hello. I'm Segundo Munoz. I'm the owner of SMA. SMA is a company that represents mainly 2 companies. Is SÜSS. SÜSS is a well-known company for mask aligners, spin coaters, wafer bonders, and all the related process in this, also nano imprint and UV nil imprint technology. And another company is ACT. Last year I talked about SMA, but this year I share with ACT. We have Damien Petit, who will explain you about flip chip bonding. The philosophy of our company is not to have many products, is to have the best products in each of the area that we can touch. And so this is why we work with SÜSS, and with ACT I work personally since year 87, last century. Okay? So I let Damien show you about flip chip.
Hola a todos. Me llamo Damien, but for the presentation I will do it in English. So I am the European So I am the European manager for ACT Corporation. ACT Corporation was founded in 1975, so 50 years ago. And since the beginning, we manufacture high accuracy equipment for semiconductor industry. And since the beginning, there is more than 3,000 equipment all around the world, and still working, I think 600 or 700. So we are 90 people in the French Alps, between Geneva and Chamonix. It's very easy to come to see us because we are only at 30 minutes from Geneva Airport. We have 800 square meters of clean rooms, and we have also a demo center. So we are mainly in flip chip process. So you know, you have a chip, you have a substrate, you need to align the chips and the substrate and to bond it. So here at ECT, we always talk about post-bonding accuracy. This is the harder to achieve, and the more accurate machine of the market is the ECT machine, and we are talking about 0.3 microns. That means the alignment is less than 0.1. Sometimes, if you have very good quality of components, we can achieve like 50 nano or 80 nano. Here is our portfolio of machine. We start with a manual machine. Here, the Acura RAM that we deliver here in Spain, for example, is a more accurate manual machine of the market. And we have also other equipment like the Acura 100 or Opto. Acura Plus, it's an Acura with a feeder. Also, the Neo machine we developed with Serality for direct bonding. It's a very good machine. We have a partnership with Swiss Microtech for the direct bonding cluster, for example. And the FC machine that makes the reputation of ECT all around the world. We have several machines in Spain, previous generation. And this machine are very interesting because we develop a leveling system in the head to achieve to adjust the parallelism between components at each bonding. This is very important for quantum chips and infrared sensor or image sensors to have the best gap as possible. So our market is already and university like UPV, for example. And we try to develop very versatile and very flexible machine that you can perform R&D on it and also production. So we have several collaboration, for example, with Serality, HIMEC, VTT, some university also in Spain and Portugal. We have a good reputation on pixel sensor, for example, infrared sensors, X-ray sensors for the space. Here, I think it's a 3. And also for quantum chips, the first Google bond his first quantum chips with FC150, for example, in 2016 or 2017. And also for if you need to stack, so you need to have a very high accuracy in the parallelism, so FC machine is the best. And also for optoelectronics, of course. And also we have a machine for nano imprinting, is the NPS 300. So, for high accuracy, what do you need? You need very good quality of components, for sure. The environment is very important, your clean rooms, your process, and of course, the flitching bonders. Here you can see, with 20 years ago, 60 years ago, the bumps was very big. And now we are talking about pitch of 5 microns of 10 microns. For example, here some beautiful indium bumps of Serality. And here is not only a fly, you can see a lot of bumps. And to bond this, for example, for an infrared detector, 4K, with a pitch of 10 microns, you will need high force, 200 kilos, with the FC150 or FC300. Room temperature for this, because it's indium bumps. And what is very important is the parallelism. As you can see, is you cannot adjust the parallelism at each bonding. Is not good. You will have not good dies. And you need also a real linear Z axis to limit the shift when you bond. This is very important. This is our philosophy, for example. So last year we have 50 years of, it's a lot. If you have some question, we will be happy to talk with you and Segundo and Eduardo Munoz here at our boss. Thank you very much.
Thank you very much, Damien. Any question for Damien? If not, we will move on, since we are a little bit late. Okay, next talk is from Heidelberg Instruments. So please go ahead.
Thank you very much. Buenas tardes, everyone. Thanks for such a presence and interest. And first of all, thank you for the organization of this nice event. We are really pleased to be in the Photonics Integration Week this year in Valencia. I would try to keep it short and easy digestible, the whole presentation. But first, let's have a look of our company. For those who don't know us, we produce laser lithography systems for industrial customers and academic customers. And today we're gonna have a look on the advanced, on the power of direct writing of the laser lithography system of advanced photonic fabrication. Moment. So our product portfolio is divided in about 4 main topics. We have the photomask production with the VPG and ultra systems, and we have for the nano fabrication offer the nanofraser systems, which run with a thermal probe. Oh, with the thermal probe. Moment. Here we go. With the thermal probe. Lithography, we call it. For the microfabrication, we have a quite variation of products with the MLA series and the VPG 300DI systems. The MLA series, they can be from tabletop up to an MLA 300, which can handle over of about 300 nanometer, 300 millimeter substrate sizes. And today, we're going to have a bit deeper look on this 2.5D lithography system. This is the main workhorse for the photonics and optics applications. And yeah, in the DWL family, we basically cover the market of the micro-optics with micro lenses, diffraction optical elements, reflectors, Fresnel lenses, all this kind of structures you can produce with that. Additionally, well, the material research and microengineering and microelectronics can be done with that tools too. On the right, you see very nice DOE and a half Fresnel lens to have a little bit of idea what is the capability of such a tool. And now we go and see what is even beyond the or what is the possibility with the, we call it high resolution bright mode. In here we offer the highest resolution available on the market with 200 nanometer feature size and 300 nanometer lines and spaces specified by us in a 50 nanometer pixel grid for consistent structure quality. The highest write speed available on this resolution and the write speed is independent of structure density. On the right, you see an example of periodic structure of 400 nanometer pitch, and there it's already visible that you can basically always push your system also beyond the limits or the specifications we offer. But here to notice that you have to know very well your resist and your processes afterwards. Here in such a, let's say, grating structure, we can achieve already structure sizes below 300 nanometer with 250 with nice shape sidewalls. To push the limits further, as an example here, we have concentric periodic structures with 500 nanometer pitch. And here notable is that we can write ring structures independent of the angle. Means we have for the horizontal and for the vertical and horizontal structures, we have a deviation in this example of about 330 nanometers for structure sizes of 266 or 235, depends on where you measure. So maybe for the photonics, even more interesting is systems like waveguides, where you have kind of splitters or combiners. And here it's interesting to see that these results, or you can place the structures even closer what the specification from our side is given. We have here structures of 250 roughly of this waveguides and a separation of about 100 nanometers. And you can even have it in a periodic setup of like several waveguides next to each other. Maybe more common in the photonics world are waveguides and ring resonator. And here, interesting is that you basically, with our systems, could tailor the coupling area for the evanescent coupling. And we are here again quite below the specifications. Here the separation is of about 90 nanometers or even down to nearly 60 nanometers. But again, here, very important to know that you have to know your processes and your resists very well. And then you can push the systems really nicely, even below the specified values we give you. Further examples we have here is like standard optics examples of microlens arrays, nicely visualized in these two pictures. Then blaze gratings with different angles, like shown in the middle, or like a diffuser reflector surface with some kind of periodic structures, whatever shape you like. This is more or less the kind of an overview of the power of the grayscaling, we call it. The DWL systems, they have this grayscale option where you can really shape the topography in this 2.5 dimension of the surface. Further examples you can see here, like a Fresnel lens. In this case, it's a full Fresnel lens. Then a diffractive optical element with here this nice SEM picture with basically it's an 8-layer or 8-height system with nicely shaped square features of 2 micrometer size. This squares you see here. Furthermore, you can texture your surface with different shaped structures. For example, here this hexagonal one. Notable is to say that you have the chance to keep your design small. You have to design just this element, like the base element, in this case, this hexagonal structure. And we offer, with all tools, a very powerful software where you can basically use your base design and arrange it in an array for and convert it for this exposure, so you have at the end your full substrate with this array covered. But for your base design, you use a little like for your own base design, you have to just to work for this element, first element of this structure, like this hexagon. I thank you for your time. It was a pleasure to talk to you, and for further questions or discussions, we are pleased to see you at our booth down in the hall. Thank you very much.
Thank you very much. Yeah, we will take the questions directly at the booth, okay?
I think it's the best. Thank you.
Thank you very much. Okay, next talk, it's from VLC Photonics, from Inigo Artundo. So, the floor is yours.
Yeah, hello. Yeah. So thank you, everyone. I think I'm the first company not being a tool vendor, so we are providing services. So many of you already know us, so I'll try to be quick and focus on the main novelties of VLC Photonics in the last year. But, working? Okay. So, for those of you who don't know VLC Photonics, we are a company actually spin-off from this same university. from UPB. We were created in 2011, so that's 15 years ago. This is our anniversary. We still have some laboratories here, but we just moved to this new facility close to the airport in Paterna. So now we have our offices, and very soon we'll have also the full clean room transferred there as well. As Carlos Lee from EPIC mentioned, we were acquired also by the Hitachi High-Tech Group back in 2020, so it's already 5 years with them. And well, what we basically do is we provide design and test services for the development of photonic integrated circuits. So we don't have any product ourselves, we just support others to develop their own chips. We are now a 42 people team, many of us engineers, many of us also with a PhD, so very much focused on the technical developments. So what do? We mostly support companies on the product development, as I mentioned, but not only that, from R&D, research, very early stage, to more engineering and pilot production as our customers grow and scale up. So we work from academics to startups and also large corporations. Obviously, when things go into production, we are out of the game here. So that's our main focus since the last 5 years with Hitachi High-Tech, was also to bridge this gap on the supply chain, not only from the R&D, but also to scale up to production. So just to mention about our new facilities, it's a pretty large infrastructure of 1,500 square meters with class 7 clean room, 300 square meters, and almost 500 square meters laboratories as well. So it's not far from here. So we have been working last year also on scaling up or improving our design offering. We have been providing design services like modeling, simulation, and layout of photonic chips and components over the last years. But now recently we have been focusing more on more advanced design services, including, for example, epitaxy design for 3,5 materials like indium phosphide or gallium arsenide. And this allows us to design more complex active devices like lasers, semiconductor optical amplifiers, VCSELs, modulators, and photodetectors. Especially also, not only in 3.5, but also in silicon photonics, we have been working with the custom silicon photonics modulators, playing with the doping process of the silicon there. We have been also working very much on design for testing. So what needs to be put in place on a layout to make sure that you can scale up and validate this testing easily and cheaply and fast. So we have these test design kits and test guidelines that we can offer to all of you if you are the ones designing these photonic chips. And we have been collaborating with some software companies like Synopsys, GTS Factory, Lucida, to develop also these test design kits that can be just plug and play on their software tools. And then if you follow these guidelines, then we can easily test these chips. In terms of designs, let me emphasize, for example, the designs on modulators that we have been working with, especially in thin film lithium niobate modulator, which, as many of you know, is an emerging technology platform for very high-speed devices. We have been working with the Luxtelligence Foundry, among many others, with very nice results of modulators. Here you can see some results of the 2 different projects we had with SEDETI and with the European Commission, the HTLN project. But not only that, we have been also working with polymer-based modulators as well in silicon photonics. Here we have a collaboration with NLM Photonics and also with Silorix as well, and also with the AMF Foundry, which recently has been acquired by Global Foundries. So now we can say it's modulators on Global Foundries on silicon photonics. Another thing that we have been working on the testing side, in this case, is on visual inspection, because it's very important to when we receive the wafers or the chips or the assemblies, to make sure that these are properly handled, these are properly evaluated before testing and after testing, especially if there is any assembly step in the middle. So we have been working especially with Hitachi, because Hitachi is leader on scanning electron microscopes and CT-SEMs, to implement these kind of services at our clean room. So you can see here, this clean room, actually, if you do the visit at UPV Fab later on, you will see that tool in the clean room. And we have been working quite heavily on that. Also to scale up the die-level testing, we have been working on different tools for that. So we have acquired a die sorter to make sure that after the wafer is diced, we can automatically pick and place the chips and put them into gel packs or trays. there is a very nice video on LinkedIn you can check of this process, and we can work up to large wafer sizes with high accuracy. And also with a collaboration with Suruga Seiki, which is a Japanese company that provides alignment setups. We have been developing an alignment setup that has 2 optical alignment arms, 2 electrical arms, and we can do chip-level alignment semi-automated in these setups. For more automated things, we have been working with Ficontech, which, by the way, you have the representatives here as well. And the most recent addition to our toolset has been this automated die-level tester, which is fully automated chip-level testing, where you place the dies in a tray holder, and then there is a gantry system that picks the dies, puts them into the chuck, performs the optical characterization, both optical and electrical probing, and eventually either puts the dies back to the tray or a different tray to do sorting or binning. Or if the die is good, potentially you can do also epoxy dispensing and UV curing, so potentially you could have also a pigtailing system as well for chips or chip-on-carrier. We have been working very much also to prove the repeatability of this performance, because it's very important if you scale up in volume, right? So as you can see here, we have done some reliability tests on vertical coupling and the repeatability and the stability of these measurements with excellent results, state of the art. Probably very few people can report these kind of results. And also not only for vertical coupling using vertical grating couplers, but also with edge coupling, which is much more difficult if you do it at the wafer level, because in this case there is a trench on the wafer and then you need to embed some kind of periscopes like the ones Nanoscribe showed, and then you perform the coupling at the edge level. So with excellent repeatability and stability. Also on the testing side, we are not focusing only on the traditional 1310 or 1550 nanometers wavelengths, typical for telecom or datacom, but also in the visible down to UV and also up to the mid-infrared, which for many biosensing or gas sensing applications or quantum, this is very much needed. So we have different sources, broadband and laser sources that can cover these wavelengths. As an example here, I can show you some examples of visible measurements that we have been doing on the QPIC project and also on mid-infrared at different projects we had with Menir or Last Step. So with very promising results for some of the technology platforms in that respect. Then polarization is also quite critical in photonics, as you know, and the more we perform testing for different applications, the more we realize how critical it is to have very good control on that. So for that, we have been working on having a setup that is able to control very much this PDL and not only the stability of the polarization, but also the polarization-dependent losses on that. So for that, we have developed this polarization controller with a built-in polarimeter to monitor the polarization on the setups. One of the most critical things also for modulator testing and high-speed testing for transceivers is speed. So being able to test not only the bandwidth or the S parameters of the modulators themselves, but also once this modulator is into a transmitter, then you need to do the system-level testing, making sure that you modulate this and transmit a signal with that. So for that, you need to later on do the measurements at the system level, meaning being able to plot eye diagrams, bit error testing, following different standards, etc. So for that, we are well equipped with tools that can reach 110 GHz modulator testing and up to 400G on 800G transceiver testing, as you can see here. I'm going quite fast, but if you want details, we can discuss later. And finally, just to close the presentation, the last year also we have been working quite a lot on thermal reliability testing, because this is something that no matter what application you are developing in photonic integration, eventually you will need some reliability testing. So for that, we have been installing and developing processes with some ovens and burning racks to be able to do thermal cycling and accelerated lifetime tests, moisture testing, HAST, etc. So for that, we have been developing the process on the engineering side, but of course, if you later on need to do this at the volume level, then with Hitachi, we can really scale that up to different partners. So that's all. Thanks a lot for your attention, and if you have any questions, I'll be around today and tomorrow. Thanks a lot.
Thank you very much, Íñigo. And let's go for the... We have just 2 talks left. Now we are going with electromech.
Hello to everybody. My name is Paolo Massimi. I am a sales manager in Electromech and Vision Robotics, Italian company. I'm here with my colleague Manu of the French and Spanish branch to somehow show you what we can do for you in photonics environment. Just very briefly who we are. We are committed to provide equipment and service in back-end and front-end microelectronics environment. We are quite widely distributed all around Europe. Headquarters is in Milano Gorgonzola, which is maybe more famous for cheese than electronics, but that's the way. And we have also branch in France, Spain. We have a sales office in Morocco, Switzerland, and other countries. So we are more or less in the main markets covering the whole electronics. Photonics, definitely automotive, a lot of power, which is pretty strong in Italy. And definitely photonics is quite interesting, so I'm very happy to stay here for this event for the first time and try to explain which are our outlook in photonics. Basically, as sectors, again, we can cover the most of semiconductor, microwaves, and MEMS products. What I want to show you is just a quick outlook on the product categories that we can support in the environment of photonics. Definitely, we have more than 40 partners somehow categorized in the different 8 products. Typologies, nano and microstructure fabrication, we support Array for wafer inspection and MINC, innovative French company for micro dispense and capillary microprinting. For packaging, Sylvain already introduced FineTech, so no need to spend more words for that. We also support surface treatments and cleaning, again in the front end with PVA Tepla, some code deposition etching, and mono auto wet benches, Italian company SPM. We are also in thermal process, ATV now Kurzherz company for batch vacuum reflow, and dispatch for thermal process. We support adhesion and dispensing with the Musashi technologies that we integrate in our platform. I can show you later in the presentation. And for machine vision, automatic robotics, that's a core business of us. And we have a Synergo company, which is an Italian company, which can provide automation system or industrial level. And we have an internal company, 100% owned by Electromech, named Vision Robotics, that can make custom machine vision and platform. So I talk about equipment, but service is as well important for us. We just built up an ISO 6 clean room, a small one, in our headquarters in Milano, which is intended to pick up some of the technologies of our partners, and including this back-end clean room to make samples or small prototyping for our customers. So universities, research centers, but even in general customers are more than welcome to come and mix their samples in our facility, broadening our experience in our partners for machining and experience specifically for photonics. I come to the point of Vision Robotics. Again, is 100% controlled by us. There are 4 engineers working on that, plus the sales support of me and Manu, and external consulting. And what Vision Robotics does, basically is an integrated solution for photonics, whatever it means. A lot of people already talk about that. We offer manual automation systems for fiber array alignment, pigtailing, as well as integration of micro-optical elements, hybridization assembly. One important point, we do not offer off-the-shelf equipment. We normally listen to customer needs, and we design the platform more than the equipment for the solution they need. So we are able to integrate and assemble in our platform the solution they are looking for. Of course, the strengths are collaborating with the partners for vision automation. The engineers comes from National Instruments Italy that has been absorbed by us. So HMI, all the software interface can be customized really depending on your needs. Last not least, the post-sale support, which is embedded in all our partners. We do not sell only the equipment, but we also support customers with the maintenance service and support with our technical group. Just a couple of pictures of the main features of visual robotics. Automation is our core business. We design the platform as you want. We customize the software and the interface as you want. And we use, for that, high-precision mechanical designs. The applications, depending on the accuracy and the type of the applications, we can work on board, but also in package for the active fiber alignment and pigtailing, as well as the micro-optics alignment and attachment. One important point I want to stress over here, we can also integrate a different type of attached material that is not only the standard dispensing and UV cure, but we can integrate also laser bundles or femtolaser or whatever is intended more suitable for your applications in our machining. Just a picture to show one working machine that is in Italy, in Sant'Anna di Pisa, that is already active in TCIP telecommunication laboratory. We have in pipe several equipment, and I would say that the Spanish market definitely is one of the most interesting for us in Europe. And yes, we are in the booth together with Manu downstairs, waiting for you and your questions and your curiosity about our company. Thanks a lot.
Thank you very much. Thank you. And now we are moving to the last presentation of the session with Photon Export.
Thank you very much, Gloria. Thank you, Pasquale and UPC, for letting us present. I'll try to be fast because it's time to lunch. So let me see if it works. Okay, I'm going to introduce very fast the company, our products, services, and equipment. So I say my name is Ernesto Barrera, sales manager for Spain and Portugal. So our products are consumables for thin film applications. That's our core business. So we provide the sputtering targets, evaporation materials, and we can custom make the sputtering target. That means specific alloys and different shapes. So we provide for the academia small targets like 1 inch diameter, or we provide also to the local industry, I will say, sputtering targets like tubular, molybdenum of 100 kilo targets. So we also provide at the local ophthalmic industry the evaporation materials. You have some pictures here. We can see that's typical evaporation materials. That's some pictures of PVD, that means physical vapor deposition targets. That's some targets we provide, some industrial tubular or planar or R&D targets. We provide also substrates. We distribute substrate. It's with our brand, but it's distribution. So all kinds of substrates from, that means bare substrates, sapphire wafers, for example, or fused silica or special glass, any type of glass wafers.
And what we say, we are a silicon wafer broker because we buy and purchase wafers sometimes from other brokers, and we have agreement with 4 wafer manufacturers. And, we have a local storage in clean room environment in our facility. We are based, I forgot to say that we are based in Barcelona and in Oporto, but the stocks is in Barcelona for wafers. And we provide also accessories for evaporations. For example, you can see here the filaments, tungsten filament for flash evaporation, for example, but also for electron beam, the small tungsten filaments for electron beam evaporation. And we have the quartz crystals to monitor the thickness when you do electron beam evaporation. We provide technical services. Our technical services are really oriented to manufacturing of spot train targets. That means target bonding with indium or with elastomer. This is different that the bonding was talked before. I mean, it's not it's also the same elements, but it's a spot train target bonding. It's completely different. It's a very manual process, and also with elastomer bonding. We are the only company, well, there were not so many competitors in Spain, but we recycle spot train targets for the industry and for the R&D sector. For the R&D sector, due to the fixed cost of recycling, the typical materials we recycle are gold and precious metal, basically. We are homologated as a recycle negotiation on recycling. In Spain, you need to be registered. We are the only company that is registered. And we also recycle for the industry because you need higher levels of consumption. The typical one are tungsten, which is, by the way, is not written here, but tungsten and chromium and zirconium are the typical. It's written there titanium, but I can tell you that titanium is not recyclable. I mean, it could be, but the fixed cost to recycle and the customers don't consume enough to be rentable. And we are ISO 9001 company, so that means that we validate all our suppliers. Then we also provide educational services. We provide mostly on the semiconductor manufacturing process. We provide seminars and workshops in several processes. We have a set of experts. Of course, the one we know the best is physical vapor deposition with sputtering and evaporation, but also in vacuum and also in plasma etching. That we collaborate here with a photonic master degree here. I think it's the 3rd or 4th edition we've collaborating here also. And for the equipment, this is purely distribution, and we have several equipments, and our partners are. We have at least one partner in nanofabrication semiconductor process. I will show some pictures here, and I will state very fast in which process we are present, and we have one or more companies according to, generally to the throughput. For example, in wafer processing, we have an equipment for chemical and mechanical polishing from France, from Aztec. For dicing, we work, you can see from the column at left is small equipment, then in the middle, in the center column is like an R&D size of equipment, and then it's a small or large scale equipment. We represent the French also. I forgot to say that in the first line, the ECM French group, that they're more known in our sector for the LPCVD ovens, for low pressure CVD, but they also do ingot growing, silicon ingot growing equipment. So I'm going to go very fast here. I just say that, for example, for splay cleaning at the end, you can see Shellback, which is some brands are not very well known because with the acquisitions there's going on the semiconductor process. This company, for example, has the spin rinse and dryer from Semitool, which is one of the original spin rinse and dryers for wafers, and it has been changed the name 3 or 4 times, but they still have the patent, and although the patent is about to become public, for this spin rinse and dryer. Another equipment we have is, for example, for plasma immersion ion implantation. We work with IBS, the French company IBS, for large equipment, and for small equipment we have some solutions, but we cannot go with the process. We only sell the equipment, but with a large company like IBS, they do go with the process. For ion beam trimming, we work with Kia System, which is a German company. And I forgot to say, for single wafer cleaning, we work with a company from Austria called Amcos, that has been recently acquired, by the way. And I'm going to go very fast. We have some discount with SPS Europe, so we provide the Polos spin coaters. And for etching and cleaning, dry etching, we work with Plasmatherm for large equipment and cluster, and with Corial, which is the same company because they Plasmatherm acquired Corial like 6 years ago. And they have a small solution for benchtop reactive ion etching equipment with advanced vacuum. And again, you can see now I go directly for rapid thermal processing. We work with a French company, Analysys, which was acquired also by some time ago by the French group based in Grenoble, ECM. And for ILD, we provide also courses for ILD, atomic layer deposition. We used to work with Picosun, but was acquired by Applied Material. So we had to change because they stopped the line for R&D products. And now we work with Swiss Cluster, which is a very innovative company, spin-off from NEMPA, because they're doing ILD and PVD in the same chamber. And yes, and then for electroplating deposition, these kind of equipments are more industrial-based equipment, but we work with Class 1 technology, which is one of the technology leaders for electroplating deposition. And then I will say for inert atmosphere, we work with glove box. This is not really related to semiconductor, but for example, for solar cells application on perovskites, we have a lot of demand on inert atmosphere, and we provide Korea Kion glove box. So that's all. If you have any question, I will be happy to talk to you at the lunch. Thank you very much.
Thank you very much, Ernesto. I would like the audience to thank all the speakers and the exhibitors and the sponsors because they have been supporting the event, as Thomas said, almost from the beginning. So this applause, I think it's for you guys. Thank you. And now, just because before going for the lunch break, our colleague from Sandra from SECFO, she will give us some.
Yes, just super quick before going to lunch. You should have received an email from me these past few days sending you the list of assistants to this fantastic event. So you could request B2B meetings. These B2B meetings are going to happen this afternoon from 5 to 7 p.m. Please check the screen in case you requested a meeting to see in which slot it was assigned to you. Also check it even if you didn't request a meeting, because maybe someone requested a meeting with you. So make sure to check the screen and see that your name is in there or not. Also, please note that these meetings are going to happen at the same time that the laboratory visiting. So please, if your name is here, just make sure to be available on this lot, or make known to us, to me or my colleague Eli, that you are not going to be able to make it, please. Also, just our colleague from ICFO told us that sadly, because an overlap on the schedule, Valerio and Luis Guillermo from ICFO are not going to be able to make it today. They're coming tomorrow. So if you have a meeting assigned with them, sadly, this will not happen today, but you will have plenty of chances to talk to them tomorrow on the coffee breaks and everything. Just make sure this is happening today here in the auditorium from 5 to 7 p.m. If you have any doubt, please come talk with me or my colleague Ellie. Thank you, everyone.
So now it's time for lunch.
Enjoy.
Every bow you break, every smile you fake, every claim you stake, I've been watching you. Every smile you fake, every claim you stake, I've been watching you. Every smile you fake, every claim you stake, I've been watching you. Every smile you fake, every claim you stake, I've been watching you. She wakes up early every morning just to do her hair now, 'cause she cares, yeah. Her day couldn't be right without her makeup. She's never had a makeup. She's just like you and me, but she's homeless. She's homeless. As she stands there singing for money. In my sleep I see her begging, preaching, please. Although her body's not mine, I ask now why, God, why? She's just like you and me, but she's homeless. She's homeless. As she stands there singing for money. She's just like you and me, as she stands there singing for money.
Holding back the years, thinking of the fear I've had so long. When somebody hears Listen to the fear that's gone, strangled by the wishes of Peter, hoping for the arms of Mater. Get to me the sooner of later. Holding back the years, chance for me to escape from all I've known. Holding back the tears, 'cause nothing here has grown. I've wasted all my tears, wasted all those years, and nothing had the chance to be good, and nothing ever could. Yeah, I'll keep holding on. I'll keep holding on. I'll keep holding on. I'll keep holding on. So tight. Wasted all my tears, wasted all those years, and nothing had the chance to be good, 'cause nothing ever could. Oh yeah, oh yeah. I'll keep holding on. I'll keep holding on. I'll keep holding on. I'll keep holding on. Holding, holding, holding on. Yeah, 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 yeah. That's all I have today. It's all I have to say. All I have
Someone told me long ago, there's a calm before the storm. I know it's been coming for some time. When it's over, so they say, it'll rain a sunny day. I know, shining down like water. I wanna know, have you ever seen the rain? I wanna know, have you ever seen the rain? Coming down on a sunny day. Yesterday and the days before, sun is cold and rain is hard. I know wonder. I wanna know, have you ever seen the rain? I wanna know, have you ever seen the rain?
have climbed highest mountain, I have run through the fields, only to be with you, only to be with you. I have run, I have crawled, I have scaled these city walls, only to be with you. But I still haven't found what I'm looking for. But I still haven't found what I'm looking for. I have kissed honey lips, felt the healing fingertips that burn like fire. This burning desire, I have spoken tongue of angels, I have held hand of the devil. It was warm in the night, I was cold as a stone. But I still haven't found what I'm looking for. But I still haven't found what I'm looking for. I believe kingdom come, then all the colors bleed into one, bleed into one. Well, yes, I'm still running. You broke the bonds, loose the chains, curved the cross of my shame, of my shame. You know I believed it. But I still haven't found what I'm looking for. But I still haven't found what I'm looking for. I can feel it coming in the air tonight. Oh Lord, I've been waiting for this moment for all my life. Oh Lord, can you feel it coming in the air tonight? Oh Lord, oh Lord. Well, if you told me we were trying, I would not lend a hand. I have seen your face before, my friend, but I don't know if you know who I am. Well, I wasn't there and I saw what you did. I saw it with my own two eyes. So you can ride off the green. I know where you've been. It's all been a pack of lies. I can feel it coming in the air tonight. Oh Lord, I've been waiting for this moment for all my life. Oh Lord, can you feel it in the air tonight. Oh Lord, oh Lord. Well, I remember, don't worry. How could I ever forget? It's the first time and the last time we ever met. But I know the reason why you keep your silence up. No, no, you don't fool me. The heart doesn't show, but it'll pay as you grow. It's no stranger to you or me. I can feel it coming in the air tonight. Oh Lord, I've been waiting for this moment for all my life. Can you feel it coming in the air tonight? Oh Lord, you don't go change. Can feel it to try and please me. Coming in the air tonight. You never let me down before. Don't imagine you're too familiar, and I don't see you anymore. I would not leave you in times of trouble. We never could have come this far. I took the good times, I'll take the bad times. I'll take you just the way you are. Don't go trying some new fashion. Don't change the color of your hair. You always have my unspoken passion. Although I might not seem to care, don't want clever conversation. I never want to work that hard. I just want someone that I can talk to. I want you just the way you are. I need to know that you will always be the same old someone that I knew. Oh, what will it take till you believe in me the way that I still together. We are one. So much time wasted playing the games with love. So many tears have cried, so much pain inside. But baby, it ain't over till it's over. So many years we've tried to keep our love alive. But baby, it ain't over till it's over. How many times did we give up? But we always work things out. And all my doubts and fear kept me wondering if we always be in love. So many tears have cried, so much pain inside. But baby, it ain't over till it's over. So many years we've tried to keep our love alive. But baby, it ain't over till it's over.
It was 929 Max Street, big city. The sun was going down, there was music all around, it felt so right. It was one of those nights when you feel the world stop turning. You were standing there, there was music in the air. I should have been away, but I knew I have to say, let's run to London, just heading out. Let's run to London, just leaving town. But I really want tonight to last forever. I really want to be with you. Let the music play on down the line tonight. It was one of those nights when you feel the fires burning. Everybody was there, everybody to share. It felt so right. There you were on your own, looking like you were the only one around. I had to be with you, nothing else that I could do. I should have been away, but I knew I have to say, let's run to London, just heading out. Let's run to London, just leaving town. But I really want tonight to last forever. I really want to be with you. Let the music play on down the line tonight. Underneath the starry sky, time was still, but ours must really have rushed by. I didn't realize, but love was in your eyes. I really should have gone, but love went on and on. Let's run to London, just heading out. Let's run to London, a virgin, touch for the very first time, like a virgin. When your heart beats next to mine, gonna give you all my love, boy. My fear is fading fast. Been saving it all for you, 'cause only love can last. You're so fine, and you're mine. Make me strong, yeah, you make me bold. Oh, your love thought out, yeah, your love thought out what was getting cold. Like a virgin, touch for the very first time, like a virgin, with your heartbeat next to mine. Oh, you're so fine, and you're mine. I'll be yours till the end of time, 'cause you make me feel, yeah, you make me feel nothing to hide. Like a virgin, touch for the very first time, like a virgin. When your heart beats next to mine, like a virgin. Ooh, like a virgin. Feels so good inside. When you hold me and your heart beats and you love me. Like a virgin.
Some boys kiss me, some boys hug me. I think they're okay. If they don't give me proper credit, I just walk away. They can beg and they can plead, but they can't see the light. 'Cause the boy with the cold hard cash is always Mr. Right. 'Cause we're living in a material world, and I am a material girl. You know that we're living in a material world, and I am a material girl. A material girl. Some boys romance, some boys slow dance. That's alright with me. If they can't rise my interest, then I have to let them be. Well, some boys try and some boys lie, but I don't let them play. The only boys who save their pennies make my rainy day. 'Cause we're living in a material world, and I am a material girl. You know that we're living in a material world, and I am a material girl. A material girl. now they're after me. 'Cause everybody's living in a material world, and I am a material girl. You know that we're living in a material world, and
Past your door, but you don't live there anymore. It's years since you've been there. Now you disappeared somewhere, like outer space. You found some better place, and I miss you. Like the deserts miss the rain, and I miss you. And I miss you. Like the deserts miss the rain. Could you be that? You always were 2 steps ahead of everyone. We'd walk behind while you run. I look up at your house, and I can almost hear you shout down to me, where I always used to be. And I miss you. Like the deserts miss the rain, and I miss you. And I miss you. Like the deserts miss the rain. Back on the train, I ask myself, why did I come again? Can I confess? I've been hanging around your old address. The years have proved to offer nothing since you moved. You're long gone, but I can move on, and I miss you. Like the deserts miss the rain, and I miss you. And I miss you. Like the deserts miss the rain. And I miss you. And I'm missing you. I miss you. Oh, I miss you. Since you took your love away, I go out every night and sleep all day. Since you took your love away, since you've been gone, I can do whatever I want. I can see whoever I choose. I can eat my dinner in a fancy restaurant, but nothing, I said nothing can take away this blue. 'Cause nothing compares, nothing compares to you. It's been so lonely without you here, like a bird without a song. he's a fool, 'cause nothing compares. Nothing compares to you. Oh, the flowers that you planted, Mama, in the backyard. All died when you went away. I know that living with the baby was sometimes hard, but I'm willing to give it another try. Nothing compares. Ooh, nothing compares. When I look into your eyes, I can see a love restrained. But darling, when I hold you, don't you know I feel the same? 'Cause nothing lasts forever, and we both know hearts can change. And it's hard to hold a candle in the cold November rain. We've been through this such a long, long time, just trying to kill the pain. Lovers always come and lovers always go, and no one's really sure who's letting go today. Walking away, if we could take the time to lay it on the line, I could rest my head just knowing that you were mine. So if you want to love me, then darling, don't refrain. Or I'll just stand up walking in the cold November rain. Do you need some time on your own? Do you need some time all alone? Everybody needs some time on their own. Don't you know you need some time all alone? I know it's hard to keep an open heart when even friends seem not to harm you. But if you could heal a broken heart, wouldn't time be out of charm you? Sometimes I need some time on my own. Sometimes I need some time all alone. Everybody needs some time on their own. Don't you know you need some time all alone? And when your fears subside and shadows still remain, oh yeah, I know that you can love me when there's no one left to blame. So never mind the darkness, we still can find a way. 'Cause nothing lasts forever, even cold November rain. Don't you think that you need somebody? Don't you think that you need someone? Everybody needs somebody, you're not the only one. Don't you think that you need somebody? Don't you think that you need someone? Everybody here 'cause I'm missing you. I'm still alright to smile. I think about you every day now. Was a time when I wasn't sure, but you set my mind at ease. There is no doubt you're in my heart now. Say, woman, take it slow. It will work itself out fine. All we need is just a little patience. Patience. Sit here on the stairs, 'cause I'd rather be alone. If I can't have you right now, I will wait, dear. Sometimes I get so tense, but I can't speed up the time. But you know, love, there's one more thing to consider. Say, woman, take it slow. It will work itself out fine. All we need is just a little patience. Say, sugar, make it slow, and we'll come together fine. All we need is just a little patience. Patience. Ooh, patience. Patience.
Your own personal Jesus, someone to hear your prayers, someone who cares. Your own personal Jesus, someone to hear your prayers, someone who's there. Feeling unknown and you're all alone, flesh and bone by the telephone. Lift up the receiver, I'll make you a believer. Takes a compass, put me to the test. Things on your chest, you need to confess. I was the believer, you know I'm a forgiver. Reach out and touch faith. Your own personal Jesus, someone to hear your prayers, someone who cares. Your own personal Jesus, someone to hear your prayers, someone who's there. Feeling unknown and you're all alone, flesh and bone by the telephone. Lift up the receiver, I'll make you a believer. I was a believer, you know I'm a forgiver. Reach out and touch faith.
your weekend lover. I only wanted to be some kind of friend. Baby, I could never steal you from another. It's such a shame our friendship had to end. Purple rain, purple rain, purple rain, purple rain, purple rain, purple rain. I only wanna see you underneath the purple rain. Honey, I know the times are changing. It's time we all return for something new. That means you too. You say you wanna lead out, but you can't seem to make up your mind. I think you better close it and get you to the purple rain. Purple rain, purple rain, purple rain, purple rain, oh purple rain, purple rain. I wanna see you in the purple rain. Said I wanna see you. I wanna see you in the purple rain. There's a rat in my kitchen. What am I gonna do? There's a rat in my kitchen. What am I gonna do? I'm gonna fix that rat. That's what I'm gonna do. I'm gonna fix that rat. When you open that mouth, you don't talk, you shout, and you give everybody the blame. But when they catch you up, they will shut you up, and you got no one to blame. When you're out in the street, you practice lies and deceit, and you scandalize my name. But when I catch you up, I'm gonna pull you up. I'm gonna check out inside your brain. There's a rat in my kitchen. What am I gonna do? There's a rat in my kitchen. What am I gonna do? I'm gonna fix that rat. That's what I'm gonna do. I'm gonna fix that rat. When you tap on the scene, you make everyone scream, 'cause they know you're so unjust. But when they catch you up, they will kick you up, 'cause you're someone they cannot trust. You invade my space, make me feel disgraced, and you just don't give a damn. If I had my way, if I had my say, I'd like to see you have. There's a rat in my kitchen. What am I gonna do? There's a rat in my kitchen. What am I gonna do? I'm gonna fix that rat. That's what I'm gonna do. I'm gonna fix that rat. come on, let me know. Should I stay or should I go? Should I stay or should I go now? Should I stay or should I go now? If I go, there will be trouble, and if I stay, it will be double. So come on and let me know. Should I stay or should I go? Just indecisions bagging me. If you don't want me, set me free. Exactly whom I'm supposed to be. Don't you know which clothes even fit me? So come on and let me know. Should I stay or should I go? Should I stay or should I go now? Should I stay or should I go now? If I go, there will be trouble, and if I stay, it will be double. So you gotta let. Wonder how you're feeling. There's ringing in my ears, and no one to relate to except the sea. Who can I believe in? I'm kneeling on the floor. There has to be a force. Who do I fall? The stars are out and shining, but all I really wanna know, I want you. Show me the way every day. I want you. Show me the way. When I can see no reason, you're living on your nerves. When someone drops a cup and I submerge, I'm swimming in a circle. I feel I'm going down. There has to be a fool to play my part. Was someone thought of healing, but all I really wanna know, I want you. Show me the way every day. I want you. Show me the way every day. I want you. Day after day.
está en rojo, ¿no? Vale. Vale. Bueno, yo creo que vamos a empezar esta sesión. Gracias a todos por... Thank you everyone. Sorry, almost. Okay, so now we officially start. In this Photonic Integration Week, we thought that it would be nice, since we are gathering the photonic ecosystem, was also to have a session in which the new people that we are introducing in photonics through the PERTE chips chairs. This is an initiative from the Spanish government within the PERTE chip funds. There are 17 chairs, and within these chairs we are organizing different types of actions to promote and to bring photonics into the industry and into the education in universities. And we have hired a different number of people, pre-docs, postdocs, and even technicians that are being trained in the area of photonics. And we thought that it would be a nice idea to have all these people to bring and to tell you what is being done in these chairs, what is their role, who they are. The idea is that they connect between each other, the different chairs, and they connect with the ecosystem that we are trying to gather in these meetings. And since these chairs will be running for 1 more year until June 2027, this was a starting point to let you know what is being done. Out of these 17 chairs, few of them, 7 that we counted, have photonics within them. So this is an initial step to bring all these people together and create a network. The idea is that we all, we've discussed this morning that we need to help each other, we have to network, we have to collaborate. So the best way to collaborate is to know each other. And this is the idea. So we are going to start out of this, well, these are the 17 that are listed. And in the program, you can find the 7 chairs that are involving photonics. And we've invited the people that are higher. So this is not the heads of the chairs, the directors of the chairs talking. What we've decided is let's give the people that are higher in these chairs to present themselves, present the work that is being done. And we start, of course, with the host, with the chair at the UPV, Photonic chip chair. And we have Demetrios Arteanou here to present the chair. You have, please. Now comes the warning. You have 15 minutes. We have to be quite strict because we are already behind schedule, but we have a caution. You have 10 minutes, all of you. This is not just for you. All of you have 10 minutes presentation to give some time for questions. Okay. When I count 10 minutes, I'll stand up. So if I stand up, it's the sign that the time is up.
Okay.
You should be wrapping up.
Okay.
Thank you.
Thank you. Hi, good afternoon, everybody. Good afternoon, everybody. I'm Demetrios Arteanou. I'm a postdoctoral researcher here at University Polytechnic of Valencia. And today I would like to share with you my experience as a postdoc student in this PIC UPV industrial chair and the outlook for future application. I will start a bit talking about the project, the Cattedra PIC UPV. Then I will pass to my personal experience here, starting with my background in photonics, and then the project that I developed together with VLC Photonics in the last year and a half, starting with the PIC characterization and assembly, and passing for the second part of my training in PIC design. So the Cattedra project were already presented in general in our particular case at UPV, where we have the PIC UPV per chip chair. The proposal and modalities of this project, you can find all the information in the website. There was an integrated photonics master with courses on design, fabrication, packaging, and testing of PICs, and even on some application, thanks to our industrial partners that they can share with the students. Then the students can do like a TFM, a trabajo fin de master in the industrial partners. And another proposal the project has was PhD in integrated photonics in various research areas, 3D nanoprint, coherent LIDAR, structural sensing. You have all this information as well on the website. The project was funded as well by our industrial partners. VLC Photonics that was presented even in the morning during the industrial pills, Cypronics, Calsen, Sparks, and Domatidia. In my particular case, I was enrolled in a postdoc project in VLC Photonics. Like I said, it was already presented the company during the morning. That is a company that offers 360 degrees services for photonic integrated circuit technology, consultancy, design, manufacturing, testing, assembly, and packaging. Now we'll move to the presentation of myself. So to my background, I am an electronic engineer. I pursued my electronic master at Polytechnic of Milan. Then I moved to Valencia to participate to a Marie Curie action in an innovating training network named FINES, Fiber Nervous Sensing System. The main objective of my thesis and of the work I developed during 3 years was the design and development of fiber sensor based on fiber Bragg gratings, plastic optical fibers, and all these sensors were for industrial application. As well, in a second part of my project, I designed and developed optical fiber sensing interrogation system. As I said, I was enrolled as a postdoc student in UPV, collaborating with VLC Photonics. At the beginning of my training in PIC, in Photonic Integrated Circuit, we decided to use my previous experience in a lab environment to move all this knowledge and all these skills that I already had to the PIC technology. So I started making PIC tests and assembly. Most of you probably know what assembly is, so I worked on the design of the metal support for PIC, on the PIC placement, fiber array alignment and placement, and wire bonding. After that, I moved to a project of simulation because there was the need to see the thermal management of some assembly that we did in the lab. So I did some thermal simulation of assembly to evaluate the thermo-optic effect and to evaluate new solution for thermal management. One part of this training was as well on test of PIC, the PIC that were tested before they were assembled. After this first part of the training that lasts more or less 6 months, I moved to the part of PIC design because I was very interested and very curious about PIC design, how the chips were made, how the layout were made, and how this world of photonic integrated circuit was working. So I was extremely lucky because just at that time there was a client that was looking for somebody to work on a project to integrate a fiber optic sensor interrogating system on an integrated chip. So I could put all my skill and my knowledge about fiber sensing and applying it to photonic integrated circuit. Unfortunately, and this is one of the main difference between making research in university and making research with a company, I cannot really share everything that I would like to share with you about the project because the chip that I designed and that will be fabricated is under consideration for patenting. What I can say that is a fiber interrogation system for a multi-point fiber sensor. I was introduced also to this design workflow of a PIC. First, the part that was the most stimulating for me, I had to have various meetings with the client to define the PIC schematic depending on the need of the client and what they want to develop in the chip. After that, I passed to the component design and simulation of the photonic element and blocks that were not included in the PDK of the foundry we choose for the project. After that, I used schematic simulation of critical architecture and part of the chip using both numerical mode and FDTD for the component design and numerical interconnect for the system simulation. And finally, I did the layout of the chip using GDS Factory. This is a part of the project that I can share, I can talk to you about. It was needed a coherent detection, and this was one of the most critical architecture of the chip. So I designed an hybrid using the classical scheme using a 4x4 multimode interferometer, and after that a more advanced and alternative implementation using a 2x4 MMI, 2x2 MMI, and a phase shifter. And this alternative implementation showed in the simulation at least having a lower wavelength sensitive loss and lower phase deviation. The hybrid simulation, as I said, they were carried out using numerical interconnect. An optical network analyzer was used to generate the signal, and the phase element is used to sweep the phase of the device under test, that in our case was the fiber sensor. In this way, we can simulate a phase in the fiber sensing, in the signal coming from the fiber sensing. They change the phase compared to a reference signal of our local oscillator. So I will talk to you about the future project I will be involved. So now we'll be involved in other design project while we are waiting for the chip to be fabricated and characterized. And this project will be focused on the design and development of 90-degree hybrid for other wavelength, the whole band, with different architecture using silicon photonics. Even in this case, I cannot really share with you all the application of this element and of this project. Since I think I was very fast, I would like to take this just a couple of minutes to thank Vulsi Photonics for welcoming me and trust me, assigning me project of design, and Pasquale for enrolled me in the postdoc and give me the opportunity to share this experience with you all this afternoon. Thank you very much.
Yes, actually within the schedule. We're getting there. So now, if we have some time as well for questions, if you have any. Okay. I have a couple of questions, just very quickly, because actually one of the things that I noticed is that you started with working in the lab in testing, and then you moved to design. What was useful from the testing that you brought into the design?
Okay, interesting. Okay, all the problems that we encountered in the lab, packaging and assembly. So from scratch, well, if you have to start working on a PIC, for the layout, for example, and you start with a white canvas in layout and you don't really know where to put the first component. I knew that because I was working on testing, so I knew that we need to put all the edge couplers on one side to a certain pitch, try to have all the electrical paths. So it was very useful. I think it was very useful overall for my colleagues that have to package this chip. So I try to follow the guidelines that I already had in mind.
Usually when you draw the flowchart of photonic integrated circuit development, you start with the design and testing is at the end. And start doing it the other way around. It's okay. Is any of that experience, are you involved in the lecturing in the master course?
No, I was not involved in lecturing.
That would be something that would be interesting to add in the course.
Okay.
And you finally mentioned that you are doing, you are considering a patent.
Yes.
Do you know how much that involves?
Yes, of course, but I'm not responsible for it. The client is, so I'm not very worried about that.
Okay.
Yeah, I know it. If I should do all the work for patenting, no, but we have the sale parts that is taking care about that, yes.
Perfect. Okay, I don't know if there is any question that... Okay.
Yes, first, thanks for the talk. You mentioned numerical interconnect. So was this available in your PTK, or did the design yourself you made, did you consider any corner analysis to check the process of the foundry you were working with? Would you have appreciated to have it? Just if you can share some.
You mean the model that I use in interconnect?
Yes.
Yes, mostly of the component we have to do it from scratch. It was simulated with mode, and I exported the model, my own model, from there.
Yeah, but have you in your designs, these components that you designed yourself, did you take into account like the process variation of these components?
Yes, of course. We added data to the simulation.
Okay, thank you very much. And I think that we can move on. And now we have from Universidad Politécnica de Madrid, Gonzalo Soldevilla.
Let me see if I can help you. Okay. Oh, this was easy.
¿Algún sitio para meter esto? Para poder pasar diapositivas con esto.
Creo que tienes.
Tengo, vale. ¿Tiene este láser?
Aquí tienes láser. En este tienes láser.
Va, perfecto.
Creo que este. Creo que este.
Sí, no voy con este. Sí, hace falta paso a mano. Muchas gracias. So, good afternoon, everybody. I'm going to present my work also in another cátedra, in the UPM Indra cátedra. This work will be related to the implementation of an RF phase shifter, which is based on photonics and is monolithically integrated in indium phosphide. This is the key that makes it novel with respect to the literature, at least the literature I have read. By the way, I'm not the only author of this work. We have a lot of other guys who also come from the same group as I do, FEMDATIC, in the Universidad Politécnica de Madrid. Continuing, I'm going to start with an index. I'm going to basically show the introduction of my work, of what the thesis is related to. I'm also going to show the circuit that I'm going to implement in a photonic integrated circuit. I'm going to show some simulations on that circuit, the layout of the PIC, and finally, the packaging that we did, let's say homemade, we did in our own department. So, to begin with, my work is related to the cathedral chip Indra UPM in microelectronics. So, as everybody knows, Indra is a really big Spanish company which is related to different kinds of technological issues. In particular, the defense group, in which is more or less kind of helping me, and also some other data transformation or transport. This cátedra has four working groups. 3 of them are related to microelectronics, like for example the one which focuses on systems based on microprocessors in open architectures, like RISC-V. Another one is based on ASIC for RF and mixed signal for heterointegration. And finally, there is another one which is fabricating different devices which are based on semiconductors. But anyway, the one that I'm going to talk the most about, obviously, is the one in which I am working, which is design and characterization of photonic integrated circuits. Apart from that, there are also some formation programs in which I have enrolled, some of them, and one of them is related to completely to photonics. I'm going to say that this is the only slide I did in Spanish. I didn't know there were going to be English speakers, but the next ones will be everything in English. So, to give some context in my thesis, we have to start talking about phased array antennas. Phased array antennas are, as the name says, an array of antennas which allows to form a complex pattern of radiation and to direct it to a certain direction in space. They are used in radar and RF communication systems. Why? Because they allow to make a better, let's say, a more controlled shape of the radiation pattern, and they also allow to control it better when we have to point it wherever. So the phased array antennas are formed of the different parts that we can see here. There is an RF source or receiver, the radiating elements, which are obviously the antennas, and in the middle we have the beamforming networks. This beamforming network consists of some independent parts, each of which has different control elements, which finally allow to make the shape of the radiation pattern and also to direct it in space. So the beamforming network is the part that I'm going to focus on, but I'm not going to work on it as usual using RF systems. I'm going to work on a beamforming network using microwave photonics, which allows to have some advantages, like for example, the higher bandwidth, the lower response time, and also we will have immunity to electromagnetic interferences of any kind. All right, so regarding the control systems, the control elements, we have two types of control elements, two-time delay control elements and phase shifters. Each of them has their own pros and cons. In particular, two-time delay allows having a higher bandwidth. Actually, it is controlled only by the instruments. However, the devices must be larger, and they are also harder to implement, calibrate, and even control when we are working with them. Whereas the phase shifters are easier to integrate and smaller, but they suffer from the beam squint phenomenon, which means that for different frequencies, the pointing direction will be different. That's why they will only be used for narrowband system. Why am I giving pros for both options? Because I'm going to work on both. In the thesis, I'm going to implement beamforming networks using microwave photonics and in particular photonic integrated circuits. Both approaches will be explored. Actually, in the first half of the thesis, I have already explored the phase shifters, which I will show you, and then I will continue exploring, because I've actually already started, with the two-time delay control elements. So, in this work in particular, I will show an RF phase shifter, which is more electrically integrated in indium phosphide, as I commented. It will serve for beam steering, in particularly in phased array antennas, which will operate in radar bands, X and Q bands. At least in principle. We will hope we will reach the 18 gigahertz. So, this is part of the proposed architecture. In this part, I don't show the whole circuit because I want to explain first a couple of things, and then I will go with the whole circuit. To begin with, we have a laser. I put a DFB because that's what we will finally have. All right, so the laser gives a signal in the frequency of the carrier, whatever it is, and then we have what we call a dual parallel mass center modulator, and in another path, we have a EOPM, an electro-optic phase modulator. All right, so as you see, the dual parallel mass center modulator consists of two paths. One of them has just a mass center modulator, and the other one has a mass sender and an EOPM. Okay, so both mass senders will work on push-pull configuration. Also, they will have a DC bias, which will allow it to work on minimum transmission point. In each mass sender, we will introduce in each mass sender, we will introduce one RF signal, and both of the signals will be in quadrature. So we have a sine and a cosine. Okay, so when we introduce them, we will get for the first one the Fourier transform of the cosine, but centered in the frequency of the carrier, and for the other one, the Fourier transform of the sine. And then we have the EOPM. What will it do? It will introduce a 90 degrees phase shift between both of the paths, and that way we will have after the coupler what we call a single sideband carrier suppressed signal. What does this mean? We have basically a frequency shifter. We have a signal in the frequency of the carrier, and now we have one in the frequency which is the frequency of the carrier plus the frequency of the RF signal. Then We have the frequency of a signal in the frequency of the carrier, which is phase shifted by the EOPM, as we can see here, and it will go to the photodiode to bit with this frequency shifted signal. What will we get? We will get an RF signal in the frequency of which will correspond to the frequency of the RF signal introduced in the master modulators, and a phase shift which will correspond to the phase shift introduced in the EOPM. All right? So the complete circuit design will have a couple of more things, but it's basically the same concept. We have, on the one hand, the DFB inside the PIC, but also we will have a laser input which will allow us to introduce an external laser in case it is needed, or maybe in case we want it for calibration reasons or whatever. We also have an SOA, a semiconductor optical amplifier, to increase the power. Then, at the output, we have, in one of the different channels, we have an optical output which will allow us to visualize both the phase shifted and frequency shifted signal. This is only for calibration, because the idea is that the PIC will allow us to go in with an RF signal and go out with an RF signal, with no need of optical inputs or outputs. Then we have 4 independent paths which allow us to get 4 phase shifted signal, obviously independently phase shifted. So I did some simulations in the software VPI Photonics for this circuit. I basically took some models, and it's interesting to see that the photodiode I took has more or less the noise which I assume would be reasonable, taking into account the temperature, and also it has a bandwidth of 20 gigahertz, which is quite realistic for the photodiodes that I'm going to use in the lab. But anyway, these are just some simulations to give some insight on how it's going to work, but the important thing, obviously, is how it works in the lab. Anyway, I'm going to show a couple of results. For example, for one of the output paths, I introduced different phase shifts in the EOPM, and I got what we can see on the left. This is the output RF signal. We see that the amplitude is the same for any phase shift, which is reasonable. We also see, for example, comparing 2 of them, that when we put a 90-degree phase shift, the signal is phase shifted 90 degrees, and basically everything works as I expected it to. Regarding the spectrum, we can see that the spurious harmonics are outside the studied band, which is really good for our purpose because it won't disturb us when we study the SFTR. Regarding that, I also introduced an RF input with 2 frequencies, and in this case, I realized that, as I expected, obviously, that the spurious intermodulation signals are actually in the radar bands which I am working on. The thing is, take into account the band from 8 to 18 gigas. What does this mean? That we have more than an octave. So the second order intermodulation is also in the band. This reduces quite a lot. Actually, this is the most critical intermodulation order for the SFTR. I studied the SFTR for the worst case, which is 2 frequencies in which the second order intermodulation is inside the band, and I got the result shown in the right figure. Anyway, as I say, the important thing will be when we see it in the lab. But this is really good because if I get, let's say, 25, I will see that I have some problem, just to have some idea. So I designed a PIC taking into account this idea. The circuit that is in this PIC is basically one I showed a couple of slides ago. For example, we have the DFB laser inside the PIC. We have the SOA also inside the PIC to amplify the optical input. We have an RF photodiode per channel for each of the 4 independent channels. And we have an optical input and an optical output. Each one of them is used for seeing the optical signal, whereas the other one is used for introducing the laser. We also have 7 RF contacts in the top part and 24 DC contacts in the bottom part. This is really hard to measure when we are working with the typical probes. All right, for the ones who work on characterization of PICs, with the probes it's really hard to have so many. So we have decided to package it. Anyway, before going to the packaging, I'm showing the real PIC. This is the PIC that we received. We did a couple of photos. It was fabricated by HHI, the Fraunhofer Heinrich Hertz Institute, and it was delivered to us some months ago. What did we do after delivery? We started packaging. The packaging required 2 PCBs, which I designed. We have the RF PCB for the RF contacts and the DC PCB for the DC contacts, all right? So as you can see, in the DC PCB, we soldered some elements for the DC pads, for temperature control and everything, but the harder part was the RF PCB. In this one, we had to design the coplanar waveguides to have 50 ohms and allow us to go to high RF frequency, at least as high as 18 gigahertz. And we also used SMP connectors, which allow to go, in principle, to 40 gigas, so we should be able to modulate in high frequencies. We also did the die bonding above this metal chuck, which will, by the way, serve as a heatsink. And we also did the wire bonding in a wire bonding machine, semi-automatic one actually. And as you can see, we wire bonded the DC contacts, and we also wire bonded the RF contacts. So, as a conclusion, I analyzed the different types of beamforming networks, in particular, how we can implement it using microwave photonics, in particular, photonic integrated circuits. I also designed an RF phase shifter, which is photonic-based, as I showed, that peak, in theory, should work as that. I also analyzed a bit of the behavior of the system, it was, let's say, an easy analysis just to see that the circuit, at least in principle, would work as I expected it to. Then I designed the indium phosphide peak layout, and it was fabricated. I didn't say it, but it was a multi-project wafer in HHI. All right, it was not a custom run. I also did the peak packaging, making the different designs and actually packaging it, which, by the way, was held by other authors like Pablo and Pavel. And finally, now I'm starting characterizing the package peak. I still don't show the results because it's not finished yet. Thank you very much. And just to finish, this work was supported, as I said, by the Cátedra UPM in Microelectronics, and I would like to thank my group, the rest of the authors, and also my supervisors in Indra. Thank you.
We left a few time for questions. You did that on purpose, right? He didn't want questions, so please. Okay.
Thank you for the presentation. How was your relation with the peaks before going to the cátedra? Before?
Well, actually, it's surprising that I say this, but I learned about the peaks existing when I did the interview for the work. It was my relation. I started working on them at the beginning. They showed me the different software and also working on the lab to characterize them and everything. And then I started working on my own peak. But let's say that I could say that I began doing the real peak stuff like 3 months after starting in the lab. At the beginning, I was at the same time I was working on the lab to learn how to characterize and everything, while I was doing the research to see what was done in the literature regarding phase shifters and beamforming networks and everything.
Okay, so it was pretty fast, I would say that.
Well,
you have developed this work in how long?
I started in September last year, but I've been 3 months in a research stay abroad, so let's say 1 year.
Okay.
Yeah.
Good. Thank you very much.
Thank you.
Just a quick question, because there are different sites in your chair, because you also have the RF guys doing ASICs. The projects on each side is given by Indra, is defined by Indra, or are you defining your own project?
All right, so the idea of this, the work plan, which I'm following, it was designed not only by Indra, but also by my supervisors, but as far as I know, because I wasn't there obviously when it happened, but as far as I know, I assume that the supervisor from each group create an idea, and Indra gives feedback and says if they like it or not. But actually, let's say that the idea was already prepared, so we have no idea of what phase shifter I was going to do, but the idea was to do a phase shifter peak, to do all this process, and to measure it, and have, let's say, 1 paper, and then do the same with a 2-time delay. That's the idea. Then let's see what happens.
And did you get any help or support from the RF group, since you are doing RF photonics? Do you have interaction with them?
Actually, luckily, Well, I got some support from some guys from Indra, above all when working in the RF PCB for the coplanar waveguides. But luckily, we had a postdoc, this guy, Pavel Gres, which is also a co-author, that is quite an expert in microelectronics, in electronics in general. So he has designed quite a lot of PCBs, and he helped me, for example, the stack of layers for the RF PCB has already been used by this co-author.
Okay. Nice. So there is collaboration between the university and the...
Well, yeah, there is some collaboration. And also the other way around, because, for example, some guys from Indra have been in the micro-credentials, because I have done the expert title in photonics, and there were some guys from Indra also learning from that. So it's nice to have that.
Okay. Thank you very much.
Thank you.
So we are going to move to the next talk from Universidad Politécnica de Catalunya. And the presenter is Abel Juárez. Thank you for coming.
I think I can remove this. Let's get this out. And you have the laser here. Okay.
Thank you very much.
Okay, hello. My name is Abel Juárez. I'm a master student, so no expert here. I'm going to explain my experience as my first experience as a researcher. Thanks to Cátedra Chip at UPC. There are many companies and institutions linked to this cátedra. I'm working at ICFO, and my job is to build these optical gratings in lithium niobate to excite boundary states in the continuum for on-chip light propagation. We're planning to do it on a 50 micron by 50 micron grating with a 410 nanometer pitch. This is very useful because we can tune the parameters and get more efficiency than just optical coupling it. Through all the characterization of this fabrication, we are using the atomic force microscopy, non-contact mode, and everything we have measured have like this problem where the tip convolution. So we really are not really sure if we're measuring our own tip or our pattern. We're also for many examples, I'm using glass instead of lithium niobate just because it's cheaper. And lithium niobate is very brittle, and they don't let me play much with it. So the first trial we did, like the first thought, it was about just milling. So lithium niobate, it's non-conductive. So we sputtered some ITO, and then we just mill it in the focused ion beam because we thought that it has nanometer resolution. We don't need lithography, no extra steps, and it should be easier. The problem is that it's really slow. This is an example for some parameters about the focused ion beam. We are seeing that it will take about 4 hours to make a grating, 50 by 50 micron grating. And then by tuning the parameters to get a more precise one, we got that we would need a 17-hour grating. 17 hours per grating, so it would take very long time. But this was not the main problem. The thing we did, we said like, okay, let's abandon this. It was because of the field of view. It was very narrow for our resolution. So we changed paths and we aimed for electron beam lithography and reactive ion etching. Here we have many approaches. We choose the one with using a positive tone resist and then etch it in this reactive ion etching. For the reactive ion etching, we will we can play with two parameters, the RF and the ICP. It's like one creates the plasma and the other one directs it to the sample. Here, we knew how to make these patterns with a big field of view, so we could make many gratings in one run. But the main problem is that there are many steps we have to follow, and so many steps we can mess up the process, and it was difficult. In the reactive ion etching, we could not see very much how, like, we didn't know the recipes for this reactive ion etching, so we played with massless alignment lithography to give like a big like some parameters for the recipe. The bad thing about massless alignment lithography is that our resolution needs to be smaller. So this was just to get a main idea of what gases, what powers we will need to use. But we can see here that we got some nice lines, but they're too big. But then when trying with EBL again, with the polymer, we saw some like this was actually the best result we got. You can see it's very inhomogeneous. We aimed for 100 nanometer depth, and we got like 25. So there was something that it wasn't very good. We had burned PMMA, and here I will be talking about dose factor. This dose factor is in the EBL machine. So yeah, here is like the best one with a 0.6 dose factor. We got burnt PMMA, we couldn't see anything, so we thought like, okay, let's again shift our research, and we tried hard mask. Good thing about hard mask is we can put it in the reactive ion etching, and the chromium will not burn. So we tried that, and doing some dose factor tests with the acids of chromium, we saw that the chromium below 0.9, it was not etched. So that gave the idea that maybe we were underexposing the resist. So in one afternoon we had nothing to do, and I said, okay, let's try. Like we crossed this idea, and that's it, and we keep going. And just to make sure, like to clarify, we're still trying another hard mask thing. Instead of etching the chromium, depositing the chromium, because we will have a better selectivity in the reactive ion etching. And finally, we got this trial in one Friday afternoon, like, okay, let's just one more try. We got finally the gratings. They're pretty good for what they has told us. It's pretty homogeneous. The lines could be straighter, but they said that it's a good run. It's a good starting point. So this now, what we're trying to do is, apart from trying again the hard mask thing, is to keep improving with this. And we have a bachelor student working with us also, and he's simulating these patterns, and we're still waiting for his results. And so finally, like a big things, we could make some gratings, but this is not the final. This is not the goal was not to produce the gratings. The goal is to excite bound states in the continuum, and that's one of the things we need to finish with. And yes, just like improve these gratings, couple light, and thanks to Cathedra Chip, because it has taught me like a lot of hands-on experience, in clean room environment using a lot of machines that I didn't know the names. I just asked for how to use them, and then I learned the names. And yeah, that's it. If you have any questions, just now, because I have to leave. Thank you. Hi.
Hi there.
Hi.
Were you able to deconvolute the tip shape to be able to have an AFM characterization with more precision? And side question as well, were you able to obtain any sort of slopes of the sidewalls of the wave that
Yes.
you were able to? Yeah.
Yes. So the AFM thing I mentioned, let me go back. This was with a really broken tip. This image is with a really broken tip. I think I'm going, yeah. This is AFM, for example, and we could see a very nice resolution. This is AFM too. We can actually see some burnt PMMA, so it's like a really small things we could see. And yeah, here the profile is very, very elongated, but this is a 50%, a 50 degree angle of the walls. For what they have told us, we can do some stuff. It's improvable, but yeah, something like. Okay.
Just if you're able to get RMS of the sidewall of your waveguides integrated couplers, would be great.
RF, sorry.
Roughness.
Okay, yeah, no,
Surface of the
roughness, yeah,
sidewall.
we need to do more statistics about the rating. Yeah. This actually, one final thing I forgot to mention. This presentation was done 2 weeks ago. I had no results 2 weeks ago. Like 2 weeks ago, this image didn't exist. So this Friday afternoon thing was 2 weeks ago. So I was about to come here and say, okay, we're trying stuff, and thanks to the tip. So yeah.
Well, it's quite impressive work. Congratulations, because you are doing the fabrication yourself.
Yes, 90 hours in the lab.
That's a good master you're doing.
Yes. Yeah.
And Friday afternoon master is.
Yes.
So what you can basically conclude is that you have to stay longer, right?
Yes, you have to stay the last one in the lab.
Right.
Yes.
You will have offers for hiring if you keep.
I'm open,
Okay.
so.
Oh yes, and just a quick question.
Yes.
Because you said that you are doing this in glass because you shouldn't say that.
Okay.
It's something that is recorded. But where do you get the lithium niobate?
Okay, that thing. It's an old sample. That's a good thing. It's an old sample that was around in the lab because I'm working in the nonlinear optical phenomena group at IGFO, and they have many samples of many sizes of lithium niobate. So they give me the ones that they are not using anymore or the ones that they don't need. So that's another thing. I broke non-usable things. Yeah.
You learn from it.
Yes, exactly. I learn from non-usable things.
Okay.
Yeah.
Thank you very much.
Thank you.
Thank you for coming.
Thank you.
So we are going to move to the next talk from Universidad de Málaga. We have Jorge Rivas. Thank you. I'll help you with this. Here you have the laser, and I think to pass the slides you have to use. Bueno, tienes que usar para pasarle o el botón o esto crea. Es que hay dos aquí, Jorge Rivas. Okay, thank you very much.
Here.
There you go.
Hello everyone, my name is Jorge. I come from the University of Malaga. I'm a predoctoral researcher at this university, and I'm going to present the photonics research that is being done within the PERTE chip chair. I come from the Photonics and Radio Frequency Research Lab from the University of Malaga that has been an important player in the research, in the photonics research that is being done in Spain since 2005, and it is known for its contributions to subjects as transceivers for telecom and datacom, metamaterials, and sensing. We are a group of about 30 researchers, including full professors, assistant and associate professors, students, and hired researchers. You can see a pic of us. I'm not in that photograph, but you can see we are beautiful people. So, but I'm not there. So, the Photonics and Radio Frequency Research Lab is the promoter and founder of two spin-off companies, which are Biohidden and AG Photonics. On one hand, Biohidden is doing photonics-based solutions for medical tests, while AG Photonics is doing integrated transceivers for optical wireless communications. The 30 researchers we are in the research lab, the employees from these two spin-offs makes more than 50 people working in photonics in Malaga. And when I started the degree, this wasn't like this. So for me, I'm happy about that. These two spin-offs are supported by venture capital investors such as Valnet Capital and other deep tech investors. And additionally, we are collaborating with Vodafone in the Vodafone Innovation Hub. In the next slides, you will see that our research in Photonics and RF Research Lab is closely related to the work that is being done in the spin-offs. But first, I will talk a little about the work that we are doing in collaboration with Vodafone, that in simple terms, we are trying to improve RF signal processing to using microwave photonics to improve mobile networks such as 5G and 6G. And I added these two figures that are the lines of work that we are currently working on. The optical phase lock loop is being tested in the lab for the photonic generation of microwave signals, while the phase shifter based on RF beamforming is being fabricated. So in the next months, we are waiting for results. In the biosensing line, we have the objective of developing level 3 photonic sensors for the detection of biomarkers. This means that we don't need any chemical labels to detect molecules, which simplifies the readout. We also want to do multiplex detection that is important for detecting multiple analytes in only one sample. It is important also to have the capability of detecting ultra-low analyte concentrations and to have the capability of do layer discrimination, which could give us better understanding of the biomolecular interactions that occur in the surface of the chip. Biosensors of these characteristics are interesting for industries such as medical diagnostics, environmental monitoring, and food quality control. Here we have two examples of the work that is being done in this research line. On the left, we have a multiplexed biosensing system that has proved the improvement in scalability that we were waiting for. On the other hand, on the right side of the slide, we present a figure about multimode detection that allow us the capability of getting layer discrimination. And we also do the mode handling on the chip. So this is good for our biosensors in terms of compactness, stability, and scalability. This is the last research line that I will talk about. In this line, centered on free space optical communications, we want to develop a photonic receiver. We want to develop a photonic receiver in order to enable photonics links using this, using free space optical communications. And we needed to push forwards to get size, weight, and power efficient devices, as well as we have to face the main problem in free space optical communications, that is the atmospheric link. So we have to develop a system that is robust to atmospheric turbulence. This kind of device is interesting for applications such as telecom, to establish short links and high capacity links for aerial, maritime, and terrestrial platforms, as well in defense, where the immunity to interferences and the low detectability of the optical links are interesting. And of course, for disaster recovery, due to the fast deployment of this kind of systems in comparison to the fiber optics-based communication systems. Due to the complexity of the problem, we decided to divide the work in different working groups. So, for example, we have a working group modeling the atmospheric link, and we have another designing the LED system to couple the propagated beam through the atmosphere to the photonic receiver. Within the photonic receiver, we are about 3 working groups. One of them is the one that is designing the coherent combining mesh, which needs to dynamically compensate the turbulences. We need a control system, and we have there 2 working groups, one working on the control algorithm and another working on the electronics to be the interface between the control algorithm and the photonic chip. We plan this development in 2 phases. The first phase will allow us to prove the control system with the coherent combining mesh using a photonic lantern. But we want in the second phase to substitute the photonic lantern with an array of antennas. So we would get a full integrated photonic receiver. Now I will talk about the micro-credentials a little, because tomorrow my colleague Anna will talk in more detail. But I would like to say that this is the second edition of the micro-credential on integrated photonics. They already started So I recommend that you check the web in case you will be interested in. They are individual courses that you can enroll independently. So depending on your interest, maybe you don't have to do the 10 courses. You can do the one you need. As I said, Anna will explain better tomorrow, but if you have any doubt, you can ask me or go to the website and mail any of the researchers, and we will be happy to help you. And just to finish, I would like to invite you to Malaga in September because, well, you will enjoy Malaga, but there's first the European Conference on Optical Communications that starts in 20th of September and ends in the 24th of September, which we are organizing as part of the local organizing committee, that is the Photonic Art and Radio Frequency Research Lab. And when the ECOC is ending, the Global Photonics Economic Forum is starting. So I think you should, maybe it's a good opportunity to come to Malaga to stay connected with Photonics. That's it. Thank you.
Is there any question for Jorge? Just had a quick question because actually, how many your line of work is in the with AGP Photonics, right?
My work is on the control system for the transceiver, but we are doing this in the Photonics and RF Research Lab. But this is strongly related with the work that is being done with AG Photonics, and there is a collaboration ongoing. So we are communicating every week.
How many of you are hired in the chair to?
I don't know how many are specifically hired within the chair, but on these research lines, we are maybe 10 students or so.
Okay, all right. And but that includes final degree students and master students, final master.
Yes, there is people who is doing his bachelor thesis or his master thesis, or people like me that we are starting the PhD. So.
And to start in your research, did you go through these micro-credentials? What was your training before?
I did the bachelor thesis and my master thesis with Professor Alejandro Ortega.
Okay.
So I did not enroll in any of the micro-credential, but you know that the knowledge is there in the lab. So.
Okay. Thank you very much. Okay, thank you. So now we move to the next chair. The presenter is Jose Carlos Terra. He's with Archimea, right? Okay. So you are actually hired in the company that is involved in the chair.
Yeah.
Okay.
Vale. ¿El láser es este? Este es el que se ve bien. Vale. Que lo tienes aquí. Vale, es este. Gracias.
Hello everyone, my name is Jose Carlos and I'm here as a part of the Cátedra Perte Chip, the one named EPIC, that is between the University Carlos III in Madrid and Archimea Research Center, that is where I'm actually working. So I'm going to keep it short. I'm going to be more focused on the applications that we have been testing in integrated photonics. So first of all, This is the main index I'm going to be following. First, I'm going to explain the cátedra and who is working and participating in the cátedra and the main organization that it's following. Then I'm going to be explaining the applications. We selected the thin film lithium niobate as it is a novel platform, and we selected these two main applications. First of all, quantum communications. So we have been trying to validate the modulation capacities in this platform, and then we switched it to optical phase arrays. That is somewhat similar to what's being explained in one of the previous cátedra in microwave photonics, but in this case it's not microwave, it's fully optical. To do this application in the same optical waves, so we don't have to modulate any photodiodes, and we don't have to get to the RF detection. And after that, we're going to follow with the conclusions. So first of all, what is this cátedra per the chip? It's called EPIC, and it means Electronic and Photonic Integrated Circuits for Quantum Technologies. And it's organized in 4 main applications, 4 main research lines. First, there's this research line, quantum spectroscopy. It's based on integrated circuits for spectroscopy and for sensing. Then you have this second research line, and this is actually where I started working in Archimia. Quantum multisensor using NV centers. NV centers are nitrogen vacancy centers in diamonds, and it's quantum sensing using room temperature, so it has less requirements for working with them. Then we have another research line that it's microelectronics for post-quantum cryptography, and it's mainly FPGA design and architectures. And last of all, and that is what I'm going to be presenting here, it's integrated photonics for QKD, or quantum communications. So who's working in this cátedra? It's several groups, several research groups in Carlos III, the university, and our group it's the Department of Quantum and Photonic Technologies and Safety, what is called now Safety, that it's the department that is working in the FPGA for quantum cryptography. So these are the several groups that are working in this cátedra, and they are all involved in this research. So here you have a photo from the kickoff in Madrid. This is the the bosses in Archimia, and part the research groups in Carlos III in Madrid. And this is the whole group of Archimia Research Center. We are a lot of people, but we have also several main research lines. And now we are going to go with the PIC applications. So this is what I've been working with. First of all, we wanted to validate a QKD-ready platform. So in the first year of my PhD, I started with a first approach to the thin film lithium niobate platforms. That it was our first step with this kind of platforms in Archimia Research Center, because previously we have been working with other substrates. So we started doing the manual characterization of different structures in this platform. This was our first chip. As you can see, there is quite a lot of structures, so we did a lot of statistics, and this was also useful for the foundry, because the foundry was relatively new with the data they have. We used LuxTelligence for lithium niobate. On behalf of the students from Carlos III in Madrid, we had a master student that did the simulations on the QKD circuits, and he used the experimental work that I did in the lab and the characterizations I did to put on some realistic values on his simulations. Then in the lab, we validated the capacity of having incoherent in the imbalance modulators we had in the peak, incoherent modulation, and coherent modulation using an IQ kind of modulator. And after all of that, because the main goal of these kind of applications is to integrate them in a satellite for inter-satellite communications. So we sent it to Walter Technology to have some radiation tests, and we validated that after quite a lot of radiation applied to the chips with gamma rays, these kind of chips were not being damaged after all the radiation. So the VPI values were exactly the same, and the performance was more or less the same also. So after that, I'm going to explain the full peak characterization that I did in the lab. So we validated the structures. We had a lot of passive characterization and also active characterization. For passive characterization, we tested quite a lot of optical paths, bands, crossing. We tested the transmission losses. And for active characterization, we tested both DC values and for the transfer function of the modulators. And we tested also the RF values, looking at the sidebands and the capacity of the modulation that we have, the extinction ratio, and also the bandwidth that we were capable of applying to the peak. And after that, we tested the incoherent modulation formats like OOK or PAN4. And after that, we reached to test a coherent modulation test using basic QPSK. So we have here some images proving what I'm saying. We tested the OK modulation before and after the radiation tests. So we validated that this platform could be used for optical communications, and also tested all the modulators to see the difference and the variance with the lengths. And the key goals that we reached here is that we were able to perform a full ad hoc assembly design. So I did the 3D model for the adjusted some measurements for the 3D models of the heat spreader. We designed the PCB in-house, and we did the die bonding of the peak and the PCB on the same spot on the heat spreader. And then we did the wire bonder to have a full testing capacity. So another goal that we had here is that I designed the whole experiment and the setup using commercially available pieces from several companies. So in the end, we had this kind of setup in the lab, and we were able to work with RF probes and DC probes. And in the end, the main goal that we had to validate is to have a coherent modulation. We did on one polarization. So we had a dual polarization receiver to see that we were able to distinguish between both polarizations. And this is the QPSK that we were implementing in the peak. So we validated that we were able to modulate the signal and in phase and quadrature. So the next application is optical phased arrays. This is similar to what I've mentioned before, that it's similar to the microwave photonics, but this is fully optical. So this is a piece, a corner of the peak that was designed for this project. So we were able to establish beam steering capabilities in lithium niobate. So we did some characterization before and compared with the values that we have from the previous peaks. We did the design of experiment. We had some problems in the end, but we were able to design the experiment fully and checking the final results, and it works fine. We were able to characterize the bias control in this kind of arrays because these arrays are not true time delays. These are modulated via thermo-optical modulators, phase shifters. And we were able to finally validate the optical phase arrays capabilities that we have for beam steering. So an image can talk better. So this is the first result that we have. So this is the same signal, the same laser divided in 8 channels. So this is at the level of the facet. So this is the image that we have at the end of the peak. And if we get out of focus, we start seeing the pattern, the interference patterns between all of those channels. So this is the same signal getting out of focus, and we get this kind of image. And if we modify the phase in between those channels, we are able to modify the pattern, shifting the angle, the output angle of the main lobes for one side of another. This other image can explain it better because this is a 4-channel phase array. In principle, we have the main lobe here centered, and by modifying the relative phase of the channels, we are able to switch and shift the main lobe up and down. And what's better to see this result than a video? So we prepare a video. This is getting out of focus, from the facet to out of focus, with just the position, and then we turn on the bias. So we see the clear pattern. And also, for the shifting up and down, we have better this video explaining when we turn up and down a single phase, because this second video is with a 2-channel array. If we modify this single value of the voltage, we can see the phase shifting up and down, so the final beam is steering up and down also. So these are the final results for this application, validating that we are able to shift the beams. So in conclusion, we have validated some applications in thin film lithium niobate for intersatellite communications. We have validated the capabilities we have to design and characterize peaks in the lab, also to design the experiments. We have tested various modulation formats using radio frequency, and also we have validated that no changes are seen when applied gamma rays radiation, and also in the end we tested the interference pattern shift with a 1-dimensional optical phase array. So in the future, the future steps are to condense both applications in the same chip, because we want to be able to direct the main beam and modulate it for optical communications. And in the near future, the next step for my PhD also is to be able to establish a QKD link to validate also the modulation applied to quantum communication. And that's all for me now.
Thank you very much. Any questions for José Carlos?
Yes, hello, great talk. I wanted to ask if you have experienced any DC drift in LuxTelligence platform.
What? Sorry?
Like DC drift.
DC drift. Yes, when we characterize the transfer function, sometimes even the same modulator was drifted was shifted not by a lot, but yes, we could see some shift in this peak. In the end, in the application, I think it shouldn't count so much because we should be able to have a bias control. So imagine in a final application, we will have a FPGA with a PID controlling the bias. But yes, in the characterization of the peaks, we have seen some small shift. So the starting point could be the quadrature point or some value a little bit higher or lower. It wasn't stable.
Okay, thanks.
Actually, one question, because you said that you are working with thin film lithium niobate after trying with other platforms. Which other platforms did you try?
Well, in my company, because I didn't try with, personally, I didn't try with other platforms because this was my starting project with the PICs. But in my company, we have worked before with indium phosphide, with HHI. We worked also with SOI, with IMF, I think it was mentioned before. And I think we worked also with CNM, and I don't know with which foundry, but yeah, we tested mainly these three substrates.
Silicon nitride, have you tried?
I think not. I think we had a project and we designed something in silicon nitride, but I think in the end we didn't fabricate it.
Okay, thank you very much. And just because you are the first from a company, so what is the support you are getting from the university within the chair?
Well, basically, my supervisor from the university, that is who directs my work in the PhD, but mainly I'm working with projects from the company. So basically, these two projects were 1-year projects from my company, and that's aligned with the expectation from the PhD there in Madrid.
Okay, thank you very much.
Welcome.
So now we are going to move on to the next chair from Vigo. And we have here
David Álvarez.
¿Es este no? Sí, ese es el láser.
Control L.
Aquí, vale, sí.
Si le amplias, control L.
Vale, aquí está la que es en PDF.
Yes. Well, as Guillermo said, my name is David Álvarez Outerello. I'm a postdoctoral researcher in the University of Vigo, and also I'm working as a lab manager there. So the thing is that as a lab manager, I was in touch with all the topics of the cátedra, from the trainings to research. It's not working. It's okay. No. Yes, usually yes. Okay. So I did this presentation for 15 minutes, so I will need to run a little bit. But let's start. So, yes, my lab is the Coffee Lab. It's the Quantum Communication and Photonic Integration, and we are located in Vigo. We have right now 2 laboratories located in the University of Vigo in the telecommunication faculty and in the Institute XP. My main head of the group is Francisco Díaz Otero, and we have a workforce of 3 postdoctoral and around 8 PhD students. So I want to start the first slide with a little bit of context because I want to explain what we are doing in the cátedra and why. So as is well known, every year we have higher and higher volume rates of ICs and also peaks.
And the problem is not this. The problem is that we are also having more complex functionalities that involves in a higher, greater structural complexity. That is translated that we're going to have more in and out waveguides. So in my case, that I did in my thesis, like a manual setup for measurement peaks. This for me is going to be prohibitive. It's like we have an estimation that in the 2040 we're going to have 256 in and out optical outputs. So here's the, I usually say this is my baby because I did the setup here in my thesis. We have an example. We have there, this is a peak, okay? It's a DVR laser designed for a LiDAR application, and it is like 0.5 millimeters by 4 millimeters. Here we don't have all enough DC contacts here. Usually you need like 6 DC contacts to drive perfectly the peak. So you can imagine here, if we have a peak with 256 outputs, and also if we have RF, because we have modulators, we have lasers, so it's for this setup it's prohibitive. So what we want to propose, and it's the output of this chair, the next chip chair, is that we propose the creation of an open access testing and characterization tool of wafer. So it's okay, we cannot measure the spare chips. What happens if we measure in the wafer process? So let's start. As I said, I taught all the topics in the thesis, in the chair next chip. So I want to start with the training. We will have a training that is aimed to design, measurement, and fabrication and packaging of the photonic chips. It's a really hands-on course because we want the students to do the measurements by themselves. So I was working as a professor here, so I was working in the design part, and also I was supervising the measurements. So I teach the students to how they can do the measurements, what they cannot do, these kind of things. And it's a very open program because we have students that have already finished the bachelor, and also we have people that coming back from the industry in order to have an opportunity in the sector. So this is the second course this year, and this is the students that we have the last year. You can see that there is a bunch of different ages, so we have older and young people here. And yeah, let's go with the models. We have 3 main models of the training. One focus in design, so we are covering passive photonic circuits, active photonic circuits, and also RF integrated circuits. We have also fabrication. We have a visit to the ENL, to the clean room of ENL in Braga. The students are there 1 week. And we have also quantum technologies and project management. Here, this is a real picture of our setup. And you can see here one of the chip designs by the students. It's aluminum oxide technology. And this is the pre-alignment stage. So we are doing a pre-alignment stage with the, yes. So we are doing a pre-alignment stage with the fibers and with a 633 nanometer laser. Okay, so the course covers all the workflow of the photonic design. So we have the design capture. Okay, we are going to have a chip, but for what? The microphone. Sorry? The microphone. Oh, yes, sorry. So I'm very focused, so I just, yes. So we are covering all the aspects here. I mean, basically you have an application, okay, you capture the application and the design. You can start with the BB simulation or do it as a circuit simulation, layout. So we are going to have all the workflow here. This is the agile pack with the chiefs of the students. And this is a gift that we usually give at the end of the course. So it's the real one chip with the design. Typically for this technology, we did a thermal variation for the phase modulators and also scanning in wavelengths so we can characterize how it's working the chip or not. In this case, I think it's a Mach Thunder. Now, ring resonator. Okay, related with the research, The main objective is the development of an open access wafer measurement platform. And for that, we have two main tasks here. So the first one is the design of the platform itself. So we want to have a COTS design platform. And the task two is the design of what we are naming here as testing design kit, TDK. For the ones that are used to the design of PICs, usually you have the PDK. So it's like, I don't know if you have used the BPI, but the BPI is like you have the PDK and you can drag and drop the components here. So what we want is to do the same, but in the stage of the testing. Also, there are people that are talking about ADK in the part of the packaging, but this is not related with that. Okay, so in the research line number 1, that is the design of the platform. We have selected a bunch of equipment here. We already have this lambda scan keysight system. We already have this lightweight component analyzer. It's a very expensive equipment. We have also arbitrary wave generators. And we have chosen this MPI table. And we have designed this schematic here in order to be able to use all this equipment with the platform. So we're waiting, but because we are waiting for the rating of this one. But we expect to try it in the next months. Okay, so related with the research line 2, okay, we have the platform, but we need the open source TDK. Why? Because we want to do custom measurements, easy testing, and fast characterization. Okay, so related with the TDK, we have subdivided in two parts. The first one is related with the positioning of the wafer. This is a real wafer of the course. So what we want? We want to develop an open source TDK that automated wafer position detection and alignment correction. So if there is a misalignment in the wafer, they will correct it by itself. They will automatically align the fibers because we are going to use hexapods and composite loop. And we are going also to have an automated position of RF and DC proofs. Because we want to have a vertical coupling. I mean, at the end, we have a wafer, so we cannot have edge coupling. So we want to have vertical coupling. And also we want to test DC and RF. Okay. Also, we have another subsection that is related with the measurements. Usually you have a wafer with a bunch of chips. And the thing is that, okay, you can have all the wafer with the same circuit, so it's easy. But you can have different circuits here in the wafer. So our idea what this is like, okay, we have like black boxes that we can name TDK number 1, TDK number 2, and we can assign it to the chips on the wafer. So what is going to have this TDK? Again, we have the TDK of the positioning and also the TDK related with the measurements. This is already done. We have all the scripts on, and this is real measurements. The thing is that, okay, we can, if the first chip has 2 lasers and a photodiode and this kind of thing, so well, I have also the interface, but I want LAB curves, I want spectral response, thermal analysis, is the laser stable or not, these kind of things. So you can set this very easy and assign to one of these chips. Also, we have a third research line. It's related with LiDAR. So we did a collaboration in another project. And what we did is that we have a development of a monolithic LiDAR that's already done. And it's, we are testing it right now. It's already packaged, but we are more focused here because what we want to have also this be able to be measured here, because we expect that we are going to have a very huge LiDAR production because, as you know, with the automotive sector, they are going to use and implement this kind of LiDARs because it's monolithic, doesn't have moving parts, so it's more reliable, and well, it's our idea at least. So we want to readapt the system in order to be able to measure these LiDARs on wafer. So more or less everything is compatible because, okay, we are going to have power supply, VDC proofs, we're going to have optical testing because these LiDARs can also be, have an external laser for turning on. And we also having the beam steering, because this LiDAR does the beam steering using a wavelength shift. But something that is missing, and we need to think about, it's the measurements of the far field and near field profile, because we want to see if the beam is steering as we want or not. And more or less it is.
Okay, perfect.
Yes, I was too fast maybe. I'm not sure.
No. Perfect. We synchronize.
Yeah, good.
Okay, then I'll take these microphones. You get that one.
Yeah.
Okay, so are there any questions? Please.
Yeah, this is Herman.
I know you.
I was just wondering, based on the dimensions on the wafer or the chips, what's going to be considered for you far field and near field measurements on?
Well, I mean, at the end, you are going to have different sources of light. So when you need to be far enough to have an uniform wavefront. So at that point, we can say that it's a far field. Usually, it's I think it's like 10, 15 centimeters. I think it's enough for this kind of sources.
Any other question? I had a very quick one.
I hope.
Actually,
yes, you can go.
It's good that I'm here. So actually, in that chip that you have there, I see that on the right hand, lower right hand.
Yeah, this is one of my chips. This
okay,
is an example
that's a question I had, because
yes.
You seem to have you have RF probes,
yes.
North and south, DC north and south, and you also said that the light is vertical.
In this case, no. This is an example because I want to decorate
in
the
that one,
presentation.
in one is edge coupling.
And in this one is edge coupling.
The question is, the TDK that you are developing is for the testing facility that you are building up,
yes.
right? What are the rules? Could you measure that on your test facility?
Well, it's not a wafer. I mean, in our right now.
You want to do on wafer?
Yes.
That's why.
Yes.
Okay.
Yes.
Okay. Then I understand the restriction about.
Okay.
But then, for example, if you had that on a wafer, because that would be the edge of the chip, could you measure that?
No, because we don't have access and we don't have lateral access.
No. I mean, assuming that you have optical. I'm on the electrical. I'm already concerned.
Electrical. Well,
I'm already concerned with the electrical.
In this chip is not be able to be measured because you need to also design the chip for the system, because you cannot have DC proofs here, and also RF. So you need to have some kind of currents, because we can use a multi-proof wafer. I mean multi-proof, multi-path proof.
So you have that
multi-contact proof.
On the TDK, you have those rules.
Yes.
Already.
Yes, of course. Yes.
And it's public. Or you have to sign in
right now, no, but it will be.
Will be public.
Yes.
It's open source.
Yes, it's open source.
Okay, thank you very much. So now we have the last presentation, and we are on time, skipping. Yes, please. And we are going to skip the roundtable for agenda issues. And now we have time for the last presentation. Actually, UC3M has 2 chairs, and this is the last photonic chair, and will be presented by Jessica Cesar. Thank you very much.
You're welcome. Hi, good afternoon, everyone. My name is Jessica. I am a postdoc researcher.
Sorry. Sorry.
No. As I was saying, my name is Jessica, and I am a postdoc researcher at the University Carlos III de Madrid. And today I'm going to present the EpiPack chip share, a collaborative initiative between university research and industrial partners. The consortium is formed by BLC Photonic, working on PEEK design and testing,
or Matidia, working on ultra-high resolution optical sensing system. Das Nano, experts in nano-imprint lithography materials and processes. Leapway, focused on high-frequency and millimeter wave systems. Keysight, a global leader for electronic measurement solution. And NanoScribe, pioneers for 3D high-precision micro and nano fabrication. Between all these companies, we expand from design, high-frequency component, testing, assembly, additive manufacturing. So we are not addressing packaging from a single perspective. We are addressing as a system-level change line, because packaging is no longer like the end process. It has been also become geopolitical. For example, let's take Nesperia as an example. It's headquartered here in Europe. It has wafer fabrication in Germany and UK, so on paper, it's like a European company. However, when the Dutch government suspended their CEO, their Chinese CEO, for some security concerns, China responded, and the response was not symbolic. Export restriction affected operation all over Europe, and this exposed something important. Even if fabrication is located here in Europe, if assembly and packaging is located elsewhere, the value chain is no longer under European control. So Europe, and is more specific, Spain, has to invest in packaging and assembly, because who controls packaging will control time to market product. Because as we all know, a chip per se is not a product. It has to go through assembly, packaging, and testing. And from what we have seen from the talks before me, packaging is like between 60 and 80% of the total cost of the product. So if we don't think about assembly and packaging during the design stage, we are gonna lose time and money. That's why it's so important during the mass layout design, having into account the three processes that have to come after: assembly, packaging, and testing finally. So in the epic picture, the vision is clear, is to establish a hybrid integration platform. The idea is to be able to establish infrastructure within the national ecosystem that enables electronic photonic chiplet integration. And for that, we have created three complementary lines of research. We have packaging high frequency, high density interconnects. We also have additive manufacturing, materials and agency for packaging, and artificial intelligence for assembly and test. Within UC3M, these three research lines are supported by three different research groups. We have optoelectronic and laser technology group leading line one of research with Guillermo Carpintero, Alberto Zarzuelo, and Miguel Sanchez as a researcher, myself as a postdoc, and Sergio Rivera as a PhD student. For line two, we have the synthesis and processing of material group led by Alejandro Vares, Cynthia Susana, and Miguel Angel. We have Anderson as a postdoc and Maria Luisa as a PhD student. And for line three, we have the Intelligent System Lab with Jose Maria Mirgol, Maria Araceli Sanchez, Arturo de la Escalera as researchers, David Joagüe as a postdoc, and Pedro Garcia as a PhD student. And all these three groups are supported by our technician, Jose Antonio Jaraba. Now, I'm gonna present some of the work that the PhD student has been done with this, within these three research lines. The first one has been done by Sergio Rivera. he started the characterization of a wire bonding performance up to 40 gigahertz. For that, he measured the transmission response of a straight CPW waveguide with and without wire bonding. As can be seen from the transmission spectrum, the response is very similar. So the wire bonding is not adding any additional or significant losses. The thing is that we were seeing some resonance that we believe become from the substrate, because the PCB that was used for this measurement has a very compact physical properties. So it's probably acting like a high Q cavity resonance. And without the ground plane, it's like generating unwanted traveling wave signals in the spectrum. He has also working on studying the impact of fiber array connection on components, in this case in a PD. For that, he characterized the transmission, the response of the PD before and after fiber array attachment. And as we can see from the figure, the response follows the same trend. So this helps us validate the assembly processing that we are developing within the cátedra. So that's a very good result. The waveguide used for the experiment are property of leap wave, which is also an industrial partner within the cátedra. For the second line, we have the work done by Maria Luisa. She is working on the fabrication of high refractive index filament for 3D printing. She started to create some different samples with thermoplastic matrix and silicon concentrated at different percent, at 10, 20, and 50%. For the preparation of the sample, she was used a rotor mixer with a torque controller and a small scale mill. And for finalizing the samples, she used a hot plate press. So she got like 4 samples for each concentration of silicon. After that, she characterized each of those samples with a terahertz frequency domain spectroscopy system from Toptica, from which she extracted the dielectric property of the material. Using this experimental result, she was able to numerically simulate a cylindrical fiber with different concentrations of silicon, just to analyze the transmission response of each fiber within the terahertz range between 0.2 and 0.4 terahertz. What she saw was that not even at 50% of silicon was any transmission happening. So what she did was by using these experimental values, she estimated higher silicon concentrations value of refractive index and loss tangent, and she realized that at 80% of silicon concentration, there are some frequency-dependent wave-guiding transmission in the fiber, indicating that controlling the concentration of silicon will help you to have some transmission in silicon fibers with a bending radius of 1.5 centimeter. Then the third line is in charge of Pedro Garcia. He's working on automatizing peak testing, because as we all know, testing takes a lot of time. If you have to test one sample, okay, no problem. But the thing is that when you have many peaks with different components, it will take too much time to do it manually. So he has created a custom data set with 300 real images that he has expanded to 1,000 through data augmentation. And with his model, he has been able to identify and detect output waveguides, the whole peak, DC pads, and also RF pads. So after doing this, he moved on to identify the fiber lengths that we usually use for copying light in and out of the chip. Right now, he's working on optimizing the coupling with this automatization system. So, besides the work that we are doing in the lab, we are also creating a state-of-the-art infrastructure for developing photonic device components that combines chip assembly, additive manufacturing, and packaging and testing. For chip assembly, we have the wire bonded TPT, the die bonded Tversky, and the wire bonded 5CI to do like a very precise placement and interconnection of the chips. For additive manufacturing, we have acquired a nanoscribe Quantum X for high precision 3D microfabrication. And for packaging and testing, we also acquired a 5 content machine. But since infrastructure without talent is worthless, we are also launching at UC3M 2 different micro-credential courses. One on design tools that has 5 different design modules. We have design with ANSI Numerical and Nazca. We have IC design with Cadence, RF with ANSI HFSS, PCB with KitKat, in 3D pieces for packaging with Solid Edge. And complementary to that, we have a hands-on training that gonna include a training with the pick and place die bonder, with the TPT, with a 5 content machine for fiber array. We are also gonna do metrology with a SEM and also terahertz characterization. This we expect to be already open for participants in June this year. So to conclude my talk, it's in time, right?
Yes.
I want to say that packaging is no longer just an end process. It's also a capability. And with EpiPack, we want to build this capability here in Spain for everyone to be able to work with that. Thank you.
Thank you very much. Any question? Okay. What is the most challenging work that you see in the chair?
I think assembly, because we have expertise with design and characterization, but assembly is like a new field for us. I think that's what it's going to take most of the time, and it's going to be the hard thing. Yeah.
And personal, what is your personal challenge?
For me, it was everything, because everything was new to me. Like my colleague at UPM, I didn't know about peak until I started working with that. So for me, everything is challenging. Or everything that is new, I think is going to be challenging. Now that you learn it, it's more familiar. But at the beginning, yeah, it takes time.
Okay, so thank you very much. I think thank you to all the presenters from all the chairs. I think it has been very important to at least know what is being done in each of the chairs. It's an impulse that we cannot afford to lose. We are training a lot of young people. That was the idea to bring them here, that there is a whole community that, in which they can join in, and especially that photonic integration is one of the leading research in Spain, and I think it's an opportunity that we have to continue pushing forward. And thankfully, they are the ones that are going to help us push this forward. But they are not alone. It's mainly the message. And I think we have seen all the things that are being done, and I think we can find how to support each other's work to push this forward. So thank you very much for your presentations. Thank you very much for joining the chairs and pushing this forward. And thank you very much for all of you for attending the session.
One last remark before leaving. Remember, some of you have planned the business-to-business meeting. So I will put the agenda again in the main screen. So maybe Ellie, do you want? Okay. So.
Hello, everyone. So the system is very easy. The ones who have the B2B meetings have to stay here. We have now these papers at the walls that are the B2B meeting spot. The one starts here and then continues until finalize at 9. Okay. Then here you can check in one what spot are you and the person. Maybe the person who has the meeting with you had to leave earlier or he doesn't have arrived. So Sandra and I will be here to attend your dubs. And if the person is not here, we can take notes and maybe we can put in contact by email or tomorrow. So we'll do our best to try to connect everyone. But well, these things happen. Sometimes there is an urgency and you have to leave. So do not worry, ask to Sandra to be. And I think that more so, the time is 30 minutes, okay? We start now until 5:30, then 6 and 6:30 until 7, okay? And at the same time, they will have the visit to the labs. And that's all.
Okay, and just 1 minute. If all the speakers of the chairs can come up front, we'll take a picture.
Of all of you, because probably you will want to put this in your social media and your chairs.
Just in case some of you are interested in the lab tours, we will make 3 different, sorry, I forgot about mentioning it. We will make 3 different groups downstairs, and we will bring you to the UPV Fab clean room, the characterization clean room, and if there is anyone from Salvador Sales group, I don't see anyone around. Okay, maybe 2 groups, depending. So if you are interested, we will join, we will make the groups downstairs, okay?
Stay, but I know that it's no use, that